Going to wait to see if it's streaming. I'm gonna try to stay for a longer time today, but I'm not really sure how long. So it's gonna depend on how tired I get. Because after some point, I think that there are diminishing returns to streaming. Like, obviously, I go a lot longer than I go when I stream, but it feels weird to. It's not only that it feels weird, it gets annoying to do several different streams on the same day, like, and uh, puts some resting time between them. And also, resting on stream feels weird as well, so that's usually why I don't stay for longer. So yeah, but I'm gonna try to stay for 5 hours or something like that. And first moment I'm gonna do 1.5, and then I'll eat something. I think I'm gonna start by writing the article about MEV, which I realized that it's better to do this than to do this one. It's better to do MEV first than to do proposer builder separation, because I wanna start from like the beginning, let's say, and I already know MEV. Now I'm contemplating whether or not it's good to do an article about the other stuff that is more basic, but someone that doesn't understand anything about blockchain, if they're gonna know, they're not gonna know. So for example, smart contracts, how do they work, and the principles behind blockchains. But I think I'm not gonna do that because like it's not really the point of the blog that I have. I think it's gonna make me like I want the blog more to be things that I'm learning about, and then that I'm sharing what I learn and that I'm more interested about. So the other kind of stuff I think is too basic to do, but maybe I'll do it in the future. So, but I'll put on the programming category, I think, if I do that on the Solidity. So extractable value. What is MEV? I have no idea what I'm gonna do, what I'm gonna write. It's hard to think about ways to write that, because usually I think straight to the point. So, but if I go straight to the point, I think it becomes too short. But maybe I'll do that. After I do this article, I work on this article, then I'm gonna continue to read this book here, which is probably gonna be really boring if anyone's gonna watch this, but whatever, because I wanna stream my learning process. So, and I already read from up to this chapter here, chapter 5, and I'm gonna continue from here. And it's actually not that complicated, I think, so far. Like, I think I tend to overcomplicate things too much. But after reading the chapters, it seems really simple. And the only thing that I have to study more now is this. So basically, it talks about how the private and public key is just a hash function using this elliptic curve cryptography. So it's pretty much a one-way function where if you have the private key, then it becomes really easy to compute the public key. But if you don't have the private key, then it's almost impossible because of the mathematical property of this function. And is an elliptic curve function, which is this one, which I'm going to study as well. And that's the function that is used to derive, and it's based on prime numbers, I think, and this formula here. Where in this part I didn't understand too much, and that's the reason why I'm gonna study this further. But it pretty much multiplies the private key by this g here, which is a factor, which it explains that if you sum this g multiple different times, you get another point in the elliptic curve, and that's the point of the. It's gonna be essentially a number, which is the equivalent to the public key. and the number is translated into hex. And also I didn't understand that part really well, but I don't know if they, I think they explained something about capital letters, but they didn't explain why it's converted to hex, the number. But pretty much you can pick any number you want from 0 to 2 elevated by 256, which is a very large number. And then that's going to be your private key. And then you put this private key into this elliptic curve, and then you get the public key from that. And then they say that it's better if you choose a true random method, not use any random pseudo random method that programming languages have and things like that, because then it's not truly random and it can be exploitable. And the reason why picking a truly random number is better, because then there's less chance than someone guessing your private key and getting your funds. Because obviously if they guess, then they can get it. But it is kind of weird to think about this. I guess because the numbers are too large, but in my mind it's also kind of weird because there's always a chance that you will pick the number from someone, and that's going to be their private key, and then you're going to be able to access their funds. And they haven't talked about the mnemonic, which is the security phrase to recover the wallet. But they said that the MetaMask and other wallet providers are pretty much an RPC. They provide RPC endpoints, but that's what pretty much they're doing. Under the hood, they just generate the private key using this random thing, or any true random number method. And then they allow you to have the connection to the blockchain through these RPC protocols, which the Ethereum network has the protocol inside, which is this execution APIs here. So, and there are several different implementations of Ethereum. The one that is considered efficient is the Go if, which is GIF, but you have other implementations on other languages as well. So that's pretty much all that it talks about so far. Most of the stuff I was familiar with, but you helped me clarify, especially the wallet thing. It's also good to know the name of this function. And also it says that it uses CACEC 256 to get the public key as well, to sign the transactions. That part I don't remember really well, but I know that after you get the public key, then there's another hash function, which is the CACEC 256, and that's the one that is used to make the transactions, I think, from your public key. But I think I need to review that part because I don't remember really well. Probably when I study this stuff here, because I'm gonna study this more, obviously. So, and I might read these chapters several different times, because that's the other thing about diminishing returns, is that it doesn't matter how hard you go for one day, you're gonna forget most of this stuff. It's just the way that the brain works. So you have to get exposure multiple times. Okay, so what can I write here? I think I'm gonna put some music to write this. Put this. I'm putting the same playlist all the time because I think that is helping me anchor like the state of that I get into for studying. It's probably the best playlist I found as well for this. So here is the part that I was wondering whether or not it's worth it to talk about other stuff, because otherwise it's gonna be too short. But let me think. I was thinking about something like this. Ethereum is a blockchain. I don't know if most popular blockchain protocols. It works by it was previously used to work with proof of model. Now it's moved to proof state. Yeah, but that's the thing that's kind of hard to think about. Because then, do I explain? I guess I can link here to the other ones. I think that's what I'm gonna do. Because I don't have the articles, I'm gonna have to leave it like this now. Then later, when I implement the articles, I put the link there. Transactions. Proof of work system transactions percent for miners to validate and miners should build blocks that contain transactions that would maximize their profits. Transactions are sent for miners to build blocks that contain transactions that will maximize their profits. And this is probably a better way to write it. I think I should write first what comes to my mind and then think about ways to write it in a better way. I'm not very good at writing, but I'm more concerned about getting the point across than to write it perfectly, I think. Because it doesn't really matter too much, I think, for people that are gonna read, as long as I'm able to explain in a good way, that's fine. Miner. How can I say this? Think about it. I want to say that there are miners that, the proof of work system, there are miners that are responsible for validating transactions and putting them on a block. Anyone downloads their history of the blockchain. transactions. Either by smart contract or external accounts. This is the part that I don't know because I don't want to talk about this stuff in this article. Like this is the more of the kind of stuff that it was supposed to be on this one. It's kind of hard to know. Like maybe I shouldn't even put this stuff here. I'm gonna use. I wonder if I should use. I think I should. I used we on previous articles, but I think I should use y, not y. I should use I, because like we is more for a company, but I don't have a company now, so it's just me. But at the same time, I don't know if I'm gonna have a company for this in the future. Like the way that I'm more thinking about this is that the blog is not gonna be so much of a. Like it is gonna be a company if I start making money, but it's more for. I don't see it as something that I wanna grow as a company, if that makes sense. Like I wanna use it as a way to test different MVPs and things like that, so I can eventually build a company on top of it related to blockchains. At least that's what I'm thinking right now. Obviously, I can change my mind in any moment. I don't know what's gonna happen, but I don't know. Like, so I should probably use I think. This is more personal. But the issue with this is that it might be worse for ranking in Google as well. But using I, because Google is they probably give a higher percentage to companies, let's say, a higher percentage of trust, which is another one of those weird things about the game theory of this SEO and search engines. Ethereum is one of the most popular blockchain protocols. Previously, it used to work with a proof of work model, now has moved to a proof of stake. For this system, there is something called a miner, which is someone that offers computing power in order to solve a mathematical puzzle in exchange for tokens from the blockchain protocol. Ethereum, these miners have the ability to build transaction blocks in a way that would maximize the amount of profit tokens they would make from each block. The article I'm going to explain how this process of maximizing amounts of value miner gets more commonly false miner acceptable value and changed the Ethereum ecosystem. And why it is one of the most important aspects of blockchain protocols. I think this is good enough for the intro. Ethereum, these miners have the ability to build transaction blocks in a way that will maximize the amount of profit. In this article, I'm going to explain how this process of maximizing the amount of value a miner will get, more commonly called miner extractable value, has changed the Ethereum ecosystem and why it is one of the most important aspects of blockchain protocols. Now I have to think about a topic to put here, what I'm gonna say first. Because there isn't too much to say actually, that's the thing. This is kind of the battle that I have in my mind as well with the other articles, not only this one. It's like I'm always thinking about, because I know that, I don't know, but I assume that from an SEO perspective and from stuff that I've seen so far, it's better to have longer articles because you keep people engaged more. But at the same time, I don't want to be like one of those people, because it's really annoying when you get to a website and you see that there's a bunch of information that is useless and the person is just stalling to keep you on the site. I hate that bullshit, and I don't want to do this. So ideally, I would want to get straight to the point as I possibly can. But then I'm concerned that it becomes too short, and then it hurts me as well, because then is a problem that's like, it doesn't matter that it gets straight to the point and is better than other articles, because then you don't get rewarded for this because the system is broken, or because most people want to waste a bunch of time. So what people actually want is for the article to be bigger, because most people want to waste time, but I'm not like that. So it's kind of hard to know what is the best approach. Obviously, like most things, probably in the middle, but I'm not really sure. So an article like this, I think I don't have a lot to talk about after this thing here, besides getting straight to the point and saying that it is just explaining the whole arbitrage thing and the front running. Maybe I can do these topics like this. Miner, let's think. In order to have transactions processed, people have to pay a fee in terms it's called gas. So that's their transaction. So that the miner has incentive to validate their transaction. The higher the fee, the higher chance the miner will give that transaction a higher priority. Because of this, and because and now let me think if I should explain front running and other stuff. What I can do as well, I'm gonna have to research this because I don't remember really well how it works. Obviously I studied this on the past on stream several times, but I don't remember really well. Like especially the bandit attack and the other kind of attack where you roll the chain back and it gets really complicated. But I think that's the thing. I don't think I want to talk about those things specifically on this one because those are bigger topics, I think, and it's harder to explain, so it would be better to have an article for each, I think. So I'm gonna keep generic here. In this case, it's called gas, so that the miner has an incentive to validate the transaction. The higher the fee, the higher the chance the miner will give the transaction a higher priority. Also, people realize that's a lot of value knowing which transactions are going to happen first. So, for example, let's say John wants to send 10. Because I need to think about an example that doesn't involve dexes, so I don't have to. Maybe I will explain. Yeah, I think I'll explain dexes on the next topic. But now I have to think about an example where front running would be possible. And maybe NFT is a better case. Buy an NFT that is currently priced at 50, but let me think. Let's use Alice because everyone uses Alice. So Alice is a miner, and she sees that John will buy that NFT. So what he does is to place an order before John to buy and sell it to John a higher price. Because the thing, that's the thing that I don't understand really well about front running, because like in this case how it would work if like the price, the value that Jones sends to the transaction is 15, but how would Alice buy before? That's the thing that I don't know really well. So I think I'm gonna search for this. I don't understand this explanation here. I think I have a better idea. I'm not gonna explain this stuff here. I'm just gonna say the names and then I'm gonna link to other articles. And then I do one article for each. That's a better approach. Because also if I try to explain everything here, it's just gonna be too much stuff. And then once I go write those articles, then I will study more, I remember how it works. A lot of facts. Saturday happened because of that. Most popular. Let's make sure if I'm writing correctly. Let's leave it like this because I think it's correct. Once you have transactions processed, people have to pay a fee. In Ethereum's case, it's called gas, so that the miner has an incentive to validate their transaction. The higher the fee gas, the higher the chance the miner will give the transaction a higher priority. Also, over time, people realized that there is a lot of value in knowing which transactions are going to happen first. So a lot of attacks started happening because of that. Some of the most popular were Don't run in sandwich attacks, bandit attacks, and that's hard prime. No, let me think. Trying to think about a title for this one, and also think about what I'm gonna write next, because I think after this there isn't too much to talk about. Like, the only thing that I'm gonna say is that MEV is this, and maybe explain a little bit of DEX arbitrage. We'll talk about game theory. Miners and construction blocks of transactions. The relationship between miners and the constructional blocks of transactions that create the blockchain. Because miners have this power, what starts to happen over time is that few players starts getting most of the money. It's really annoying to put things in a way, in a text form, and start to think about what is the best way to write it so that people understand. Like, in my head it's really easy to talk about it, let's say, but to write it is very difficult without opening up a bunch of different side things, side tracks. I guess that's the problem, because in my mind then I'm gonna have to start talking about a bunch of other stuff, and then like I'm never gonna finish this one article. It's kinda hard to know the limits of each article. What starts to happen over time is that a few players start getting most of the money. Since it is profitable, you know what transactions are happening first, and you have people that start specializing from knowing what transactions are happening, so they can make arbitrage. You can access, for example, or with NFTs using bots that track wallets. Since it's profitable to know what transactions are happening first, and you have people that start specializing and capitalizing from knowing what transactions are happening, so they can make arbitrage between indexes, for example, or flip NFTs using bots that track wallets. There is an incentive for these two types of people who work together. People searching for the opportunities are called searchers. Maybe I should explain before this one how the whole thing of multiple different mempools work, and how does a mempool work. Yeah, I think I'm gonna do this first. What is a mempool and how does it work? So on this section I explain that there are multiple different mempools and the whole stuff about the dark forest. There's an incentive for these two types of people to work together. People searching for the opportunities are often called searchers. And this part is hard for me because what I want to say, like what I want this to come across is the point of the whole market economy and the Nash equilibrium of the market economy, which for me is like, I wouldn't say obvious, but because that's the problem, because in order to say that, like, there's so many different other concepts that are related to that, that is kind of like almost impossible to reduce that in a way that is gonna make sense when writing without having to go in a bunch of different tangents. That's the hard part here. And so I want to say that the Nash equilibrium is gonna be for, because of the market economy works like that, the Nash equilibrium is gonna be for very few people to have most of the money, because that's how human nature evolves in relationship to the environment, because of the nature of politics, which is the nature of information flow between different bodies of the system. So like every conversation is kind of like playing poker. is the same thing, where either consciously or subconsciously, the two people have a strategy and they are sharing information, and both of the people don't know the full information, so they don't know what's going on with the other person experience fully. They only have access to their words and their appearance. So there's lack of information, and they both have a strategy. And then through this exchange of information, you create this dynamic, which is politics. And then you also create the market economy, which is supply and demand. And then the interaction between the two in relationship to any environment is going to be to go towards an exponential distribution where very few people control everything, because the limbic system gets hacked and is not strong enough to contain the evolution, or not the evolution, the technology that the conscious parts produces in order to control the limbic system. But obviously I can write all of this stuff, because then it becomes a very big thing that I'm gonna have to talk about a bunch of different other topics, and it's not good. And the question is, how do I put it in a way that like it makes sense for people without talking about all of this stuff. Starts to happen over time is that a few players start getting most of the money, since it is profitable to know what transaction happening first, and have people that start specializing. Yeah, I'm also gonna rewrite this because it's not good, but just writing like this to have an idea of what I wanna say. The issue is that to send transactions to a public RPC endpoint, other people, searchers, are going to see and potentially take advantage of the opportunity you found. So did all the work, but they got all the money.
For those who strive so hard.
Because there are many impulse, each one with its RPC connection to Ethereum. New private RPC, new private mempools and RPCs started and created in order to gain an edge over everyone else. The results of this is that Ethereum starts to become more centralized, because now only those that have the most mining power and best strategies can play the game. Which defeats points of the blockchain in the first place. Yeah, I'm gonna have to rewrite this stuff. But after this thing, then I think I'm just gonna do one more and then I'll stop the article. Because what I want to say after is that, because the whole point of this one is so I can write the proposer builder separation thing. So this one is like explaining the reason why the proposer builder separation exists and why most likely they moved to proof of stake. But I've learned through the Ethereum book that the proof of stake thing was already planned in the 200,000 block, which is a very long time ago. So I think they already had in mind, once they created Ethereum, that they would move to proof of stake eventually, which is an interesting thing to think about. Because right now it's on block 15 million or 18 million, something like that. So they have, or maybe something happened on that one, some exploitation. I also saw that they suffered DDoS attacks, denial of service. And because of that, they had to change to do a hard fork at some point. But I think that was after the plan they had to move to proof of stake eventually. We refers to this relationship between miners and the construction of blocks of transactions that create the blockchain. Let me write this one first, then I'll think about. Each miner connects to other miners or anyone running an Ethereum nodes, because Ethereum is just like any other software. So anyone running the software has access to others running software as well. In similar way that your browser communicates with other servers around the world when you navigate the web. Line connection to other miners or anyone running an Ethereum node. Think as if Ethereum is just like any other software, so anyone running the software has access to others running as well. Similar way that your browser communicates with other servers around the world when you navigate the web. However, miners are not all connected. Depending on, this is the part that I, because I don't know yet how it works on the specifics, but I know the concept and that's what I wanna say here. But like, I don't know what it depends on to determine which miners are gonna be connected to other ones. I'm not really sure if it's location. I think it can't be location because that wouldn't make sense. So I don't know, but maybe it is. I don't know what is how is the decision of which miners are going to be connected with is made. So maybe I would just say instead there are several different groups of miners that are connected other, and these groups propagate transactions other groups once they are validated. Yeah, this is shitty. Our transactions become parts of the official. Yeah, let's know this. There you go. Ensure. Good, it's an analogy would be an exchange where people place transactions, but they are not executed right away. They only happen after someone fulfills their order. The difference is that instead of needing someone to fulfill the order, maybe search for fulfill is right. It's written. Fulfill. Yeah, so it's just a difference there, but difference is that instead of needing someone to fulfill the order, the miner has to validate the transaction and include it in a block. Our transactions become part of the official Ethereum blockchain history to a network of miners that perform calculations in order to validate them. It's called a mempool. An analogy will be an exchange where people place transactions but they are not executed right away. They only happen after someone fulfills their order. The difference is that instead of needing someone to fulfill the order, the miner has to validate the transaction and include it in a block. Miners are not all connected. Instead of thinking about it like a giant network of miners across the world. Think about several different groups, smaller groups of miners that are connected to each other. This means that different groups will have different maples and different RPC material. Miners are all connected instead of thinking about it like a giant network of miners across the world. I'm trying to think about an analogy to use here that makes sense. I'm just thinking about it using cities, but I'm not really sure if that makes a lot of sense. But maybe it does. Instead of thinking about it as if everything is one country, but I don't know if it's a good analogy. This means that different groups will have different mempools and a different RPC connection to Ethereum. I think that this session is probably good enough to put it like this. Where transactions become part of the official Ethereum blockchain history, they go through a network of miners that perform calculations in order to validate them. And decides its position. Merge validate them and deciding what position they will be putting the block of transactions. This is called a mempool. Analogy will be an exchange where people place transactions but they are not executed right away after someone fulfills their order. The difference is that instead of needing someone to fulfill the order, miner has to validate the transactions and include it in a block. Miners are not all connected. Instead of thinking about it like a giant network of miners across the world, think about several different smaller groups of miners that are connected to each other. This means that different groups will have different mempools and a different RPC connection to Ethereum. MEV refers to this relationship between miners and the construction of blocks of transactions that create the blockchain. Yeah, I'm gonna rewrite this part here. because there is money to be made by observing transactions that are happening and in what order they will include it in a block. A group of people starts to specialize in creating bots to take advantage of these opportunities. This group is often called searchers. So, a relationship between different pools, miners, and searchers starts to happen. Because not all mempools are private, can become So a relationship between different mempools, miners, and searchers starts to happen. Because some mempools can be private, meaning that the transactions will only be seen by everyone once they are already included in Ethereum. But inside the mempool, only a selected group of miners and searchers will be able to see them. This becomes a large problem for Ethereum because it is a centralized using force. The miners that have the most computation power and the connection with the best searchers, you gain more money and use that money and you invest it, so even more influence over the network. Because of this, what ends up happening is that these miners and RPC providers start to gain control over the blockchain. wanna erase this part here. Because there's money to be made by observing the transactions that are happening and in what order they will be included in a block. A group of people starts to specialize in creating bots that will take advantage of these opportunities. These people are often called searchers. So a relationship between the different mempools, miners, and searchers starts to happen, because some mempools can be private, meaning that the transactions will only be seen by everyone once they are already included in Ethereum. And the mempool only select the... Maybe we should start with this one. Because some mempools can be private, meaning that the transactions will only be seen. I think this is wrong. It will only be seen. Because some mempools can be private, meaning that the transactions will only be seen by everyone. Yeah. They are already included in Ethereum. Inside the mempool, only select a group of miners. Some mempools can be private, meaning that they're just going to be seen by everyone once they are. But some mempools can be private, meaning that the transactions will only be seen by everyone once they are already included in Ethereum and not inside the mempool. Since only select a group of miners and searchers will be able to see them. This is just a better way to write this, but And I don't know. I think it's better if I study more before doing this, because then I'll be able to talk more about in detail of the differences, because I still don't know really well. Like, to me, that's the question that I have now is what is the both how is decided the peers for each one, what decides that, and the second question is how is it possible that one of the some of the mempools should be private and some of them should be public. Because I understand that the whole Flashbots thing is that they created the private thing, and I guess it's just because of an agreement. It's not something that is to do with Ethereum, probably. Like, it's just, I assume that it's just like creating a normal server where you create a normal server that is centralized, and then through that server you send the transactions only to the miners that are part of a specific pool. But then it also doesn't make a lot of sense, because then, like, how would it be possible to make a mempool private where only a few people have access, only some miners have access to the mempool? That's what I don't understand. The thing is, I wanted to do this article now because I wanted to explain the basic stuff first. But I think the issue is that I probably can't build this article without knowing this stuff. Like, what I wanted to do in this article is just explain what I just talked about, the normal, like the concept, and not the specifics. But I think it's very difficult to explain, like, through text this without talking about the specifics. And I can do it, but I guess it's not very good, I think. And the idea that I had was to do this article first, then go and read the book, and then study this stuff, and then write the other articles. But I think there isn't a way, because I want to start writing more articles now, so I have more articles on the blockchain category of the thing. But like, everything is really connected with each other, so I think that there's no way to start writing the articles now without knowing all the other stuff. Like, ideally what I was thinking about doing is writing the articles as I go, but then, like, the more I think about it, the more I realize that I have to know everything first to write, because all the articles are connected to each other. And this is another challenge that I'm having, is how do I decide what's the line there to cut articles, the topics apart, and connect them in different ways. I think I'm gonna put, like, searchers and all of it. So after, it's okay, so explain this stuff, then transaction, the mempool, and here explain this relationship between private and public mempools, and how this centralizes things. And then after this, I explain what is MEV. But I think MEV is already explained through here. I think I'm gonna write it on the conclusion actually. After this, I'm gonna write the conclusion here. Because there isn't anything else that I want to say about this, I think. So the only part that I'm stuck is this one, which is the difference between private and public mempools. The specifics of how it is determined, how the miners connect with each other in the mempool. How is it possible that you have the... And if that's the only thing that made it so that they wanted to do the proposer-builder separation, it's another thing. Because I think that it may be the fundamental reason why they wanted to do it like this, but I also think that there's other reasons, I think. But maybe not, actually. Because I think, yeah, not sure. Maybe I should talk about wallet providers as well. Which is also something that I don't know really well. Okay, is exactly what is the relationship between the wallet providers and the mempools. Because I think it's three different types of people. Is the mempools, which is the miners. Then you have the wallet providers, which are the RPC endpoints through the miners. And then you have the searchers, which are the people searching for the opportunities in the blockchain. And obviously searcher and miners are very strongly correlated because it is very beneficial to also be a miner if you are a searcher. Because obviously the miners make the most money. Because they are the ones receiving the money from the gas wars to place the transactions. And I guess the thing that I don't know really well is like if the proposer builder separation thing solves this problem, because I don't think it does. I think like, it doesn't change much, I think. You still have the problem of most, because mining is going to be more and more expensive, especially the longer the blockchain is alive, because there's more transaction, more history, so more hardware that you need. So the only argument is that you need less hardware because then you can validate. But I don't think that's strong enough, because it doesn't matter, because anyway that the person that is creating the blocks is still the miners, and they still have the power there, I think. So those are the parts that I don't understand really well, I think. That's what I'm trying to clarify. So I think that it is what is worth it to do here is just to read the book and then study more, I think, before I write these articles. I think up until this part is probably good, but then here, and the other thing is that I have to think about how I'm gonna split this into different categories. In the conclusion, I'll probably say that MEV is pretty much this, is the priority in the order of transactions, and that this causes a centralizing force through the blockchain. And that's the thing is, I also wanted to talk about Nash equilibrium here, and this whole thing about, because I think it is very important to talk about this. It's a very big problem, and I think that it's actually the most essential problem of the blockchains in general. I think that the whole point of the blockchain is to try to solve this problem. which is how to regulate centralization in an autonomous way. I think that's what blockchain is about, under the hood, like the fundamental property of it. That's the whole point, I think. Let's see how long I have. 3 minutes. Yeah. So while I eat, I'm gonna read the book. The book here with the text to speech.
Wallets.
I should also read the yellow paper again at some point. I guess a better way would be to say like this: some impulse are public and others can be private, meaning that in some impulse only the people that have access to that mempool can see the transactions in the pool before they get included in the blockchain on other pools. Everyone can see what transactions are parts of. This means that private impulse give an extra edge to searchers looking for opportunities because they could be sniped by other searchers, making all of their work useless and exploits, and by just observer that transactions and stealing the opportunities. I think now that this part is good, but I'm gonna probably study more and redo the article or this part once I understand the difference more. I also have to think about if it makes sense to put the difference here when I study. But maybe it does because there isn't any other topic. I think that, yeah, I think this one is the one that makes most sense to put the distinction between the private pool and the public, because it is what MEV, the whole MEV thing is about, I think. Like the core of the issue is the connection there, the way that the connection happens. Because there is money to be made by observing the transactions that are happening and in what order they will be included in a block, a group of people start to specialize in creating bots that will take advantage of these opportunities. These people are often called searchers. Some mempools are public and others can be private, meaning that in some mempools only the people, miners and others running. Yeah, I'm not sure if this is good because of the way that this is here. Like it goes from this to something completely different. Maybe I should do it like this. Made by observing the transactions that are happening and in what order they will be included in a block. Group of people starts to specialize in creating bots that will take advantage of these opportunities. These people are often called searchers. Some mempools are public and others can be private, meaning that some mempools only the people, miners, and others that are running a node have access to that mempool can see the transactions in the pool before they get included in the blockchain. Other pools, everyone can see what transactions are part of the pool. This means that the private mempools give an extra edge to searchers looking for opportunities because they don't want to be sniped by other searchers. Making all of their work useless because someone can exploit them by just observing their transactions and stealing the opportunities. This becomes a large problem for Ethereum because it is a centralizing force. The miners that have the most computational power and the connection to the best searchers will gain more money and will invested so reinvested so they gain even more influence over the network. Because of this, what ends up happening is that these miners and wallet providers start to gain control over the blockchain, which defeats the point of having the blockchain in the first place. Reason why is because the miners work as a bridge between the external world and the blockchain. So if the only people that are validating transactions think about it a different way. I'll leave it like this for now. I'm gonna read the book now. I'm gonna go grab something to eat and then read the book while I eat. So I'll be right back.
Wallets. At a high level, a wallet is a software application that serves as the primary user interface to Ethereum. The wallet controls access to a user's money, managing keys and addresses, tracking the balance, and creating and signing transactions. In addition, some Ethereum wallets can also interact with contracts, such as ERC20 tokens. More narrowly, from a programmer's perspective, the word wallet refers to the system used to store and manage a user's keys. Every wallet has a key management component. For some wallets, that's all there is. Other wallets are part of a much broader category, that of browsers, which are interfaces to Ethereum-based decentralized applications, or dApps, which we will examine in more detail in Decentralized Applications Cap. There are no clear lines of distinction between the various categories that are conflated under the term wallet. In this chapter we will look at wallets as containers for private keys, and as systems for managing these keys. Wallet Technology Overview. In this section we summarize the various technologies used to construct user-friendly, secure, and flexible Ethereum wallets. One key consideration in designing wallets is balancing convenience and privacy. The most convenient Ethereum wallet is one with a single private key and address that you reuse for everything. Unfortunately, such a solution is a privacy nightmare, as anyone can easily track and correlate all your transactions. Using a new key for every transaction is best for privacy, but becomes very difficult to manage. The correct balance is difficult to achieve, but that's why good wallet design is paramount. A common misconception about Ethereum is that Ethereum wallets contain Ether or tokens. In fact, very strictly speaking, the wallet holds only keys. The Ether or other tokens are recorded on the Ethereum blockchain. Users control the tokens on the network by signing transactions with the keys in their wallets. In a sense, an Ethereum wallet is a keychain. Having said that, given that the keys held by the wallet are the only things that are needed to transfer Ether or tokens to others, in practice this distinction is fairly irrelevant. Where the difference does matter is in changing one's mindset from dealing with the centralized system of conventional banking, where only you, and the bank, can see the money in your account. And you only need convince the bank that you want to move funds to make a transaction, to the decentralized system of blockchain platforms, where everyone can see the Ether balance of an account. Although they probably don't know the account's owner, and everyone needs to be convinced the owner wants to move funds for a transaction to be enacted. In practice this means that there is an independent way to check an account's balance, without needing its wallet. Moreover, you can move your account handling from your current wallet to a different wallet, if you grow to dislike the wallet app you started out using. Ethereum wallets contain keys, not Ether, or tokens. Wallets are like keychains containing pairs of private and public keys. Users sign transactions with the private keys, thereby proving they own the Ether. The Ether is stored on the blockchain. There are two primary types of wallets, distinguished by whether the keys they contain are related to each other or not. The first type is a non-deterministic wallet, where each key is independently generated from a different random number. The keys are not related to each other. This type of wallet is also known as a JBOK wallet, from the phrase, just a bunch of keys. The second type of wallet is a deterministic wallet, where all the keys are derived from a single master key, known as the seed. All the keys in this type of wallet are related to each other and can be generated again if one has the original seed. There are a number of different key derivation methods used in deterministic wallets. The most commonly used derivation method uses a tree-like structure, as described in hierarchical deterministic wallets, BIP32/BIP44. To make deterministic wallets slightly more secure against data loss accidents, such as having your phone stolen or dropping it in the toilet. The seeds are often encoded as a list of words, in English or another language, for you to write down and use in the event of an accident. These are known as the wallet's mnemonic code words. Of course, if someone gets hold of your mnemonic code words, then they can also recreate your wallet and thus gain access to your Ether and smart contracts. As such, be very, very careful with your recovery word list. Never store it electronically, in a file, on your computer or phone. Write it down on paper and store it in a safe and secure place. Non-deterministic, random, wallets. In the first Ethereum wallet, produced for the Ethereum presale, each wallet file stored a single randomly generated private key. Such wallets are being replaced with deterministic wallets because these old-style wallets are in many ways inferior. For example, it is considered good practice to avoid Ethereum address reuse as part of maximizing your privacy while using Ethereum I.E. to use a new address, which needs a new private key, every time you receive funds. You can go further and use a new address for each transaction, although this can get expensive if you deal a lot with tokens. To follow this practice, a non-deterministic wallet will need to regularly increase its list of keys, which means you will need to make regular backups. If you ever lose your data, disk failure, drink accident, phone stolen, before you've managed to back up your wallet, you will lose access to your funds and smart contracts. The Type 0 non-deterministic wallets are the hardest to deal with, because they create a new wallet file for every new address in a just-in-time manner. Nevertheless, many Ethereum clients, including Geth, use a keystore file, which is a JSON encoded file that contains a single, randomly generated, private key, encrypted by a passphrase for extra security. The JSON file's contents look like this. Address, 001D3F1F827552811140227BD3ECF1F086BA0F9, crypto, cipher, AES128CTR, ciphertext, 233A9F4223C0C13394B504B6to5DF02587C8BF1. The keystore format uses a key derivation function, KDF, also known as a password stretching algorithm, which protects against brute force, dictionary, and rainbow table attacks. In simple terms, the private key is not encrypted by the passphrase directly. Instead, the passphrase is stretched by repeatedly hashing it. The hashing function is repeated for 262,144 rounds, which can be seen in the keystore JSON as the parameter crypto.caveparams.n. An attacker trying to brute force the passphrase would have to apply 262,144 rounds of hashing for every attempted passphrase, which slows down the attack sufficiently to make it infeasible for passphrase of sufficient complexity and length. There are a number of software libraries that can read and write the keystore format, such as the JavaScript library Ethereum. The use of non-deterministic wallets is discouraged for anything other than simple tests. They are too cumbersome to back up and use for anything but the most basic of situations. Instead, use an industry standard. Deterministic, seeded, wallets. Deterministic or seeded wallets are wallets that contain private keys that are all derived from a single master key, or seed. The seed is a randomly generated number that is combined with other data, such as an index number or chain code, see extended public and private keys, to derive any number of private keys. In a deterministic wallet, the seed is sufficient to recover all the derived keys, and therefore a single backup, at creation time, is sufficient to secure all the funds and smart contracts in the wallet. The seed is also sufficient for a wallet export or import, allowing for easy migration of all the keys between different wallet implementations. This design makes the security of the seed of utmost importance, as only the seed is needed to gain access to the entire wallet. On the other hand, being able to focus security efforts on a single piece of data can be seen as an advantage. Hierarchical deterministic wallets, BIP32/BIP44. Deterministic wallets were developed to make it easy to derive many keys from a single seed. Currently, the most advanced form of deterministic wallet is the hierarchical deterministic (HD) wallet defined by Bitcoin's BIP32 standard. HD wallets contain keys derived in a tree structure, such that a parent key can derive a sequence of child keys, each of which can derive a sequence of grandchild keys, and so on. This tree structure is illustrated in HD wallet, a tree of keys generated from a single seed. HD wallets offer a few key advantages over simpler deterministic wallets. First, the tree structure can be used to express additional organizational meaning, such as when a specific branch of subkeys is used to receive incoming payments and a different branch is used to receive change from outgoing payments. Branches of keys can also be used in corporate settings, allocating different branches to departments, subsidiaries, specific functions, or accounting categories. The second advantage of HD wallets is that users can create a sequence of public keys without having access to the corresponding private keys. This allows HD wallets to be used on an insecure server or in a watch-only or receive-only capacity, where the wallet doesn't have the private keys that can spend the funds. Seeds and mnemonic codes, BIP39. There are many ways to encode a private key for secure backup and retrieval. The currently preferred method is using a sequence of words that, when taken together in the correct order, can uniquely recreate the private key. This is sometimes known as a mnemonic, and the approach has been standardized by BIP39. Today, many Ethereum wallets, as well as wallets for other cryptocurrencies, use this standard, and can import and export seeds for backup and recovery using interoperable mnemonics. In practical terms, the chance of an error when writing down the hex sequence is unacceptably high. In contrast, the list of known words is quite easy to deal with, mainly because there is a high level of redundancy in the writing of words, especially English words. If insect had been recorded by accident, it could quickly be determined, upon the need for wallet recovery, that insect is not a valid English word and that insect should be used instead. We are talking about writing down a representation of the seed because that is good practice when managing HD wallets. The seed is needed to recover a wallet in the case of data loss, whether through accident or theft, so keeping a backup is very prudent. However, the seed must be kept extremely private, so digital backups should be carefully avoided, hence the earlier advice to back up with pen and paper. In summary, the use of a recovery word list to encode the seed for an HD wallet makes for the easiest way to safely export, transcribe, record on paper, read without error, and import a private key set into another wallet. Wallet best practices. As cryptocurrency wallet technology has matured, certain common industry standards have emerged that make wallets broadly interoperable, easy to use, secure, and flexible. These standards also allow wallets to derive keys for multiple different cryptocurrencies, all from a single mnemonic. These common standards are. These standards may change or be obsolete by future developments, but for now they form a set of interlocking technologies that have become the de facto wallet standard for most blockchain platforms and their cryptocurrencies. The standards have been adopted by a broad range of software and hardware wallets, making all these wallets interoperable. A user can export a mnemonic generated in one of these wallets and import it to another wallet, recovering all keys and addresses. Some examples of software wallets supporting these standards include, listed alphabetically, Jax, MetaMask, MyCrypto, and MyEther wallet, MEV. Examples of hardware wallets supporting these standards include Keepkey, Ledger, and Trezor. If you are implementing an Ethereum wallet, it should be built as an HD wallet, with a seed encoded as a mnemonic code for backup, following the BIP32, BIP39, BIP43, and BIP44 standards, as described in the following sections. Mnemonic code words, BIP39. Mnemonic code words are word sequences that encode a random number used as a seed to derive a deterministic wallet. The sequence of words is sufficient to recreate the seed, and from there recreate the wallet in all the derived keys. A wallet application that implements deterministic wallets with mnemonic words will show the user a sequence of 12 to 24 words when first creating a wallet. That sequence of words is the wallet backup, and can be used to recover and recreate all the keys in the same or any compatible wallet application. As we explained earlier, mnemonic word lists make it easier for users to back up wallets, because they are easy to read and correctly transcribe. Mnemonic words are often confused with brain wallets. They are not the same. The primary difference is that a brain wallet consists of words chosen by the user, whereas mnemonic words are created randomly by the wallet and presented to the user. This important difference makes mnemonic words much more secure, because humans are very poor sources of randomness. Perhaps more importantly, using the term brain wallet suggests that the words have to be memorized, which is a terrible idea, and a recipe for not having your backup when you need it. Mnemonic codes are defined in BIP39. Note that BIP39 is one implementation of a mnemonic code standard. There is a different standard, with a different set of words, used by the Electrum Bitcoin wallet in predating BIP39. BIP39 was proposed by the company behind the Trezor hardware wallet and is incompatible with Electrum's implementation. However, BIP39 has now achieved broad industry support across dozens of interoperable implementations and should be considered the de facto industry standard. Furthermore, BIP39 can be used to produce multi-currency wallets supporting Ethereum, whereas Electrum seeds cannot. BIP39 defines the creation of a mnemonic code and seed, which we describe here in 9 steps. For clarity, the process is split into 2 parts. Steps 1 through 6 are shown in generating mnemonic words and steps 7 through 9 are shown in from mnemonic to seed. Generating mnemonic words. Mnemonic words are generated automatically by the wallet using the standardized process defined in BIP 39. The wallet starts from a source of entropy, adds a checksum, and then maps the entropy to a word list. Create a cryptographically random sequence S of 128 to 256 bits. Create a checksum of S by taking the first length of S divided by 32 bits of the SHA-256 hash of S. Add the checksum to the end of the random sequence S. Divide the sequence and checksum concatenation into sections of 11 bits. Map each 11-bit value to a word from the predefined dictionary of 2048 words. Create the mnemonic code from the sequence of words, maintaining the order. Generating entropy Generating entropy and encoding as mnemonic words shows how entropy is used to generate mnemonic words. Mnemonic codes, entropy and word length shows the relationship between the size of the entropy data and the length of mnemonic codes in words. Entropy, bits, checksum, bits, entropy plus checksum, bits, mnemonic length, words. 128. 4. 132. 12. 160. 5. 165. 15. 192. 6. 198. 18. 224. 7. 231. 21. 256. 8. Generating entropy and encoding as mnemonic words. From mnemonic to seed. The mnemonic words represent entropy with a length of 128 to 256 bits. The entropy is then used to derive a longer, 512-bit, seed through the use of the key stretching function pbkdf2. The seed produced is used to build a deterministic wallet and derive its keys. The key stretching function takes two parameters, the mnemonic and assault. The purpose of assault in a key stretching function is to make it difficult to build a lookup table enabling a brute force attack. In the BIP39 standard, the salt has another purpose. It allows the introduction of a passphrase that serves as an additional security factor protecting the seed, as we will describe in more detail in optional passphrase in BIP39. The process described in steps 7 through 9 continues from the process described in the previous section. The first parameter to the pbkdf2 key stretching function is the mnemonic produced in step 6. The second parameter to the pbkdf2 key stretching function is assault. The salt is composed of the string constant mnemonic concatenated with an optional user-supplied passphrase. pbkdf2 stretches the mnemonic and salt parameters using 2048 rounds of hashing with the HMAC SHA-512 algorithm, producing a 512-bit value as its final output. That 512-bit value is the seed. From mnemonic to seed shows how a mnemonic is used to generate a seed. Figure 3. From mnemonic to seed. From mnemonic to seed. Note. The key stretching function, with its 2048 rounds of hashing, is a somewhat effective protection against brute force attacks against the mnemonic or the passphrase. It makes it costly, in computation, to try more than a few thousand passphrase and mnemonic combinations, while the number of possible derived seeds is vast, 2, or about 10, far bigger than the number of atoms in the visible universe, about 10. Tables hashtag mnemonic 128 nopass, hashtag mnemonic 128 opus, and hashtag mnemonic 256 nopass show some examples of mnemonic codes and the seeds they produce. Entropy input, 128 bits. 0 C1 E24 E5917779 D297 E14 D45 F14 E1A1A. Mnemonic, 12 words. Army van Defense carry jealous true garbage claim echo media make crunch. Passphrase. None. Seed, 512 bits. 5B56C41730 FA3 FSP7 E5740 E120A0 CA83 EC5A4 FC9 FP757 B63 FBD77A89A1A3 B4C67196 F57 C39A88 B763737333891 FB16 Ed27 A813 Seed 498804 C0570. Entropy input, 128 bits. 0 C1 E24 E5917779 D297 E14 D45 F14 E1A1A. The BIP39 standard allows the use of an optional passphrase in the derivation of the seed. If no passphrase is used, the mnemonic is stretched with a salt consisting of the constant string mnemonic, producing a specific 512-bit seed from any given mnemonic. If a passphrase is used, the stretching function produces a different seed from that same mnemonic. In fact, given a single mnemonic, every possible passphrase leads to a different seed. Essentially, there is no wrong passphrase. All passphrases are valid and they all lead to different seeds, forming a vast set of possible uninitialized wallets. The set of possible wallets is so large, too, that there is no practical possibility of brute forcing or accidentally guessing one that is in use, as long as the passphrase has sufficient complexity and length. There are no wrong passphrases in BIP39. Every passphrase leads to some wallet, which unless previously used will be empty. A second factor, something memorized, that makes a mnemonic useless on its own, protecting mnemonic backups from compromise by a thief. A form of plausible deniability or Duris wallet, where a chosen passphrase leads to a wallet with a small amount of funds, used to distract an attacker from the real wallet that contains the majority of funds. If the wallet owner is incapacitated or dead and no one else knows the passphrase, the seed is useless and all the funds stored in the wallet are lost forever. Conversely, if the owner backs up the passphrase in the same place as the seed, it defeats the purpose of a second factor. While passphrases are very useful, they should only be used in combination with a carefully planned process for backup and recovery, considering the possibility of heirs surviving the owner being able to recover the cryptocurrency. Working with mnemonic codes. Python mnemonic. The reference implementation of the standard by the Satoshi Labs team that proposed BIP39, in Python. Consensi/Ethlite wallet. Lightweight JS Ethereum wallet for nodes in browser, with BIP39. npm/BIP39. JavaScript implementation of Bitcoin BIP39, mnemonic code for generating deterministic keys. There is also a BIP39 generator implemented in a standalone web page. A BIP39 generator is a standalone web page, which is extremely useful for testing and experimentation. The mnemonic code converter generates mnemonics, seeds, and extended private keys. It can be used offline in a browser, or accessed online. Creating an HD wallet from the seed. HD wallets are created from a single root seed, which is a 128-256- or 512-bit random number. Most commonly, this seed is generated from a mnemonic as detailed in the previous section. Every key in the HD wallet is deterministically derived from this root seed, which makes it possible to recreate the entire HD wallet from that seed in any compatible HD wallet. This makes it easy to export, backup, restore, and import HD wallets containing thousands or even millions of keys by transferring just the mnemonic from which the root seed is derived. HD wallets, BIP32, and paths, BIP43/44. Most HD wallets follow the BIP32 standard, which has become a de facto industry standard for deterministic key generation. We won't be discussing all the details of BIP32 here, only the components necessary to understand how it is used in wallets. The main important aspect is the tree-like hierarchical relationships that it is possible for the derived keys to have, as you can see in HD wallet, a tree of keys generated from a single seed. It's also important to understand the ideas of extended keys and hardened keys, which are explained in the following sections. There are dozens of interoperable implementations of BIP32 offered in many software libraries. These are mostly designed for Bitcoin wallets, which implement addresses in a different way, but share the same key derivation implementation as Ethereum's BIP32 compatible wallets. Use one designed for Ethereum, or adapt one from Bitcoin by adding an Ethereum address encoding library. There is also a BIP32 generator implemented as a standalone web page that is very useful for testing and experimentation with BIP32. The standalone BIP32 generator is not an HTTPS site. That's to remind you that the use of this tool is not secure. It is only for testing. You should not use the keys produced by this site with real funds. Extended public and private keys. In BIP32 terminology, keys can be extended. With the right mathematical operations, these extended parent keys can be used to derive child keys, thus producing the hierarchy of keys and addresses described earlier. A parent key doesn't have to be at the top of the tree. It can be picked out from anywhere in the tree hierarchy. Extending a key involves taking the key itself and appending a special chain code to it. A chain code is a 256-bit binary string that is mixed with each key to produce child keys. A very useful characteristic of HD wallets is the ability to derive child public keys from parent public keys, without having the private keys. This gives us two ways to derive a child public key, either directly from the child private key, or from the parent public key. An extended public key can be used, therefore, to derive all of the public keys, and only the public keys, in that branch of the HD wallet structure. This shortcut can be used to create very secure public key only deployments, where a server or application has a copy of an extended public key, but no private keys whatsoever. That kind of deployment can produce an infinite number of public keys and Ethereum addresses, but cannot spend any of the money sent to those addresses. Meanwhile, on another, more secure server, the extended private key can derive all the corresponding private keys to sign transactions and spend the money. One common application of this method is to install an extended public key on a web server that serves an e-commerce application. The web server can use the public key derivation function to create a new Ethereum address for every transaction, example for a customer shopping cart, and will not have any private keys that would be vulnerable to theft. Without HD wallets, the only way to do this is to generate thousands of Ethereum addresses on a separate secure server and then preload them on the e-commerce server. That approach is cumbersome and requires constant maintenance to ensure that the server doesn't run out of keys, hence the preference to use extended public keys from HD wallets. Another common application of this solution is for cold storage or hardware wallets. In that scenario, the extended private key can be stored in a hardware wallet, while the extended public key can be kept online. The user can create receive addresses at will, while the private keys are safely stored offline. To spend the funds, the user can use the extended private key in an offline signing Ethereum client, or sign transactions on the hardware wallet device. Hardened child key derivation. The ability to derive a branch of public keys from an extended public key, or SPUB, is very useful, but it comes with a potential risk. Access to an SPUB does not give access to child private keys. However, because the SPUB contains the chain code, used to derive child public keys from the parent public key, if a child private key is known, or somehow leaked, it can be used with the chain code to derive all the other child private keys. A single leaked child private key, together with a parent chain code, reveals all the private keys of all the children. Worse, the child private key together with a parent chain code can be used to deduce the parent private key. To counter this risk, HD wallets use an alternative derivation function called hardened derivation, which breaks the relationship between parent public key and child chain code. The hardened derivation function uses the parent private key to derive the child chain code, instead of the parent public key. This creates a firewall in the parent/child sequence, with a chain code that cannot be used to compromise a parent or sibling private key. In simple terms, if you want to use the convenience of an SPUB to derive branches of public keys without exposing yourself to the risk of a leaked chain code, you should derive it from a hardened parent, rather than a normal parent. Best practice is to have the level 1 children of the master keys always derived by hardened derivation, to prevent compromise of the master keys. Index numbers for normal and hardened derivation. It is clearly desirable to be able to derive more than one child key from a given parent key. To manage this, an index number is used. Each index number, when combined with a parent key using the special child derivation function, gives a different child key. The index number used in the BIP32 parent-to-child derivation function is a 32-bit integer. To easily distinguish between keys derived through the normal, unhardened, derivation function versus keys derived through hardened derivation, this index number is split into two ranges. Index numbers between 0 and 2 to 1, 0x0 to 0x7ffffff, are used only for normal derivation. Index numbers between 2 and 2 to 1, 0x800000000 to 0xffffff, are used only for hardened derivation. Therefore, if the index number is less than 2, the child is normal, whereas if the index number is equal to or above 2, the child is hardened. To make the index numbers easier to read and display, the index numbers for hardened children are displayed starting from 0, but with a prime symbol. The first normal child key is therefore displayed as 0, whereas the first hardened child, index 0x8000000, is displayed as 0. In sequence, then, the second hardened key would have index of 0x800000001 and would be displayed as 1, and so on. When you see an HD wallet index I, that means 2 plus I. HD wallet key identifier, path. Keys in an HD wallet are identified using a path naming convention, with each level of the tree separated by a / character. See HD wallet path examples. Private keys derived from the master private key start with M. Public keys derived from the master public key start with M. Therefore, the first child private key of the master private key is M/0. The first child public key is M/0. The second grandchild of the first child is M/0/1, and so on. The ancestry of a key is read from right to left, until you reach the master key from which it was derived. For example, identifier M/X/Y/Z describes the key that is the ZTH child of key M/X/Y, which is the YTH child of key M/X, which is the XTH child of M. HD path key described. M/0. The first, 0, child private key of the master private key, M. M/0/0. The first grandchild private key of the first, navigating the HD wallet tree structure. The HD wallet tree structure is tremendously flexible. The HD wallet tree structure is tremendously flexible. The flip side of this is that it also allows for unbounded complexity. Each parent extended key can have 4 billion children, 2 billion normal children and 2 billion hardened children. Each of those children can have another 4 billion children, and so on. The tree can be as deep as you want, with a potentially infinite number of generations. With all that potential, it can become quite difficult to navigate these very large trees. 2BIP offer a way to manage this potential complexity by creating standards for the structure of HD wallet trees. BIP 43 proposes the use of the first hardened child index as a special identifier that signifies the purpose of the tree structure. Based on BIP 43, an HD wallet should use only one level 1 branch of the tree, with the index number defining the purpose of the wallet by identifying the structure and namespace of the rest of the tree. More specifically, an HD wallet using only branch M/I/ is intended to signify a specific purpose, and that purpose is identified by index number I. Extending that specification, BIP 44 proposes a multi-currency multi-account structure signified by setting the purpose number to 44. All HD wallets following the BIP 44 structure are identified by the fact that they only use one branch of the tree, M/44/*. BIP 44 specifies the structure as consisting of 5 predefined tree levels. M/purpose/cointype/account/change/address index. The first level, purpose, is always set to 44. The second level, coin type, specifies the type of cryptocurrency coin, allowing for multi-currency HD wallets where each currency has its own subtree under the second level. There are several currencies defined in a standards document called SLIP 0044. For example, Ethereum is M/44/60, Ethereum Classic is M/44/61, Bitcoin is M/44/0, and testnet for all currencies is M/44/1. The third level of the tree is account, which allows users to subdivide their wallets into separate logical sub-accounts for accounting or organizational purposes. For example, an HD wallet might contain 2 Ethereum accounts, M/44/60/0 and M/44/60/1. Each account is the root of its own subtree. Because BIP 44 was created originally for Bitcoin, it contains a quirk that isn't relevant in the Ethereum world. On the fourth level of the path, change, an HD wallet has 2 subtrees, one for creating receiving addresses and one for creating change addresses. Only the receive path is used in Ethereum, as there is no necessity for a change address like there is in Bitcoin. Note that whereas the previous levels used hardened derivation, this level uses normal derivation. This is to allow the account level of the tree to export extended public keys for use in a non-secured environment. Usable addresses are derived by the HD wallet as children of the fourth level, making the fifth level of the tree the address index. For example, the third receiving address for Ethereum payments in the primary account would be M/44/60/0/0/2. BIP 44 HD wallet structure examples shows a few more examples. HD path key described. M/44/60/0/0/2. The third receiving public key for the primary Ethereum account. M/44/0/3/1/14. The 15 change address public key for the 4 Bitcoin account. M/44/2/0/0/1. The second private key in the Litecoin main account, for signing transactions. Conclusions. Wallets are the foundation of any user-facing blockchain application. They allow users to manage collections of keys and addresses. Wallets also allow users to demonstrate their ownership of Ether and authorize transactions by applying digital signatures, as we will see in this chapter. Transactions. Transactions are signed messages originated by an externally owned account, EOA, transmitted by the Ethereum network, and recorded on the Ethereum blockchain. This basic definition conceals a lot of surprising and fascinating details. Another way to look at transactions is that they are the only things that can trigger a change of state, or cause a contract to execute in the EVM. Ethereum is a global singleton state machine, and transactions are what make that state machine tick, changing its state. Contracts don't run on their own. Ethereum doesn't run autonomously. Everything starts with a transaction. In this chapter, we will dissect transactions, show how they work, and examine the details. Note that much of this chapter is addressed to those who are interested in managing their own transactions at a low level, perhaps because they are writing a wallet app. You don't have to worry about this if you are happy using existing wallet applications, although you may find the details interesting. The structure of a transaction. First, let's take a look at the basic structure of a transaction, as it is serialized and transmitted on the Ethereum network. Each client and application that receives a serialized transaction will store it in memory using its own internal data structure, perhaps embellished with metadata that doesn't exist in the network serialized transaction itself. The network serialization is the only standard form of a transaction. Nonce. A sequence number, issued by the originating EOA, used to prevent message replay. Gas price. The amount of Ether, in way, that the originator is willing to pay for each unit of gas. Gas limit. The maximum amount of gas the originator is willing to buy for this transaction. Recipient. The destination Ethereum address. Value. The amount of Ether, in way, to send to the destination. Data. The variable length binary data payload. VRS. The 3 components of an hexadigital signature of the originating EOA. The transaction message's structure is serialized using the recursive length prefix, RLP, encoding scheme, which was created specifically for simple, byte-perfect data serialization in Ethereum. All numbers in Ethereum are encoded as big-endian integers, of lengths that are multiples of 8 bits. Note that the field labels, to, gas limit, etc., are shown here for clarity, but are not part of the transaction serialized data, which contains the field values RLP encoded. In general, RLP does not contain any field delimiters or labels. RLP's length prefix is used to identify the length of each field. Anything beyond the defined length belongs to the next field in the structure. While this is the actual transaction structure transmitted, most internal representations and user interface visualizations embellish this with additional information, derived from the transaction or from the blockchain. For example, you may notice there is no from data in the address identifying the originator EOA. That is because the EOA's public key can be derived from the VRS components of the EXA signature. The address can, in turn, be derived from the public key. When you see a transaction showing a from field, that was added by the software used to visualize the transaction. Other metadata frequently added to the transaction by client software includes the block number, once it is mined and included in the blockchain, and a transaction ID, calculated hash. Again, this data is derived from the transaction, and does not form part of the transaction message itself. The transaction nonce. The nonce is one of the most important and least understood components of a transaction. The definition in the yellow paper, see references, reads: nonce, a scalar value equal to the number of transactions sent from this address or, in the case of accounts with associated code, the number of contract creations made by this account. Strictly speaking, the nonce is an attribute of the originating address, that is, it only has meaning in the context of the sending address. However, the nonce is not stored explicitly as part of an account's state on the blockchain. Instead, it is calculated dynamically, by counting the number of confirmed transactions that have originated from an address. There are two scenarios where the existence of a transaction counting nonce is important, the usability feature of transactions being included in the order of creation, and the vital feature of transaction duplication protection. Let's look at an example scenario for each of these. Imagine you wish to make two transactions. You have an important payment to make of 6 Ether, and also another payment of 8 Ether. You sign and broadcast the 6 Ether transaction first, because it is the more important one, and then you sign and broadcast the second, 8 Ether transaction. Sadly, you have overlooked the fact that your account contains only 10 Ether, so the network can't accept both transactions, one of them will fail. Because you sent the more important 6 Ether one first, you understandably expect that one to go through and the 8 Ether one to be rejected. However, in a decentralized system like Ethereum, nodes may receive the transactions in either order. There is no guarantee that a particular node will have one transaction propagated to it before the other. As such, it will almost certainly be the case that some nodes receive the 6 Ether transaction first and others receive the 8 Ether transaction first. Without the nonce, it would be random as to which one gets accepted and which rejected. However, with the nonce included, the first transaction you sent will have a nonce of, let's say, 3, while the 8 Ether transaction has the next nonce value, i.e., 4. So, that transaction will be ignored until the transactions with nonces from 0 to 3 have been processed, even if it is received first. Phew. Now imagine you have an account with 100 Ether. Fantastic. You find someone online who will accept payment in Ether for a MacGuffin widget that you really want to buy. You send them 2 Ether and they send you the MacGuffin widget. Lovely. To make the 2 Ether payment, you signed a transaction sending 2 Ether from your account to their account, and then broadcast it to the Ethereum network to be verified and included on the blockchain. Now, without a nonce value in the transaction, a second transaction sending 2 Ether to the same address a second time will look exactly the same as the first transaction. This means that anyone who sees your transaction on the Ethereum network, which means everyone, including the recipient or your enemies, can replay the transaction again and again and again until all your Ether is gone simply by copying and pasting your original transaction and resending it to the network. However, with the nonce value included in the transaction data, every single transaction is unique, even when sending the same amount of Ether to the same recipient address multiple times. Thus, by having the incrementing nonce as part of the transaction, it is simply not possible for anyone to duplicate a payment you have made. In summary, it is important to note that the use of the nonce is actually vital for an account-based protocol, in contrast to the unspent transaction output (UTXO) mechanism of the Bitcoin protocol. Keeping track of nonces. In practical terms, the nonce is an up-to-date count of the number of confirmed, i.e., on-chain, transactions that have originated from an account. To find out what the nonce is, you can interrogate the blockchain, for example via the Web3 interface. Open a JavaScript console in Geth, or your preferred Web3 interface, on Ropsten testnet, then type. The nonce is a zero-based counter, meaning the first transaction has nonce 0. In this example, we have a transaction count of 40, meaning nonces 0 through 39 have been seen. The next transaction's nonce will need to be 40. Your wallet will keep track of nonces for each address it manages. It's fairly simple to do that, as long as you are only originating transactions from a single point. Let's say you are writing your own wallet software or some other application that originates transactions. How do you track nonces? When you create a new transaction, you assign the next nonce in the sequence. But until it is confirmed, it will not count toward the getTransaction_count total. Be careful when using the getTransaction_count function for counting pending transactions, because you might run into some problems if you send a few transactions in a row. Web3.eth.getTransactionCount 0x9E713963892C0231. If you're trying to recreate these code examples yourself in Geth's JavaScript console, you should use Web3.toWay instead of Web3.utils.toWay. This is because Geth uses an older version of the Web3 library. As you can see, the first transaction we sent increased the transaction count to 41, showing the pending transaction. But when we sent 3 more transactions in quick succession, the getTransaction_count call didn't count them. It only counted 1, even though you might expect there to be 3 pending in the mempool. If we wait a few seconds to allow for network communications to settle down, the getTransaction_count call will return the expected number. But in the interim, while there is more than 1 transaction pending, it might not help us. When you build an application that constructs transactions, it cannot rely on getTransaction_count for pending transactions. Only when the pending and confirmed counts are equal, all outstanding transactions are confirmed, can you trust the output of getTransaction_count to start your nonce counter. Thereafter, keep track of the nonce in your application until each transaction confirms. Parity's JSON RPC interface offers the parity next nonce function, which returns the next nonce that should be used in a transaction. The parity next nonce function counts nonces correctly, even if you construct several transactions in rapid succession without confirming them. $curl data, method parity next nonce, /param 0x9E713963892C023178A681B9BB3065A82492124F, /ID1, JSON erp : 2.0, H, content type, application /JSON, X post /localhost 8545 JSON erp : 2.0, result : 0x32, ID1. Parity has a web console for accessing the JSON RPC interface, but here we are using a command line HTTP client to access it. Gaps in nonces, duplicate nonces, and confirmation. It is important to keep track of nonces if you are creating transactions programmatically, especially if you are doing so from multiple independent processes simultaneously. The Ethereum network processes transactions sequentially, based on the nonce. That means that if you transmit a transaction with nonce 0 and then transmit a transaction with nonce 2, the second transaction will not be included in any blocks. It will be stored in the mempool, while the Ethereum network waits for the missing nonce to appear. All nodes will assume that the missing nonce has simply been delayed and that the transaction with nonce 2 was received out of sequence. If you then transmit a transaction with the missing nonce 1, both transactions, nonces 1 and 2, will be processed and included, if valid, of course. Once you fill the gap, the network can mine the out-of-sequence transaction that it held in the mempool. What this means is that if you create several transactions in sequence and one of them does not get officially included in any blocks, all the subsequent transactions will be stuck, waiting for the missing nonce. A transaction can create an inadvertent gap in the nonce sequence because it is invalid or has insufficient gas. To get things moving again, you have to transmit a valid transaction with the missing nonce. You should be equally mindful that once a transaction with the missing nonce is validated by the network, all the broadcast transactions with subsequent nonces will incrementally become valid. It is not possible to recall a transaction. If, on the other hand, you accidentally duplicate a nonce, for example by transmitting two transactions with the same nonce but different recipients or values, then one of them will be confirmed and one will be rejected. Which one is confirmed will be determined by the sequence in which they arrive at the first validating node that receives them i.e. It will be fairly random. As you can see, keeping track of nonces is necessary, and if your application doesn't manage that process correctly you will run into problems. Unfortunately, things get even more difficult if you are trying to do this concurrently, as we will see in the next section. Concurrency, transaction origin. Concurrency, transaction origination, and nonces. Concurrency is a complex aspect of computer science, and it crops up unexpectedly sometimes, especially in decentralized and distributed real-time systems like Ethereum. In simple terms, concurrency is when you have
I think I'm gonna continue to read this book for probably the remainder of the stream. Like, it looks like each one of them
in
is
simple
very
terms.
long. Like this one is 50 minutes, and I'm still on chapter 6. And the issue with here is that I wanna write articles as fast as possible, but the problem is, like I said before, is that everything is integrated, so I have to understand more how the other parts work before I start writing this stuff. But maybe I'll do like I did today, I'll go like this where I'm writing some of the parts and then as I write I realize which ones I don't really understand the details very good. And then I will go back to studying and then I'll go back to writing. I think that's what I'm gonna do. But I wanna finish this book first, and after I finish the book, if I still don't understand the process of, which looks like I'm not gonna understand because it doesn't seem like they talk about it. Maybe they will talk about in oracles or decentralized applications, but I think probably not. And maybe you can derive how it works from the parts that they talked about, but I still don't get it about the whole thing about. Obviously, on the concept level, I get it, but on the details, I don't get it. Where of how is it possible that some mempools are private and some are public, and the connection between them. And I think I'm gonna have to read the wallets again because I was reading, I was eating, so I was kind of distracted. And probably the cryptography ones. I think the first ones were very good, so I'm probably gonna have to read them again. But I think I'll reread them off stream, and I'm just gonna read the remainder ones now. And then what I'm probably gonna have to do is to continue to study the source code here to understand how it works, which is gonna be very hard, I think, to understand everything. That's why I'm hoping that at least I gain some clarification about this mempool stuff with the book, because with the book it's gonna be easier to understand. But reading the source code is gonna take more time, I think, to understand how it works. And then once I understand that, then I'll go back to writing the article, I think. Or if I see that it's gonna take a long time, then I might just keep writing this and just leave the article like this, and then I'll improve the article later, which is also possible. I think like leaving it like this and just putting a conclusion here is not too bad, I think. I might do that, and then I'll go back eventually as I write the other articles as well, because the other ones I'm gonna have to do research as well and study. So, and because everything is connected, then it's probably gonna help me understand this one. Then I can go back and improve this one as well.
In simple terms, concurrency is when you have simultaneous computation by multiple independent systems. These can be in the same program, example multithreading, on the same CPU, example multiprocessing, or on different computers, i.e., distributed systems. Ethereum, by definition, is a system that allows concurrency of operations, nodes, clients, dApps, but enforces a singleton state through consensus. Now, imagine that you have multiple independent wallet applications that are generating transactions from the same address or addresses. One example of such a situation would be an exchange processing withdrawals from the exchange's hot wallet, a wallet whose keys are stored online, in contrast to a cold wallet where the keys are never online. Ideally, you'd want to have more than one computer processing withdrawals, so that it doesn't become a bottleneck or single point of failure. However, this quickly becomes problematic, as having more than one computer producing withdrawals will result in some thorny concurrency problems, not least of which is the selection of nonces. How do multiple computers generating, signing, and broadcasting transactions from the same hot wallet account coordinate? You could use a single computer to assign nonces, on a first-come first-served basis, to computers signing transactions. However, this computer is now a single point of failure. Worse, if several nonces are assigned and one of them never gets used, because of a failure in the computer processing the transaction with that nonce, all subsequent transactions get stuck. Another approach would be to generate the transactions, but not assign a nonce to them, and therefore leave them unsigned. Remember that the nonce is an integral part of the transaction data and therefore needs to be included in the digital signature that authenticates the transaction. You could then queue them to a single node that signs them and also keeps track of nonces. Again, though, this would be a choke point in the process. The signing and tracking of nonces is the part of your operation that is likely to become congested under load, whereas the generation of the unsigned transaction is the part you don't really need to parallelize. You would have some concurrency, but it would be lacking in a critical part of the process. In the end, these concurrency problems, on top of the difficulty of tracking account balances and transaction confirmations in independent processes, force most implementations toward avoiding concurrency and creating bottlenecks such as a single process handling all withdrawal transactions in an exchange, or setting up multiple hot wallets that can work completely independently for withdrawals and only need to be intermittently rebalanced. Transaction gas. We talked about gas a little in earlier chapters, and we discuss it in more detail in gas. However, let's cover some basics about the role of the gas price and gas limit components of a transaction. Gas is the fuel of Ethereum. Gas is not Ether, it's a separate virtual currency with its own exchange rate against Ether. Ethereum uses gas to control the amount of resources that a transaction can use, since it will be processed on thousands of computers around the world. The open-ended, Turing-complete, computation model requires some form of metering in order to avoid denial of service attacks or inadvertently resource-devouring transactions. Gas is separate from Ether in order to protect the system from the volatility that might arise along with rapid changes in the value of Ether, and also as a way to manage the important and sensitive ratios between the costs of the various resources that gas pays for, namely, computation, memory, and storage. The gas price field in a transaction allows the transaction originator to set the price they are willing to pay in exchange for gas. The price is measured in weight per gas unit. For example, in the sample transaction in intro chapter, your wallet set the gas price to 3 GWh, 3 GAUDI or 3 billion WEI. The popular site Gas Station provides information on the current prices of gas and other relevant gas metrics for the Ethereum main network. Wallets can adjust the gas price in transactions they originate to achieve faster confirmation of transactions. The higher the gas price, the faster the transaction is likely to be confirmed. Conversely, lower priority transactions can carry a reduced price, resulting in slower confirmation. The minimum value that gas price can be set to is 0, which means a fee-free transaction. During periods of low demand for space in a block, such transactions might very well get mined. The minimum acceptable gas price is 0. That means that wallets can generate completely free transactions. Depending on capacity, these may never be confirmed, but there is nothing in the protocol that prohibits free transactions. You can find several examples of such transactions successfully included on the Ethereum blockchain. The Web3 interface offers a gas price suggestion. By calculating a median price across several blocks, we can use the Truffle console or any JavaScript Web3 console to do that. The second important field related to gas is gas limit. In simple terms, gas limit gives the maximum number of units of gas the transaction originator is willing to buy in order to complete the transaction. For simple payments, meaning transactions that transfer Ether from one EOA to another EOA, the gas amount needed is fixed at 21,000 gas units. To calculate how much Ether that will cost, you multiply 21,000 by the gas price you are willing to pay. For example, if your transaction's destination address is a contract, then the amount of gas needed can be estimated but cannot be determined with accuracy. That's because a contract can evaluate different conditions that lead to different execution paths, with different total gas costs. The contract may execute only a simple computation or a more complex one, depending on conditions that are outside of your control and cannot be predicted. To demonstrate this, let's look at an example. We can write a smart contract that increments a counter each time it is called and executes a particular loop a number of times equal to the call count. Maybe on the 100th call it gives out a special prize, like a lottery, but needs to do additional computation to calculate the prize. If you call the contract 99 times, one thing happens, but on the 100th call something very different happens. The amount of gas you would pay for that depends on how many other transactions have called that function before your transaction is included in a block. Perhaps your estimate is based on being the 99th transaction, but just before your transaction is confirmed someone else calls the contract for the 99th time. Now you're the 100th transaction to call, and the computation effort, and gas cost, is much higher. To borrow a common analogy used in Ethereum, you can think of gas limit as the capacity of the fuel tank in your car. Your car is the transaction. You fill the tank with as much gas as you think it will need for the journey, the computation needed to validate your transaction. You can estimate the amount to some degree, but there might be unexpected changes to your journey, such as a diversion, a more complex execution path, that increase fuel consumption. The analogy to a fuel tank is somewhat misleading, however. It's actually more like a credit account for a gas station company, where you pay after the trip is completed, based on how much gas you actually used. When you transmit your transaction, one of the first validation steps is to check that the account it originated from has enough Ether to pay the gas price * gas limit. But the amount is not actually deducted from your account until the transaction finishes executing. You are only billed for gas actually consumed by your transaction, but you have to have enough balance for the maximum amount you are willing to pay before you send your transaction. Transaction recipient. The recipient of a transaction is specified in the to field. This contains a 20-byte Ethereum address.
And I think that this property here is what allows for atomic transactions, because then if you don't have enough, for example, when you're doing an arbitrage, if you don't have enough balance after the transaction, it reverts everything. I think that's one of the things. But maybe not actually, because that doesn't have to do with the gas, I think. But yeah, I think it is related because it's the gas price and the gas limits. So, and the gas can change during the transaction, like it says here.
This contains a 20-byte Ethereum address. The address can be an EOA or a contract address. Ethereum does no further validation of this field. Any 20-byte value is considered valid. If the 20-byte value corresponds to an address without a corresponding private key, or without a corresponding contract, the transaction is still valid. Ethereum has no way of knowing whether an address was correctly derived from a public key, and therefore from a private key, in existence. The Ethereum protocol does not validate recipient addresses in transactions. You can send to an address that has no corresponding private key or contract, thereby burning the Ether, rendering it forever unspendable. Validation should be done at the user interface level. Sending a transaction to the wrong address will probably burn the Ether sent, rendering it forever inaccessible, unspendable, since most addresses do not have a known private key and therefore no signature can be generated to spend it. It is assumed that validation of the address happens at the user interface level, see EIP 55. In fact,
I think an interesting thing about this is, like, but obviously it would be very unlikely to happen, but like it is possible that someone sends a transaction for an address that doesn't exist, that doesn't have a private key, but then someone else later creates the private key and then gets lucky, and it is that the address that has the thing. So effectively, I think it would still be possible for someone to get the money, but very unlikely.
in fact, there are a number of valid reasons for burning Ether, for example, as a disincentive to cheating in payment channels and other smart contracts, and since the amount of Ether is finite. Burning Ether effectively distributes the value burned to all Ether holders, in proportion to the amount of Ether they hold. Transaction value and data. The main payload of a transaction is contained in two fields, value and data. Transactions can have both value and data, only value, only data, or neither value nor data. All four combinations are valid. A transaction with only value is a payment. A transaction with only data is an invocation. A transaction with both value and data is both a payment and an invocation. A transaction with neither value nor data, well, that's probably just a waste of gas. But it is still possible. Let's try all of these combinations. First, we'll set the source and destination addresses from our wallet, just to make the demo easier to read. Our wallet shows a confirmation screen indicating the value to send, as shown in Parity Wallet showing a transaction with value, but no data. Our wallet shows a confirmation screen indicating the value to send as well as the data payload, as shown in Parity Wallet showing a transaction with value and data. Our wallet shows a confirmation screen indicating the zero value and the data payload, as shown in Parity Wallet showing a transaction with no value, only data. Our wallet shows a confirmation screen indicating zero value, as shown in Parity Wallet showing a transaction with no value, and no data. Transmitting value to EOAs and contracts. When you construct an Ethereum transaction that contains a value, it is the equivalent of a payment. Such transactions behave differently depending on whether the destination address is a contract or not. For EOA addresses, or rather for any address that isn't flagged as a contract on the blockchain, Ethereum will record a state change, adding the value you sent to the balance of the address. If the address has not been seen before, it will be added to the client's internal representation of the state and its balance initialized to the value of your payment. If the destination address, too, is a contract, then the EVM will execute the contract and will attempt to call the function named in the data payload of your transaction. If there is no data in your transaction, the EVM will call a fallback function and, if that function is payable, will execute it to determine what to do next. If there is no code in fallback function, then the effect of the transaction will be to increase the balance of the contract, exactly like a payment to a wallet. If there is no fallback function or non-payable fallback function, then transaction will be reverted. A contract can reject incoming payments by throwing an exception immediately when a function is called, or as determined by conditions coded in a function. If the function terminates successfully, without an exception, then the contract state is updated to reflect an increase in the contract's ether balance. Transmitting a data payload to an EOA or contract. When your transaction contains data, it is most likely addressed to a contract address. That doesn't mean you cannot send a data payload to an EOA that is completely valid in the Ethereum protocol. However, in that case, the interpretation of the data is up to the wallet you use to access the EOA. It is ignored by the Ethereum protocol. Most wallets also ignore any data received in a transaction to an EOA they control. In the future, it is possible that standards may emerge that allow wallets to interpret data the way contracts do, thereby allowing transactions to invoke functions running inside user wallets. The critical difference is that any interpretation of the data payload by an EOA is not subject to Ethereum's consensus rules, unlike a contract execution. For now, let's assume your transaction is delivering data to a contract address. In that case, the data will be interpreted by the EVM as a contract invocation. Most contracts use this data more specifically as a function invocation, calling the named function and passing any encoded arguments to the function. The data payload sent to an ABI-compatible contract, which you can assume all contracts are, is a hex-serialized encoding of a function selector. The first 4 bytes of the CUCK256 hash of the function's prototype. This allows the contract to unambiguously identify which function you wish to invoke. The function arguments. The function's arguments, encoded according to the rules for the various elementary types defined in the ABI specification. The prototype of a function is defined as the string containing the name of the function, followed by the data types of each of its arguments, enclosed in parentheses and separated by commas. The function name here is withdraw and it takes a single argument that is a uint, which is an alias for uint256, so the prototype of withdraw would be web3.utils.sha3, withdraw, uint256, 0x2e1a7d413322e7b96f9a57413e15250c2508b7a9021c5c250f b69f16a49f. The first 4 bytes of the hash are 0x2e1a7d4d. That's our function selector value, which will tell the contract which function we want to call. Next, let's calculate a value to pass as the argument withdraw amount. We want to withdraw 0.01 ether. Let's encode that to a hex-serialized big-endian unsigned 256-bit integer, denominated in way. Withdraw amount equals web3.utils.to-way, 0.01, ether, 10,000,000,000,000,000,000,000,000. Withdraw amount hex equals web3.utils.to-hex, withdraw amount, 0x2386f26fc10,000. That's the data payload for our transaction, invoking the withdraw function and requesting 0.01 ether as the withdraw amount. Special transaction, contract creation. One special case that we should mention is a transaction that creates a new contract on the blockchain, deploying it for future use. Contract creation transactions are sent to a special destination address called the zero address. The to field in a contract registration transaction contains the address 0x0. This address represents neither an EOA, there is no corresponding private, public key pair, nor a contract. It can never spend ether or initiate a transaction. It is only used as a destination, with the special meaning, create this contract. While the zero address is intended only for contract creation, it sometimes receives payments from various addresses. There are 2 explanations for this: either it is by accident, resulting in the loss of ether, or it is an intentional ether burn, deliberately destroying ether by sending it to an address from which it can never be spent. However, if you want to do an intentional ether burn, you should make your intention clear to the network and use the specially designated burn address instead. A contract creation transaction need only contain a data payload that contains the compiled bytecode which will create the contract. The only effect of this transaction is to create the contract. You can include an ether amount in the value field if you want to set the new contract up with a starting balance, but that is entirely optional. If you send a value, ether, to the contract creation address without a data payload, no contract, then the effect is the same as sending to a burn address there is no contract to credit, so the ether is lost. As an example, we can create the faucet.sol contract used in intro chapter by manually creating a transaction to the 0 address with the contract in the data payload. The contract needs to be compiled into a bytecode representation. This can be done with the Solidity compiler. $sol bin faucet.sol binary 60606052341561000. It is good practice to always specify a parameter, even in the case of zero address contract creation, because the cost of accidentally sending your ether to 0x0 and losing it forever is too great. You should also specify a gas price and gas limit. Once the contract is mined, we can see it on the Etherscan block explorer, as shown in Etherscan showing the contract successfully mined. web3.eth.get transaction receipt \0. web3.eth.get transaction receipt \0x7bcc327ae5. This includes the address of the contract, which we can use to send funds to and receive funds from the contract as shown in the previous section. Contract address equals 0xb22. After a while, both transactions are visible on Etherscan, as shown in Etherscan showing the transactions for sending and receiving funds. Digital signatures. So far, we have not delved into any detail about digital signatures. In this section, we look at how digital signatures work and how they can be used to present proof of ownership of a private key without revealing that private key. The elliptic curve digital signature algorithm. The digital signature algorithm used in Ethereum is the elliptic curve digital signature algorithm, EXA. It's based on elliptic curve private, public key pairs, as described in elliptic curve. A digital signature serves three purposes in Ethereum. See the following sidebar. First, the signature proves that the owner of the private key, who is by implication the owner of an Ethereum account, has authorized the spending of Ether, or execution of a contract. Secondly, it guarantees non-repudiation. The proof of authorization is undeniable. Thirdly, the signature proves that the transaction data has not been and cannot be modified by anyone after the transaction has been signed. A digital signature is a mathematical scheme for presenting the authenticity of digital messages or documents. A valid digital signature gives a recipient reason to believe that the message was created by a known sender, authentication, that the sender cannot deny having sent the message, non-repudiation, and that the message was not altered in transit, integrity. How digital signatures work. A digital signature is a mathematical scheme that consists of two parts. The first part is an algorithm for creating a signature, using a private key, the signing key, from a message, which in our case is the transaction. The second part is an algorithm that allows anyone to verify the signature by only using the message in a public key. Creating a digital signature. In Ethereum's implementation of EXA, the message being signed is the transaction, or more accurately, the CUCK256 hash of the RLP encoded data from the transaction. The signing key is the EOA's private key. The result is the signature. The function fsig produces a signature sig that is composed of two values, The function fsig produces a signature sig that is composed of two values, commonly referred to as RNS. Verifying the signature. To verify the signature, one must have the signature, RNS, the serialized transaction, and the public key that corresponds to the private key used to create the signature. Essentially, verification of a signature means only the owner of the private key that generated this public key could have produced this signature on this transaction. The signature verification algorithm takes the message, i.e., a hash of the transaction for our usage, the signer's public key, and the signature, RNS values, and returns true if the signature is valid for this message in public key. Examath. As mentioned previously, signatures are created by a mathematical function fsig that produces a signature composed of two values, R and S. In this section we look at the function fsig in more detail. The signature algorithm first generates an ephemeral, temporary, private key in a cryptographically secure way. This temporary key is used in the calculation of the R and S values to ensure that the sender's actual private key can't be calculated by attackers watching signed transactions on the Ethereum network. As we know from PubKey, the ephemeral private key is used to derive the corresponding, ephemeral, public key, so we have. Verification is the inverse of the signature generation function, using the Verification is the inverse of the signature generation function, using the RNS values and the sender's public key to calculate a value Q, which is a point on the elliptic curve, the ephemeral public key used in signature creation. The steps are as follows. If the X coordinate If the x-coordinate of the calculated point Q is equal to r, then the verifier can conclude that the signature is valid. EXA is necessarily a fairly complicated piece of math. A full explanation is beyond the scope of this book. A number of great guides online take you through it step by step. Search for EXA Explained, or try this one, http://bit.ly/2r0hhgb. Transaction.
I think I'll leave this to study tomorrow because I'm already tired, so I think it's not gonna be that effective to study now. It's better to study this stuff when I'm fresh, when I just woke up.
EXA Explained. Or try this one, http://bit.ly/2r0hhgb. Transaction signing in practice. To produce a valid transaction, the originator must digitally sign the message, using the elliptic curve digital signature algorithm. When we say sign the transaction, we actually mean sign the CUCAKE256 hash of the RLP serialized transaction data. The signature is applied to the hash of the transaction data, not the transaction itself. The special signature variable V indicates two things. The special signature variable V indicates two things, the chain ID and the recovery identifier to help the ECDSR recover function check the signature. It is calculated as either one of 27 or 28, or as the chain ID doubled plus 35 or 36. For more information on the chain ID, see raw transaction creation with EIP 155. The recovery identifier, 27 or 28 in the old style signatures, or 35 or 36 in the full spurious dragon style transactions, is used to indicate the parity of the Y component of the public key. See the signature prefix value, V, and public key recovery for more details. At block number 2,675,000 Ethereum implemented the spurious dragon hard fork, which, among other changes, introduced a new signing scheme that includes transaction replay protection, preventing transactions meant for one network being replayed on others. This new signing scheme is specified in EIP 155. This change affects the form of the transaction and its signature, so attention must be paid to the first of the three signature variables, i.e., V, which takes one of two forms and indicates the data fields included in the transaction message being hashed. Raw transaction creation and signing. In this section we'll create a raw transaction and sign it, using the Ethereum JSTX library, which can be installed with npm. This demonstrates the functions that would normally be used inside a wallet, or an application that signs transactions on behalf of a user. The source code for this example is in the file rotsdemo.js in the book's GitHub repository. $node rotsdemo.js RLP encoded TX 0xe680860000008300000094B092C523D58204F2BCB1BD7FB1C7C1. TX hash 0XF03529F4525F6 9F8366D2BBC77065880 add 0A068FF6525BA33721AT6992 signed raw transaction 0xF8668086098400000000994B092C523D58204F2BCB1. Raw transaction creation with EIP 155. The signature prefix value, V, and public key recovery. As mentioned in the structure of a transaction, the transaction message doesn't include a from field. That's because the originator's public key can be computed directly from the EXA signature. Once you have the public key, you can compute the address easily. The process of recovering the signer's public key is called public key recovery. First, we compute two elliptic curve points, R and R, from the X coordinate R value that is in the signature. There are 2 points because the elliptic curve is symmetric across the x-axis, so that for any value x there are 2 possible values that fit the curve, one on each side of the x-axis. Finally, we calculate z, which is the n lowest bits of the message hash, where n is the order of the elliptic curve. To make things more efficient, the transaction signature includes a prefix. To make things more efficient, the transaction signature includes a prefix value v, which tells us which of the 2 possible r values is the ephemeral public key. If v is even, then r is the correct value. If v is odd, then it is r. That way, we need to calculate only one value for r and only one value for k. Separating signing and transmission, offline signing. Once a transaction is signed, it is ready to transmit to the Ethereum network. The 3 steps of creating, signing, and broadcasting a transaction normally happen as a single operation, for example using web3.eth.send transaction. However, as you saw in raw transaction creation and signing, you can create and sign the transaction in 2 separate steps. Once you have a signed transaction, you can then transmit it using web3.eth.send signed transaction, which takes a hex-encoded and signed transaction and transmits it on the Ethereum network. Why would you want to separate the signing and transmission of transactions? The most common reason is security. The computer that signs a transaction must have unlocked private keys loaded in memory. The computer that does the transmitting must be connected to the internet and be running an Ethereum client. If these 2 functions are on one computer, then you have private keys on an online system, which is quite dangerous. Separating the functions of signing and transmitting and performing them on different machines, on an offline and an online device, respectively, is called offline signing and is a common security practice. Depending on the level of security you need, your offline Depending on the level of security you need, your offline signing computer can have varying degrees of separation from the online computer, ranging from an isolated and firewalled subnet, online but segregated, to a completely offline system known as an air-gapped system. In an air-gapped system there is no network connectivity at all. The computer is separated from the online environment by a gap of air. To sign transactions you transfer them to and from the air-gapped computer using data storage media or, better, a webcam and QR code. Of course, this means you must manually transfer every transaction you want signed, and this doesn't scale. While not many environments can utilize a fully air-gapped system, even a small degree of isolation has significant security benefits. For example, an isolated subnet with a firewall that only allows a message queue protocol through can offer a much reduced attack surface and much higher security than signing on the online system. Many companies use a protocol such as 0MQ for this purpose. With a setup like that, transactions are serialized and queued for signing. The queuing protocol transmits the serialized message, in a way similar to a TCP socket, to the signing computer. The signing computer reads the serialized transactions from the queue, carefully, applies a signature with the appropriate key, and places them on an outgoing queue. The outgoing queue transmits the signed transactions to a computer with an Ethereum client that dequeues them and transmits them. Transaction propagation. The Ethereum network uses a flood routing protocol. Each Ethereum client acts as a node in a peer-to-peer, P2P, network, which, ideally, forms a mesh network. No network node is special, they all act as equal peers. We will use the term node to refer to an Ethereum client that is connected to and participates in the P2P network. Transaction propagation starts with the originating Ethereum node creating, or receiving from offline, a signed transaction. The transaction is validated and then transmitted to all the other Ethereum nodes that are directly connected to the originating node. On average, each Ethereum node maintains connections to at least 13 other nodes, called its neighbors.
That's the thing that I wanted to know. So, I guess it's random, and then it's maximum to 13, I think. But it says on average here. At least 13. So it's gonna talk about it here. And here, yeah, I can see here, I think the number of peers are the neighbors, I guess. In my case, I have 81 now. I think this is working, but I'm not really 100% sure. I think I'll just know once it finishes syncing. Because the thing is that the number of days goes up and down, and I think it's because of the bandwidth of the internet that is, and the number of neighbors probably. But I can tell that it is working because of the amount of space that it is taking. So I can see that there is a difference between the way that it was yesterday and the way that it was today. But I'm curious to see what is gonna happen once it gets to the once it syncs completely. And the other thing that also uh, because I talked about this before, and I said that this time I'm turning it off every time I go to sleep, and then I turn back on. And this wouldn't be possible if I was going to validate the nodes, because if you want to validate, then you have to keep it running 24/7 because you need the node to be synced. So it's not ideal to be turning it off and on again. So that's the other thing that I'm not really sure how it's gonna be. Because I know that if you turn it off, then it takes some time to sync the next time.
Each neighbor node validates the transaction as soon as they receive it. If they agree that it is valid, they store a copy and propagate it to all their neighbors, except the one it came from. As a result, the transaction ripples outwards from the originating node, flooding across the network, until all nodes in the network have a copy of the transaction. Nodes can filter the messages they propagate, but the default is to propagate all valid transaction messages they receive. Within just a few seconds, an Ethereum transaction propagates to all the Ethereum nodes around the globe. From the perspective of each node, it is not possible to discern the origin of the transaction. The neighbor that sent it to the node may be the originator of the transaction or may have received it from one of its neighbors. To be able to track the origins of transactions, or interfere with propagation, an attacker would have to control a significant percentage of all nodes. This is part of the security and privacy design of P2P networks, especially as applied to blockchain networks. Recording on the blockchain. While all the nodes in Ethereum are equal peers, some of them are operated by miners and are feeding transactions and blocks to mining farms, which are computers with high-performance graphics processing units, GPUs. The mining computers add transactions to a candidate block in attempt to find a proof of work that makes the candidate block valid. We will discuss this in more detail in consensus. Without going into too much detail, valid transactions will eventually be included in a block of transactions and, thus, recorded in the Ethereum blockchain. Once mined into a block, transactions also modify the state of the Ethereum singleton, either by modifying the balance of an account, in the case of a simple payment, or by invoking contracts that change their internal state. These changes are recorded alongside the transaction, in the form of a transaction receipt, which may also include events. We will examine all this in much more detail in EV chapter. A transaction that has completed its journey from creation through signing by an EOA, propagation, and finally mining has changed the state of the singleton and left an indelible mark on the blockchain. Multiple signature, multisig, transactions. If you are familiar with Bitcoin's scripting capabilities, you know that it is possible to create a Bitcoin multisig account which can only spend funds when...
Yeah, so this makes things, I think, more confusing, because based on the way that it's written here, it means that you can't really have private mempools. But then I don't know how that happens. I think I need to study this, because I don't know what a peer-to-peer network is. Like, and it seems for the way that is written here, that is something that Ethereum uses, but is not from Ethereum. So I think that's the case, where it's just a protocol of communication that existed, and then that they incorporated in Ethereum. So I think I have to study. And now it's not really clear to me. Because it says it doesn't explain anything about the, like, what decides the amount of neighbors. Validates the transactions as soon as they receive it. So it's also not clear if it's referring to the mempool here, when it says that it copies and then propagates. And they can filter. This is interesting.
Recording on the blockchain. While all the nodes in Ethereum are equal peers, some of them are operated by miners and are feeding transactions and blocks to mining farms, which are computers with high-performance graphics processing units, GPUs. The mining computers at
So I guess that's the part, but it's still not clear how does it do that. Operator miners and are feeding transactions and blocks to mining farms. Like this is the part that I wanted you, like how does that work? Because if you send the transaction through the network, then like how is it possible that you take that transaction out of the network and then you do the I guess that you just create a simple communication between your nodes and the miners. So you just send the data, like, and this means that they wouldn't be part of the Ethereum, but you can send the data and then they run the calculations because they have the data, and then they send the result again to the miner, and then once they send the result to the miner, then it gets validated. That's probably what's going on. But this means that like the mining, the GPUs that they're using to mine are not part of Ethereum. They are outside, and then they're just receiving the data from outside and doing the calculations. But then that means that anyone that has access to that node then can run the calculation as well. Yeah, but the thing is you need to have a connection with the node. Like, I'm not really sure if it is completely clear to me still.
the mining computers add transactions to a candidate block in attempt to find a proof of work that makes the candidate block valid. We will discuss this in more detail in consensus. Without going into too much detail, valid transactions will eventually be included in a block of transactions and, thus, recorded in the Ethereum blockchain. Once mined into a block, transactions also modify the state of the Ethereum singleton, either by modifying the balance of an account, in the case of a simple payment, or by invoking contracts that change their internal state. These changes are
Like the main thing that I want to understand is the connection between the RPC and the nodes. Like, how does it work? Because I don't understand really well. So for example, I have this thing that I'm running here, which is a node. Then how does it work for making this an RPC point, for example? Like as far as I understand right now, I can just use a Web3 library and then I can open another command prompt. And because I have the way that I set up this, I have the localhost connection. That means that only I can interact with this node from my localhost. But then if I wanted to, I could put another configuration and then it would allow other people to interact with this node as well. And I assume that that's the way that it works on other RPC endpoints. But then something like MetaMask, like how does it work? This is the part that is confusing to me. Even after reading the sections about the wallet. It's not very clear this connection between the wallet provider that creates the seeds and stuff like that, and how does it connect to the blockchain. I guess it is just sending, like, but in order to send the transactions, it needs to have some sort of protocol or server or something like that. And I guess it uses the browser window object. That's how we do it. How it does it. Yeah, but still, you would need a program there to run on the browser that communicates with Ethereum. It's probably, and then that's the thing. So what I imagine is happening is that it's just a bunch of code that is like part of the wallet, and the code has all the functions that use the RPC, the JSON RPC thing from Ethereum to connect the wallet, which is just using the addresses that it creates based on those seeds, based on the seed that creates the other child addresses, like it explained before.
These changes are recorded alongside the transaction, in the form of a transaction receipt, which may also include events. We will examine all this in much more detail in EVM chapter. A transaction that has completed its journey from creation through signing by an EOA, propagation, and finally mining has changed the state of the singleton and left an indelible mark on the blockchain. Multiple signature, multisig, transactions. If you are familiar with Bitcoin's scripting capabilities, you know that it is possible to create a Bitcoin multisig account which can only spend funds when multiple parties sign the transaction. We will examine all this in much more detail in EV chapter. A transaction that has completed its journey from creation through signing by an EOA, propagation, and finally mining has changed the state of the singleton and left an indelible mark on the blockchain. Multiple signature, multisig, transactions. If you are familiar with Bitcoin's scripting capabilities, you know that it is possible to create a Bitcoin multisig account which can only spend funds when multiple parties sign the transaction. Example 2 of 2 or 3 of 4 signatures. Ethereum's basic EOA value transactions have no provisions for multiple signatures. However, arbitrary signing restrictions can be enforced by smart contracts with any conditions you can think of to handle the transfer of Ether and tokens alike. To take advantage.
And this is where account abstraction goes into play, I think. Where it uses a smart contract to do this multi-sig thing, and then there's some stuff you can do with it. I don't remember really well.
To take advantage of this capability, Ether has to be transferred to a wallet contract that is programmed with the spending rules desired, such as multi-signature requirements or spending limits, or combinations of the two. The wallet contract then sends.
Yeah, I guess you can have a dApp sign the transaction for you, or something like that. And that's the whole thing about account abstraction.
The wallet contract then sends the funds when prompted by an authorized EOA once the spending conditions have been satisfied. For example, to protect your Ether under a multisig condition, transfer the Ether to a multisig contract. Whenever you want to send funds to another account, all the required users will need to send transactions to the contract using a regular wallet app, effectively authorizing the contract to perform the final transaction. These contracts can also be designed to require multiple signatures before executing local code or to trigger other contracts. The security of the scheme is ultimately determined by the multisig contract code. The ability to implement multi-signature transactions as a smart contract demonstrates the flexibility of Ethereum. However, it is a double-edged sword, as the extra flexibility can lead to bugs that undermine the security of multi-signature schemes. There are, in fact, a number of proposals to create a multi-signature command in the EVM that removes the need for smart contracts, at least for the simple MEV and multi-signature schemes. This would be equivalent to Bitcoin's multi-signature system, which is part of the core consensus rules and has proven to be robust and secure. Conclusions. Transactions are the starting point of every activity in the Ethereum system. Transactions are the inputs that cause the Ethereum virtual machine to evaluate contracts, update balances, and more generally modify the state of the Ethereum blockchain. Next, we will work with smart contracts in a lot more detail and learn how to program in the Solidity contract-oriented language.
Yeah, but so far I've been really liking this book. It's very good. And I'm probably gonna read it again, I think. We're gonna read this multiple times, to be honest. Along with the yellow paper. Until I really start, like, to not get it, but to, I don't know how to say that in English. Like, incorporate the learning. And it becomes more intuitive. I have more clarity over everything. And only after that, I think I'm gonna think about studying the other blockchains. But I think I already have a very decent, like, level of understanding of how things are connected. At least much better than I had before. Like a couple of months back, I think. I think I already know, understand pretty well how it works. The only thing to clarify is the RPC thing, the connection between the RPC and the nodes, and how is the number of the nodes determined. I think studying the peer-to-peer is gonna help me understand a lot, I think. Watching these videos here, probably. What is this? The extension broke. I'm waiting to see if it's gonna start. If it doesn't work, then I think I'm just gonna go back to writing the article. And I think I have to change on the article the whole thing about private and public. But that's the thing, I need to study this stuff more to be able to explain the details there. I'm very confident that it is what I was talking about, where it leads to centralization, but about the details, I don't know. And it doesn't look like it's gonna work.
A peer-to-peer network, sometimes referred to as a P2P network, is one of the key parts of blockchain technology and is a huge improvement in how we store our data. But let's start with, what is a network? A network is a group of interconnected devices that exchange information. These devices can be connected locally, via cable, or wirelessly through the internet. The most commonly used type of network is a centralized client-server model. A client-server network is a single server, often operated by a single entity such as one company. This server will handle all the tasks and requests on the network and store all the information exchanged. Because there is a central authority storing and managing all the information, this model has some serious problems. For example, all the private data can be stolen by hacking one server, and the user has almost no control in the way that their information is controlled or even exploited. For example, you don't own any of the photos that you upload to social media. The company that owns the social media network owns your photos, and it can do whatever it likes with them. Blockchain networks are different from traditional client-server models because there's no central point of storage and therefore no controlling party. Instead, all the information on the network is constantly recorded and transferred between the participants on the network, who all store multiple identical copies of the network's information. These participants are known as nodes, or peers. So, a peer-to-peer network is a distributed network that stores and transfers data without a central server. Blockchain technology is built on top of P2P networks. Having no central point of storage makes the information on a network far less vulnerable to being hacked, exploited, or lost, which is why P2P networks and blockchain technology in particular are seen as huge improvements on traditional centralized models and are the future of data storage.
Yeah, it doesn't explain what I wanna know.
Many of the protocols online organize communication between computers that are participating in the protocol along the lines of the client-server model. So there's a server that's available all the time, and there are clients that connect to the server to retrieve information. So a classic example of this is the web. There's some web server somewhere. Maybe this is a client server type of interaction. Remember, the server has to be online all the time. If I'm trying to browse to www.upload.edu and that server is down, then I can't retrieve the information. There's no one else to get that information. So the availability of this particular website is entirely determined by whether or not this server is available. Now, let's think about how you might distribute. Now, normally for web pages, if the server is down, it's because maybe somebody screwed up over a cable or whatever, or sound for maintenance or something like that. But let's say you're trying to distribute something online that is more controversial. Let's say, for example, you're trying to make it possible for people to download music files that they shouldn't have access to. In that case, setting up a centralized server is a problem. The reason it's a problem is because let's say that I'm trying to distribute MP3s online, and I set up a server and I put a bunch of MP3s up there and I say they're free, music should be free, everybody should go and download my MP3s, and music should be free. Right? Music shouldn't be free. We should pay artists. But let's say that's your model. So you put up your server, you put all your content there, and you tell everyone come get it. So what's going to happen? First thing that's going to happen is about 10 minutes later, the recording industry of America is going to notice this, and they're going to talk to whoever's providing the connection to your server, and they're going to say, by the way, that server has all sorts of copyrighted content on it, and that's not something that is legal to distribute. And so what's going to happen is someone's going to come get the server and take it offline. Once that server is offline, any of the clients that were trying, all these people out there that are desperate to download my MP3s, won't be able to access that content. And so the client-server model, while it's great for lots of legitimate types of internet services, including the above four, it also means that in the case where the server is down for some reason, the clients that are participating in the protocol online, the protocol of the system will subset them. Same thing.
This explain it.
Centralized infrastructure with those peers directly.
I don't think this video is
Alright
explain.
guys, in my client-server architecture video, we learned why they are so popular and common. Wherein typically a server will be serving multiple clients. Peer-to-peer is a network architecture in which each computer or device on the network can function as both server and a client. This means that rather than having a single central server hosting all of the content, each user can host some of it. Peer-to-peer networks are relatively advanced, which make it a good candidate to know for your system design interviews. Perhaps the best way to understand what peer-to-peer network is and how they work is through an example. Let's say you are asked to design a system for a big tech company, wherein you need to download and transfer large video footage files from security cameras to thousands of machines at once. So here I have a server on one machine which will deploy or transfer large files to thousands of other machines. Now in any system design interview, it is sometimes important a powerful data center, which will have a total network throughput of say servers in a balanced way, meaning each server will serve about 100 machines, and this will speed up our system by 10 times over. So some machines will request the file to this server, some machines will request the file to this server, all the machines. But then we run into the same issue, where if a machine has to transfer the file to all the other 1,000 machines, one server machine will become bottleneck for all those 1,000 machines. None of our approaches have worked so far, and as you might have guessed by now, that is where peer-to-peer networks comes into play. Let's see how we can improve the system using peer-to-peer network. In a peer-to-peer network, you refer to machines as peers. So instead of saying 1,000 machines to a server, we call them as peers. The idea is that they will work together as peers to achieve a common goal. Now let's go back to our first solution, where we had just one server machine trying to send the 5 GB files to this 1,000 machine, and so there was a bottleneck. Now what if instead we were to split up the 5 GB file? That is, we split up the file in small chunks and send these chunks to all the peers, and then let the peers communicate with each other to find the missing chunks from each other, and build up their own total file. That is the general gist of a peer-to-peer network. Continuing with our example, let's say we divide 5 GB files into 1,000 files of size 5 MB each. After we split the 5 GB files into 1,000 5 MB megabyte files, we can now transfer all these 1005 megabyte files into 1000 machines. That is, we send one 5 megabyte file to each machine. And this will take 1 second because 1005 megabyte file is effectively 5 gigabyte file. And since we assumed a network throughput of 5 gigabyte per second, this means we can transfer 1005 megabyte files per second to 1000 machines. So if a single machine has one 5 megabyte file, now it needs 999 remaining 5 megabyte files. And so a single machine needs to talk to 999 other machines to get the missing pieces it doesn't have. Now the big question is, how long will it take a single machine to receive all the 999 files? Well, it would take 0.999 seconds to get all the other files. Because 5 gigabyte file take 1 second, and we have divided 5 gigabyte file into 1005 megabyte files. So to transfer one file 1 second to get the complete file, compare our nice solution of using the with one. Whereas in our peer-to-peer network solution, we have transferred 3 5 megabyte solution. Okay, so let's go to the third step. Here we transfer another chunk in our nice solution. And so let's mark it 3. And in our peer-to-peer network solution, let's say this machine receives number 3 chunk. And then we have 3 peers which will send their chunks to one of their peers simultaneously. Let's number them accordingly. As you can see at step 3 with our nice solution, we have now transferred 3 chunks of 5 megabytes. Whereas in our peer-to-peer solution, we have transferred 7 5 megabyte chunks. As you can imagine, at each step with our peer-to-peer network solution, the rate of transfer will grow exponentially as compared to our nice solution. Because we have so many peers who can communicate to each. This can be done in a couple of ways. One is by having, based upon that information, the other peer will at each peer level to store information on what peer has what data. It's called distributed hash table or DHT. Peer-to-peer networks can be extremely gossip or talk to each other and figure out which peer they should be sending data or receiving data from. So instead of having a central database or tracker, each peer will now carry mappings of what chunks they have received versus what they need. So one peer might say, I have chunk 2, 4, and 7, and I know this peer carries chunk 1 and 5. Based upon that information, the other peer will know which peer to go next to. Now this kind of a setup is usually implemented by each peer having its own hash table. For example, peer 1 will have hash table that will map IP address of peer to the chunks it has got. Same goes with other peers. They exchange information with other peers, keep populating and sharing their local hash table information with other peers. This concept of using hash table at each peer level to store information on what peer has what data is called distributed hash table or DHT. Peer-to-peer networks can be extremely fast, and they have lots of applications. You can in fact check out the system pattern that was created by Uber. Link to the GitHub page in the description.
I'm gonna have to look at the source code for specifics, I think. Because this part of the videos that the videos are explaining, I already understand.
Peer-to-peer network. In a peer-to-peer network, the peers are computer systems that are connected to each other via the internet. Files can be shared directly between systems on the network without the need for a central server. In other words, each resource is available to other users or to access shared. A peer-to-peer network is designed around the notion of equal peer nodes, simultaneously functioning as both clients and servers to the other nodes on the network. This model of network arrangement differs from the client-server model where communication is usually to and from the central server. A typical example of a file transfer that uses the client-server model is the file transfer protocol service, in which the client and server programs are distinct. The clients initiate the transfer, and the servers satisfy these requests. Peer-to-peer networks generally implement some form of virtual overlay network on top of the physical network topology, where the nodes in the overlay form a subset of the nodes in the physical network. Data is still exchanged directly over the underlying TCP/IP network, but at the application layer, peers are able to communicate with each other directly via the logical overlay links, each of which corresponds to a path through the underlying physical network. Overlays are used for indexing and peer discovery, and make the peer-to-peer system independent from the physical network topology. Based on how the nodes are linked to each other within the overlay network, and how resources are indexed and located, we can classify networks as unstructured or structured, or as a hybrid between the two. Unstructured networks. Unstructured peer-to-peer networks do not impose a particular structure on the overlay network by design, but rather are formed by nodes that randomly form connections to each other. Gnutella, Gossip, and Kazaa are examples of unstructured peer-to-peer protocols. Because there is no structure globally imposed upon them, unstructured networks are easy to build and allow for localized optimizations to different regions of the overlay. Also, because the role of all peers in the network is the same, unstructured networks are highly robust in the face of high rates of churn, that is, when large numbers of peers are frequently joining and leaving the network. However, the primary limitations of unstructured networks also arise from this lack of structure. Shared by only a few other peers. Ownership of each file to a particular peer. Nodes in a structured overlay must maintain lists of neighbors, discovering resources, and networks. Many peer-to-peer file sharing networks, such as some proprietary multimedia applications use a peer-to-peer network along with streaming servers to stream audio and video to their clients. Peercasting for multicasting streams. Pennsylvania. Energy trading. Companies such as
Blah blah blah. I think this one is not gonna work. I don't understand what's going on. He's opening this stuff. Maybe if I select everything.
Smart contracts and solidity. As
There
we
we go.
discussed in intro chapter, there are 2 different types of accounts in Ethereum: externally owned accounts, EOAs, and contract accounts.
I think
EOAs are controlled by users, often
I'm gonna review this article, like the parts that I wrote about the private and public. And I'm gonna review it so I know which question I'm trying to answer. Which I think I already know, but roughly, but just to review. Ethereum is one of the most popular blockchain protocols. Previously, it used to work with a proof of work model and now has to move to proof of stake. Proof of work system, there is something called a miner, which is someone that offers computing power in order to solve a mathematical puzzle in exchange for tokens from the blockchain protocol. Ethereum, these miners had the ability to build transaction blocks in a way that would maximize the amount of profit they would make from each block. In this article, I'm going to explain how this process of maximizing the amount of value a miner would get, more commonly called miner extractable value, has changed the Ethereum ecosystem and why it is one of the most important aspects of the blockchain protocols. In order to have transactions processed by people have to pay a fee. In Ethereum's case, it's called gas, so that the miner has an incentive to validate their transaction. The higher the fee, gas, the higher the chance the miner will give that transaction a higher priority. Also, over time, people realize that there is a lot of value in knowing which transactions are going to happen first. So a lot of attacks started happening because of that. Some of the most popular were front-running sandwich attacks, bandit attacks, and DEX arbitrage. What is mempool and how this works? Before transactions become part of the official Ethereum blockchain history, they go through a network of miners that perform calculations in order to validate them and decide in what position they will be put in the block. This is called a mempool. An analogy would be an exchange where people place transactions, but they are not executed right away. They only happen after someone fulfills their order. The difference is that instead of needing someone to fulfill the order, the miner has to validate the transaction and include it in a block. These parts, it feels like there's something missing here because of the way that I wrote this. Be an exchange where people place transactions, but they are not executed right away. They only happen after someone fulfills their order. The difference is that instead of someone needing to fulfill the order, to validate the transaction. Okay. But maybe it's good enough. Maybe I should put the equivalent of someone fulfilling an order. Miners are not all connected. Instead of thinking about it like a giant network of miners across the world, think about several different smaller groups of miners that are connected to each other. This means that different groups will have different mempools and a different RPC. This is the stuff that I don't know. So maybe I should. Because that's the thing that is not clear here. Is how the propagate, like at what point, because of the book there, it doesn't describe this really well, I think. Like at what point the transactions that are propagated propagated are considered the mempool. Like where does the mempool fit in on that thing? Because as it says there, it seems like each node validates first. Like the mempools are separate, only based on one node, but I think that doesn't make sense. Like I think the mempool is the connection of peers for each node, probably. And the RPC, like that's why it's different for each RPC, because each RPC is gonna connect with a different set of neighbors. So all the peers are connected to each other, but the thing is that each peer is connected to an average of 13 nodes or something like that. So it is not like each peer is connected through the whole network, just connected to its neighbors. And then the neighbors that is connected to would be considered the mempool for that specific node. But then how do you make that private? I guess that what to make private is the connection between the node and the miners. That's where the privacy comes from. Because the mining is done off chain, that's the thing. Because you need more computational power to gain. So that's where the private pool comes from, probably. So maybe I will rewrite this part here. Because works using a peer. Ethereum works using a peer-to-peer network protocol. Each node is only connected with a set of neighbors, not the entire network of nodes. Also, some of the nodes offload the work to mine. For GPUs. Hardware that exists outside of the chain. And then this part is the one that I'm gonna explain this one. I think that this one is good enough to leave it like this. Before transactions become part of the official Ethereum blockchain history, they go through a network of miners that perform calculations in order to validate them. Network of nodes. They perform in order to validate them and decide in what position they will be put in the block. I'm gonna leave this part out because I'm not really sure. Like I don't think that's how it works, because it depends on which node it is, and yeah, I think that you can have some nodes. Some nodes are going to be nodes that are mining, which means that they are going to do the calculation and choose the blocks. But that's the part that is still unclear to me, which is the definition of the mempool, like the specifics when it comes to the details. Like how many nodes are going to be part of each mempool, and how does this process work of the like how do you offload the work to miners outside of the thing? Is it through an RPC endpoint where you communicate? I guess like to mine, I remember that you can pass certain parameters that and it's gonna make your node mine, which means it's gonna use the resources of the GPU that it's using. But obviously that wouldn't be the case in this case here where you're offloading the work for other GPUs. So that's the stuff that I wanna understand. And also when it comes to mining pools, how is that possible? I imagine that is an algorithm that you install and then it uses GPUs from everyone to run some calculations, and it's kind of like decentralizing the calculation, where each GPU does some part of the job, and then collectively they all arrive at the solution faster. But it's still not really clear to me how it works. Well, then, this is called a mempool. Uh, you raised something there after this dance. And that perform calculations. Go through a network of nodes. Yeah. Analogy would be an exchange where people place transactions, but they are not executed right away. They only happen after someone fulfills their order. Difference that in Ethereum, the equivalent of someone fulfilling their order would be the miner validating the transaction and including it in a block. Because the Ethereum works using a peer-to-peer network protocol, each node is only connected with a set of neighbors, not the entire network of nodes. Also, some of the nodes offload the work to mine for specialized GPUs and hardware that exists outside of the chain. Yeah, this is the part. I have to think more because the thing is I don't wanna talk about like I don't wanna go on the tangent talking about mining pools and stuff like that. I guess I'll continue to read there. Like, what is the question though? So how People load the work. How? I think that those are the two questions here to understand. Like, what is the part? I think studying flashbots again is gonna be better to understand how it works. This is still confusing. Like, how exactly is the mempool defined? What portion is private? How is it possible? Flashbots and control. So from my current level of understanding, I think what was happening is just deal with the miners, and is this kind of thing where, like, imagine you are a miner and you have a lot of computing power, and then you set up a node, and then your node receives transactions, and then somehow you create a program that sends those transactions through external GPUs, and then you use those external GPUs to mine. So you set up a mining node, but it's not the mining node that is doing the mining. Like, you're offloading the work to other external GPUs. And then because of this, it increases the likelihood that your transactions are going to be, and your blocks are going to be included first. And also because you are more capable of building better blocks that give more money based on the order of transactions. And then because of that, it creates this centralization, because the network itself is not centralized because it's peer-to-peer, and the mempool is not centralized, but what is centralized is the connection of mempool, is the connection of the mempool with the miners, because the miners that have the most computing power are the ones that validate transactions most often, and that make the most money. But then, and then that is centralized because only a few miners starts getting all of the transactions because they validate more. But still don't understand how that, like, would centralize too much, because yeah, I guess so. I have to understand how what is the algorithm, because I remember there is some element of luck as well to validate. But yeah, I guess it's because of computing power, because if you're always, and this is the thing that it doesn't make sense, because if you have the most computing power, then you always validate all the transactions. So it doesn't make a lot of sense how proof of work works, because you can validate faster, I think. Yeah, I still don't know. So how RPCs are connected to nodes? This is the kind of questions I think I need to clarify. How the relationship between the endpoints, the miners, the nodes work, and the exact definition of what defines each mempool. If it is just based on the node and the neighbors that it has, in which case each specific node will have a different mempool because it has different neighbors. I think that's what happens. And then what determines who is gonna mine what? Is it just a computational power? And is it an issue if only one or a few people mine? Like what is... I assume the answer to that would be that they can control what transactions are done and what transactions are not done, and they can also control the order of the block. Like they have control over the network, but intuitively that makes sense. But I'm thinking more about the details of it, like thinking about the algorithms themselves and how it works. Like that's the stuff that I don't really understand really well. The concept level is pretty easy to understand, but like when it actually comes to the code here and like doing things with the node is not very clear to me how it works.
EOAs are controlled by users.
I think I'm gonna grab something to eat and I'm gonna continue to read this stuff. I think after I eat, I'm also gonna meditate like for 15 minutes or something like that because I'm already tired. So, and then I'll probably read for the rest of the stream, or maybe I'll search for, or search on either use ChatGPT or search on Google or DuckDuckGo to try to answer these questions here, to clarify my mind. So I'll be right back.
EOAs are controlled by users. EOAs are controlled by users, often via software such as a wallet application that is external to the Ethereum platform. In contrast, contract accounts are controlled by program code, also commonly referred to as smart contracts, that is executed by the Ethereum virtual machine. In short, EOAs are simple accounts without any associated code or data storage, whereas contract accounts have both associated code and data storage. EOAs are controlled by transactions created and cryptographically signed with a private key in the real world external to and independent of the protocol. Whereas contract accounts do not have private keys and so control themselves in the predetermined way prescribed by their smart contract code. Both types of accounts are identified by an Ethereum address. In this chapter, we will discuss contract accounts and the program code that controls them. What is a smart contract? The term smart contract has been used over the years to describe a wide variety of different things. In the 1990s, cryptographer Nick Szabo coined the term and defined it as a set of promises, specified in digital form, including protocols within which the parties perform on the other promises. Since then, the concept of smart contracts has evolved, especially after the introduction of decentralized blockchain platforms with the invention of Bitcoin in 2009. In the context of Ethereum, the term is actually a bit of a misnomer, given that Ethereum smart contracts are neither smart nor legal contracts, but the term has stuck. In this book, we use the term smart contracts to refer to immutable computer programs that run deterministically in the context of an Ethereum virtual machine as part of the Ethereum network protocol I.E. On the decentralized Ethereum world computer. Let's unpack that definition. Computer programs. Smart contracts are simply computer programs. The word contract has no legal meaning in this context. Immutable. Once deployed, the code of a smart contract cannot change. Unlike with traditional software, the only way to modify a smart contract is to deploy a new instance. Deterministic. The outcome of the execution of a smart contract is the same for everyone who runs it. Given the context of the transaction that initiated its execution and the state of the Ethereum blockchain at the moment of execution. EVM context. Smart contracts operate with a very limited execution context. They can access their own state, the context of the transaction that called them, and some information about the most recent blocks. Decentralized world computer. The EVM runs as a local instance on every Ethereum node. But because all instances of the EVM operate on the same initial state and produce the same final state, the system as a whole operates as a single world computer. Life cycle of a smart contract. Smart contracts are typically written in a high-level language, such as Solidity. But in order to run, they must be compiled to the low-level bytecode that runs in the EVM. Once compiled, they are deployed on the Ethereum platform using a special contract creation transaction, which is identified as such by being sent to the special contract creation address, namely 0x0, C. Contract reg. Each contract is identified by an Ethereum address, which is derived from the contract creation transaction as a function of the originating account in nonce. The Ethereum address of a contract can be used in a transaction as the recipient, sending funds to the contract or calling one of the contract's functions. Note that, unlike with EOAs, there are no keys associated with an account created for a new smart contract. As the contract creator, you don't get any special privileges at the protocol level, although you can explicitly code them into the smart contract. You certainly don't receive the private key for the contract account, which in fact does not exist. We can say that smart contract accounts own themselves. Importantly, contracts only run if they are called by a transaction. All smart contracts in Ethereum are executed, ultimately, because of a transaction initiated from an EOA. A contract can call another contract that can call another contract, and so on, but the first contract in such a chain of execution will always have been called by a transaction from an EOA. Contracts never run on their own or in the background. Contracts effectively lie dormant until a transaction triggers execution, either directly or indirectly as part of a chain of contract calls. It is also worth noting that smart contracts are not executed in parallel. In any sense, the Ethereum world computer can be considered to be a single-threaded machine. Transactions are atomic. They are either successfully terminated or reverted. A successful termination of a transaction means different things under different scenarios. 1. If a transaction is sent from an EOA to another EOA, then any changes to the global state, e.g. account balances, made by the transaction are recorded. 2. If a transaction is sent from an EOA to a contract that does not invoke any other contracts, then any changes to the global state are recorded, e.g. account balances. State variables of the contracts. 3. If a transaction is sent from an EOA to a contract that only invokes other contracts in a manner that propagates errors, then any changes to the global state are recorded, e.g. account balances, state variables of the contracts. And 4. If a transaction is sent from an EOA to a contract that invokes other contracts in a manner that does not propagate errors, then there may only be some changes to the global state recorded, e.g. account balances, state variables of the non-erroring contracts, whereas other changes to the global state are not recorded, e.g. state variables of the erroring contracts. Otherwise, if a transaction is reverted, all of its effects, changes in state, are rolled back as if the transaction never ran. A failed transaction is still recorded as having been attempted, and the ether spent on gas for the execution is deducted from the originating account. But it otherwise has no other effects on contract or account state. As mentioned previously, it is important to remember that a contract's code cannot be changed. However, a contract can be deleted, removing the code in its internal state, storage, from its address, leaving a blank account. Any transactions sent to that account address after the contract has been deleted do not result in any code execution, because there is no longer any code there to execute. To delete a contract, you execute an EVM opcode called self-destruct, previously called suicide. That operation costs negative gas, a gas refund, thereby incentivizing the release of network client resources from the deletion of stored state. Deleting a contract in this way does not remove the transaction history, past, of the contract, since the blockchain itself is immutable. It is also important to note that the self-destruct capability will only be available if the contract author programmed the smart contract to have that functionality. If the contract's code does not have a self-destructive code, or it is inaccessible, the smart contract cannot be deleted. Introduction to Ethereum high-level languages. The EVM is a virtual machine that runs a special form of code called EVM bytecode. Analogous to your computer's CPU, which runs machine code such as x86-64. We will examine the operation and language of the EVM in much more detail in EVM chapter. In this section we will look at how smart contracts are written to run on the EVM. While it is possible to program smart contracts directly in bytecode, EVM bytecode is rather unwieldy and very difficult for programmers to read and understand. Instead, most Ethereum developers use a high-level language to write programs, and a compiler to convert them into bytecode. While any high-level language could be adapted to write smart contracts, adapting an arbitrary language to be compilable to EVM bytecode is quite a cumbersome exercise and would in general lead to some amount of confusion. Smart contracts operate in a highly constrained and minimalistic execution environment, the EVM. In addition, a special set of EVM-specific system variables and functions needs to be available. As such, it is easier to build a smart contract language from scratch than it is to make a general-purpose language suitable for writing smart contracts. As a result, a number of special-purpose languages have emerged for programming smart contracts. Ethereum has several such languages, together with the compilers needed to produce EVM executable bytecode. In general, programming languages can be classified into two broad programming paradigms: declarative and imperative, also known as functional and procedural, respectively. In declarative programming, we write functions that express the logic of a program, but not its flow. Declarative programming is used to create programs where there are no side effects, meaning that there are no changes to state outside of a function. Declarative programming languages include Haskell and SQL. Imperative programming, by contrast, is where a programmer writes a set of procedures that combine the logic and flow of a program. Imperative programming languages include C++ and Java. Some languages are hybrid, meaning that they encourage declarative programming but can also be used to express an imperative programming paradigm. Such hybrids include Lisp, JavaScript, and Python. In general, any imperative language can be used to write in a declarative paradigm, but it often results in inelegant code. By comparison, pure declarative languages cannot be used to write in an imperative paradigm. In purely declarative languages, there are no variables. While imperative programming is more commonly used by programmers, it can be very difficult to write programs that execute exactly as expected. The ability of any part of the program to change the state of any other makes it difficult to reason about a program's execution and introduces many opportunities for bugs. Declarative programming, by comparison, makes it easier to understand how a program will behave, since it has no side effects. Any part of a program can be understood in isolation. In smart contracts, bugs literally cost money. As a result, it is critically important to write smart contracts without unintended effects. To do that, you must be able to clearly reason about the expected behavior of the program. So, declarative languages play a much bigger role in smart contracts than they do in general-purpose software. Nevertheless, as you will see, the most widely used language for smart contracts, Solidity, is imperative. Programmers, like most humans, resist change. Currently supported high-level programming languages for smart contracts include Ordered by Approximate Age LLA Functional, Declarative, Programming Language, with Lisp-like syntax. It was the first high-level language for Ethereum smart contracts but is rarely used today. Serpent A Procedural, Imperative, Programming Language with a syntax similar to Python. Can also be used to write functional, declarative, code, though it is not entirely free of side effects. Solidity A Procedural, Imperative, Programming Language with a syntax similar to JavaScript, C++, or Java. The most popular and frequently used language for Ethereum smart contracts. Viper, a more recently developed language, similar to Serpent and again with Python-like syntax. Intended to get closer to a pure functional Python-like language than Serpent, but not to replace Serpent. Bamboo, a newly developed language, influenced by Erlang, with explicit state transitions and without iterative flows, loops. Intended to reduce side effects and increase auditability. Very new and yet to be widely adopted. As you can see, there are many languages to choose from. However, of all of these, Solidity is by far the most popular, to the point of being the de facto high-level language of Ethereum and even other EVM-like blockchains. We will spend most of our time using Solidity, but we'll also explore some of the examples in other high-level languages to gain an understanding of their different philosophies. Building a smart contract with Solidity. Solidity was created by Dr. Gavin Wood, co-author of this book, as a language explicitly for writing smart contracts with features to directly support execution in the decentralized environment of the Ethereum world computer. The resulting attributes are quite general, and so it has ended up being used for coding smart contracts on several other blockchain platforms. It was developed by Christian Reitewisner and then also by Alex Bergzazi, Liana Huzikian, Yoichi Hire, and several former Ethereum core contributors. Solidity is now developed and maintained as an independent project on GitHub. The main product of the Solidity project is the Solidity compiler, SOLC, which converts programs written in the Solidity language to EVM bytecode. The project also manages the important application binary interface, ABI, standard for Ethereum smart contracts, which we will explore in detail in this chapter. Each version of the Solidity compiler corresponds to and compiles a specific version of the Solidity language. To get started, we will download a binary executable of the Solidity compiler. Then we will develop and compile a simple contract, following on from the example we started with in Intro chapter. Selecting a version of Solidity. Solidity follows a versioning model called semantic versioning, which specifies version numbers structured as three numbers separated by dots. Major.minor.patch. The major number is incremented for major and backward incompatible changes. The minor number is incremented as backward compatible features are added in between major releases. And the patch number is incremented for backward compatible bug fixes. At the time of writing, Solidity is at version 0.6.4. The rules for major version 0, which is for initial development of a project, are different. Anything may change at any time. In practice, Solidity treats the minor number as if it were the major version and the patch number as if it were the minor version. Therefore, in 0.6.4, 6 is considered to be the major version and 4 the minor version. The 0.5 major version release of Solidity is anticipated imminently. As you saw in intro chapter. Your Solidity programs can contain a pragma directive that specifies the minimum and maximum versions of Solidity that it is compatible with, and can be used to compile your contract. Since Solidity is rapidly evolving, it is often better to install the latest release. Download and install. There are a number of methods you can use to download and install Solidity, either as a binary release or by compiling from source code. You can find detailed instructions in the Solidity documentation. Here's how to install the latest binary release of Solidity on an Ubuntu/Debian operating system, using the apt package manager. $sudo add apt repository p. The Solidity compiler command line interface version 0.6.4 plus commit.1 dca32f3.linux.g++. For more information see https://github. However, you might find that some text editors designed for development, such as Emacs, Vim, and Atom, offer additional features such as syntax highlighting and macros that make Solidity development easier. There are also web-based development environments, such as Remix IDE and Ethfiddle. Use the tools that make you productive. In the end, Solidity programs are just plain text files. While fancy editors and development environments can make things easier, you don't need anything more than a simple text editor, such as Nano, Linux/Unix, TextEdit, Mac OS, or even Notepad, Windows. Simply save your program source code with a .sol extension and it will be recognized by the Solidity compiler as a Solidity program. Writing a simple Solidity program. In intro chapter, we wrote our first Solidity program. When we first built the Faucet contract, we used the Remix IDE to compile and deploy the contract. In this section, we will revisit, improve, and embellish Faucet. Our first attempt looked like Faucet.sol, a Solidity contract implementing a Faucet. Example 1. Faucet.sol, a Solidity contract implementing a Faucet link code /Solidity/Faucet.sol compiling with the Solidity compiler, Solc. Now, we will use the Solidity compiler on the command line to compile our contract directly. The Solidity compiler Solc offers a variety of options, which you can see by passing the help argument. We use the bin and optimize arguments of Solc to produce an optimized binary of our example contract. $Solc optimize bin binary that can be submitted to the Ethereum blockchain. The Ethereum contract ABI. In computer software, an application binary interface is an interface between two program modules, often between the operating system and user programs. An ABI defines how data structures and functions are accessed in machine code. This is not to be confused with an API, which defines this access in high-level, often human-readable formats as source code. The ABI is thus the primary way of encoding and decoding data into and out of machine code. In Ethereum, the ABI is used to encode contract calls for the EVM and to read data out of transactions. The purpose of an ABI is to define the functions in the contract that can be invoked and describe how each function will accept arguments and return its result. A contract's ABI is specified as a JSON array of function descriptions, c. functions, and events, c. events. A function description is a JSON object with fields type, name, inputs, outputs, constant, and payable. An event description object has fields type, name, inputs, and anonymous. We use the Sol command line Solidity compiler to produce the ABI for our Faucet.sol example contract. As you can see, the compiler produces a JSON array describing the two functions that are defined by Faucet.sol. This JSON can be used by any application that wants to access the Faucet contract once it is deployed. Using the ABI, an application such as a wallet or dApp browser can construct transactions that call the functions in Faucet with the correct arguments and argument types. For example, a wallet would know that to call the function withdraw it would have to provide a uint256 argument named withdraw amount. The wallet could prompt the user to provide that value. Then create a transaction that encodes it and executes the withdraw function. All that is needed for an application to interact with the contract is an ABI and the address where the contract has been deployed. Selecting a Solidity compiler and language Varion as we saw in the previous code, our Faucet contract compiles successfully with Solidity version 0.6.4. But what if we had used a different version of the Solidity compiler? The language is still in constant flux and things may change in unexpected ways. Our contract is fairly simple, but what if our program used a feature that was only added in Solidity version 0.6.1 and we tried to compile it with 0.6.0? To resolve such issues, Solidity offers a compiler directive known as a version pragma that instructs the compiler that the program expects a specific compiler and language version. Let's look at an example pragma Solidity 0.6.0. The Solidity compiler reads the version pragma and will produce an error if the compiler version is incompatible with the version pragma. In this case, our version pragma says that this program can be compiled by a Solidity compiler with a minimum version of 0.6.0. The symbol states, however, that we allow compilation with any minor revision above 0.6.0, example 0.6.1, but not 0.7.0, which is a major revision, not a minor revision. Pragma directives are not compiled into EVM bytecode. They are only used by the compiler to check compatibility. Let's add a pragma directive to our Faucet contract. We will name the new file Faucet2.sol to keep track of our changes as we proceed through these examples, starting in Faucet2.sol, adding the version pragma to Faucet.example2. Faucet2.sol, adding the version pragma to Faucet link code /Solidity/Faucet2.sol. Adding a version pragma is a best practice, as it avoids problems with mismatched compiler and language versions. We will explore other best practices and continue to improve the Faucet contract throughout this chapter. Programming with Solidity. In this section, we will look at some of the capabilities of the Solidity language. As we mentioned in intro chapter, our first contract example was very simple and also flawed in various ways. We'll gradually improve it here, while exploring how to use Solidity. This won't be a comprehensive Solidity tutorial, however, as Solidity is quite complex and rapidly evolving. We'll cover the basics and give you enough of a foundation to be able to explore the rest on your own. The documentation for Solidity can be found on the project website. Data types. First, let's look at some of the basic data types offered in Solidity. Boolean, bool. Boolean value, true or false, with logical operators. Not, and, or, equals, equal, and, equals, not equal. Integer, int, uint. Signed, int, and unsigned, uint, integers, declared in increments of 8 bits from int 8 to uint 256. Without a size suffix, 256-bit quantities are used to match the word size of the EVM. Fixed point, fixed, fixed. Fixed point numbers, declared with u. Fixed. M. X. N. Where M is the size in bits, increments of 8 up to 256, and N is the number of decimals after the point, up to 18, example u fixed 32x2. Smart contracts and Viper. Viper is an experimental, contract-oriented programming language for the Viper is an experimental, contract-oriented programming language for the Ethereum virtual machine that strives to provide superior auditability by making it easier for developers to produce intelligible code. In fact, one of the principles of Viper is to make it virtually impossible for developers to write misleading code. In this chapter we will look at common problems with smart contracts, introduce the Viper contract programming language, and compare it to Solidity, demonstrating the differences. Vulnerabilities in Viper. A recent study analyzed nearly 1 million deployed Ethereum smart contracts and found that many of these contracts contain serious vulnerabilities. During their analysis, the researchers outlined 3 basic categories of trace vulnerabilities. Suicidal contracts. Smart contracts that can be killed by arbitrary addresses. Greedy contracts. Smart contracts that can reach a state in which they cannot release Ether. Prodigal contracts. Smart contracts that can be made to release Ether to arbitrary addresses. Vulnerabilities are introduced into smart contracts via code. It may be strongly argued that these and other vulnerabilities are not intentionally introduced, but regardless, undesirable smart contract code evidently results in the unexpected loss of funds for Ethereum users, and this is not ideal. Viper is designed to make it easier to write secure code, or equally to make it more difficult to accidentally write misleading or vulnerable code. Comparison to Solidity. One of the ways in which Viper tries to make unsafe code harder to write is by deliberately omitting some of Solidity's features. It is important for those considering developing smart contracts in Viper to understand what features Viper does not have, and why. Therefore, in this section, we will explore those features and provide justification for why they have been omitted. Modifiers. As we saw in the previous chapter, in Solidity you can write a function using modifiers. For example, the following function, changeOwner, will run the code in a modifier called onlyBy as part of its execution. This modifier enforces a rule in relation to ownership. As you can see, this particular modifier acts as a mechanism to perform a pre-check on behalf of the changeOwner function. But modifiers are not just there to perform checks, as shown here. In fact, as modifiers, they can significantly change a smart contract's environment, in the context of the calling function. Put simply, modifiers are pervasive. On the one hand, developers should always check any other code that their own code is calling. However, it is possible that in certain situations, like when time constraints or exhaustion result in lack of concentration, a developer may overlook a single line of code. This is even more likely if the developer has to jump around inside a large file while mentally keeping track of the function call hierarchy and committing the state of smart contract variables to memory. Let's look at the preceding example in a bit more depth. Imagine that a developer is writing a public function called A. The developer is new to this contract and is utilizing a modifier written by someone else. At a glance, it appears that the stage time confirmation modifier is simply performing some checks regarding the age of the contract in relation to the calling function. What the developer may not realize is that the modifier is also calling another function, next stage. In this simplistic demonstration scenario, simply calling the public function results in the smart contract stage variable moving from safestage to dang-erstage. Viper has done away with modifiers altogether. The recommendations from Viper are as follows: if only performing assertions with modifiers, then simply use inline checks and asserts as part of the function. If modifying smart contract state and so forth, again make these changes explicitly part of the function. Doing this improves auditability and readability, as the reader doesn't have to mentally, or manually, wrap the modifier code around the function to see what it does. Class inheritance. Inheritance allows programmers to harness the power of pre-written code by acquiring pre-existing functionality, properties, and behaviors from existing software libraries. Inheritance is powerful and promotes the reuse of code. Solidity supports multiple inheritance as well as polymorphism, but while these are key features of object-oriented programming, Viper does not support them. Viper maintains that the implementation of inheritance requires coders and auditors to jump between multiple files in order to understand what the program is doing. Viper also takes the view that multiple inheritance can make code too complicated to understand, a view tacitly admitted by the Solidity documentation, which gives an example of how multiple inheritance can be problematic. Inline assembly. Inline assembly gives developers low-level access to the Ethereum virtual machine, allowing Solidity programs to perform operations by directly accessing EVM instructions. For example, the following inline assembly code adds 3 to memory location 0x80. Viper considers the loss of readability to be too high a price to pay for the extra power, and thus does not support inline assembly. Function overloading. Function overloading allows developers to write multiple functions of the same name. Which function is used on a given occasion depends on the types of the arguments supplied. Take the following 2 functions, for example. The first function, named f, accepts an input argument of type uint. The second function, also named f, accepts 2 arguments, one of type uint and one of type bytes32. Having multiple function definitions with the same name taking different arguments can be confusing, so Viper does not support function overloading. Variable typecasting. Implicit typecasting is often performed at compile time. For example, if a type conversion is semantically sound and no information is likely to be lost, the compiler can perform an implicit conversion, such as converting a variable of type uint8 to uint16. The earliest versions of Viper allowed implicit typecasting of variables, but recent versions do not. Explicit typecasts can be inserted in Solidity. Unfortunately, they can lead to unexpected behavior. For example, casting a uint32 to the smaller type uint16 simply removes the higher order bits, as demonstrated here. Viper instead has a convert function to perform explicit casts. The convert function, found on line 82 of convert.py. Conversion table equals int 128, to int 128, uint 256, town int 256, decimal, to decimal, bytes 32, to bytes 32. When a developer calls convert, it references conversion table, which ensures that the appropriate conversion is performed. For example, if a developer passes an int 128 to the convert function, the to int 128 function on line 26 of the same convert.py file will be executed. The to int 128 function is as follows. At signature, int 128, uint 256, bytes 32, bytes, strliteral, def to int 120. As you can see, the conversion process ensures that no information can be lost. If it could be, an exception is raised. The conversion code prevents truncation as well as other anomalies that would ordinarily be allowed by implicit typecasting. Choosing explicit over implicit typecasting means that the developer is responsible for performing all casts. While this approach does produce more verbose code, it also improves the safety and auditability of smart contracts. Infinite loop. Although there is no merit because of gas limit, developers can write an endless loop processing in Solidity. Infinite loop makes it impossible to set an upper bound on gas limits, opening the door for gas limit attacks. Therefore, Viper doesn't permit you to write the processing and has the following 3 features. The while statement. You can use while statement in Solidity, but Viper doesn't have the statement. Deterministic number of iterations of for statement. Viper has a for statement, but the upper limit of the number of iterations must be determinate, and range can only accept integer literals. Recursive calling. Recursive calling can be written in Solidity, but not in Viper. Preconditions and postconditions. Viper handles preconditions, postconditions, and state changes explicitly. While this produces redundant code, it also allows for maximal readability and safety. When writing a smart contract in Viper, a developer should observe the following 3 points. Condition. What is the current state/condition of the Ethereum state variables? Effects. What effects will this smart contract code have on the condition of the state variables upon execution? That is, what will be affected, and what will not be affected. Are these effects congruent with the smart contract's intentions? Interaction. After the first 2 considerations have been exhaustively dealt with, it is time to run the code. Before deployment, logically step through the code and consider all of the possible permanent outcomes, consequences, and scenarios of executing the code, including interactions with other contracts. Ideally, each of these points should be carefully considered and then thoroughly documented in the code. Doing so will improve the design of the code, ultimately making it more readable and auditable. Decorators. At private. The @private decorator makes the function inaccessible from outside the contract. At public. The @public decorator makes the function both visible and executable publicly. For example, even the Ethereum wallet will display such functions when viewing the contract. At constant. Functions with the @constant decorator are not allowed to change state variables. In fact, the compiler will reject the entire program, with an appropriate error, if the function tries to change a state variable. At payable. Only functions with the @payable decorator are allowed to transfer value. Viper implements the logic of decorators explicitly. For example, the Viper compilation process will fail if a function has both a @payable decorator and a @constant decorator. This makes sense because a function that transfers value has by definition updated the state, so cannot be @constant. Each Viper function must be decorated with either @public or @private, but not both. Function and variable ordering. Each individual Viper smart contract consists of a single Viper file only. In other words, all of a given Viper smart contract's code, including all functions, variables, and so forth, exists in one place. Viper requires that each smart contract's function and variable declarations are physically written in a particular order. Solidity does not have this requirement at all. Let's take a quick look at a Solidity example. In this example, the function called top function is calling another function, lower function. Top function is also assigning a value to a variable called initiatized below top function. As you can see, Solidity does not require these functions and variables to be physically declared before being called upon by the executing code. This is valid Solidity code that will compile successfully. Viper's ordering requirements are not a new thing. In fact, these ordering requirements have always been present in Python programming. The ordering required by Viper is straightforward and logical, as illustrated in this next example. #declare a variable called the bool, public, bool. #declare a function. This shows the correct ordering of functions and variables in a Viper smart contract. Note how the variable the bool and the function top function are declared before they are assigned a value and called, respectively. If the bool was declared below top function or if top function was declared below lower function, this contract would not compile. Compilation. Viper has its own online code editor and compiler, which allows you to write and then compile your smart contracts into bytecode, ABI, and LLL using only your web browser. The Viper online compiler has a variety of pre-written smart contracts for your convenience, including contracts for a simple open auction, safe remote purchases, UC20 tokens, and more. This tool offers only one version of the compilation software. It is updated regularly but does not always guarantee the latest version. Etherscan has an online Viper compiler which allows you to select the compiler version. Also Remix, originally designed for Solidity smart contracts, now has a Viper plugin available in the Settings tab. Viper implements UC20 as a precompiled contract, allowing these smart contracts to be easily used out of the box. Contracts in Viper must be declared as global variables. An example for declaring the UC20 variable is as follows. You can also compile a contract using the command line. Each Viper contract is saved in a single file with the .vy extension. Once installed, you can compile a contract with Viper by running the following command. The human-readable ABI description, in JSON format, can then be obtained by running the following command. Protecting against overflow errors at the compiler level. Overflow errors in software can be catastrophic when dealing with real value. For example, one transaction from mid-April 2018 shows the malicious transfer of over 57,896,044,618,6. This transaction was the result of an integer overflow issue in BeautyChain's UC20 token contract, becktoken.sol. Solidity developers do have access to libraries like SafeMath as well as Ethereum smart contract security analysis tools like Mithril OSS. However, developers are not forced to use the safety tools. Put simply, if safety is not enforced by the language, developers can write unsafe code that will successfully compile and later on successfully execute. Viper has built-in overflow protection, implemented in a two-pronged approach. Firstly, Viper provides a SafeMath equivalent that includes the necessary exception cases for integer arithmetic. Secondly, Viper uses clamps whenever a literal constant is loaded, a value is passed to a function, or a variable is assigned. Clamps are implemented via custom functions in the low-level Lisp-like language, LLL, compiler, and cannot be disabled. The Viper compiler outputs LLL rather than EVM bytecode. This simplifies the development of Viper itself. Reading and writing data. While it is costly to store, read, and modify data, these storage operations are a necessary component of most smart contracts. Smart contracts can write data to two places. Global state. The state variables in a given smart contract are stored in Ethereum's global state tree. A smart contract can only store, read, and modify data in relation to that particular contract's address, i.e., smart contracts cannot read or write to other smart contracts. Logs. A smart contract can also write to Ethereum's chain data through log events. While Viper initially employed the log syntax for declaring these events, an update has been made that brings its event declaration more in line with Solidity's original syntax. For example, Viper's declaration of an event called mylog was originally mylog, log, arg1, indexed, bytes 3. The syntax has now become mylog, event, arg1, indexed, bytes 3. It is important to note that the execution of the log event in Viper was, and still is, as follows, log.mylog, 123. While smart contracts can write to Ethereum's chain data, through log events, they are unable to read the on-chain log events they've created. Notwithstanding, one of the advantages of writing to Ethereum's chain data via log events is that logs can be discovered and read, on the public chain, by light clients. For example, the log's bloom value in a mined block can indicate whether or not a log event is present. Once the existence of log events has been established, the log data can be obtained from a given transaction receipt. Conclusions. Viper is a powerful and interesting new contract-oriented programming language. Its design is biased toward correctness, at the expense of some flexibility. This may allow programmers to write better smart contracts and avoid certain pitfalls that cause serious vulnerabilities to arise. Next, we will look at smart contract security in more detail. Some of the nuances of Viper design may become more apparent once you read about all the possible security problems that can arise in smart contracts.
I think that Viper is analogous to Python and Solidity is analogous to JavaScript. And it's interesting, the order of functions is kind of like similar to the way that JavaScript is, where it doesn't matter really much where you declare the functions because of hoisting. So I think in Solidity is pretty much the same thing based on the example they give here, but on Viper it's more like Python where the order matters. Really interesting. And it's also interesting that Solidity is the one that is used the most in the blockchain. So it probably has to do with the nature of the thing, but at the same time, it means that there's probably other applications that will allow to use more Viper or other languages like that, in the same way that JavaScript is more used in the browser, but then Python is more used for machine learning. So for the thing that I'm trying to do, which is to combine both artificial intelligence and blockchain, there might be something there that connects both of them and that uses Viper more, but I'm not really sure if that makes any sense, this analogy. But I think it is similar, but not sure for me specifically if it's does it has any difference. Because right now I'm more interested on the fundamentals and not so much on the languages. Because I want to study other protocols as well. I think the most interesting chapter is probably going to be this last two here, the Ethereum virtual machine and the consensus. Because they're probably going to have stuff related to the stuff that I'm trying to clarify here about the RPC and the mempool, how it works. Same thing is happening again. I think in some pages it can't parse the thing correctly. I think I'm not gonna read this one, actually. Just gonna skip this. It's talking about the hacks. So, and I already studied the hacks. Will be good to read, but I think I'll read it another time. The other stuff has more priority to me. Yeah, whatever. Maybe I should just jump to the ones that I think that are going to be more interesting. I'm already really tired, so I think I'm just gonna read this stuff. I think I'm gonna try to close at 6 hours. I've been here for 4 hours and around 40 minutes. I want to stay for 6 hours today. Yeah, it looks like this one will be interesting to read, but I'll probably read it later. Maybe I should study the source code. But I think that's the source code is one of those things where it's probably better to start with this, because then I'm gonna have a lot more energy and can pay attention more. I should try to understand how everything works. I need to have a clear understanding of what I'm trying to figure out here with the code, which I kind of already do, but it would be better if I clarify as much as possible before trying to understand exactly what I'm trying to achieve here. Maybe I should come up with something that I can do, like something I can build or something like that. I think that might be better. But then I have to think about like what sort of application would be good to, like, obviously I don't want to build something big now. I just like it would be just building something for the sake of understanding the connection. And the problem is that I don't have the node is not working yet, so but maybe there is something I can try to do, like using Web3 library. The problem is that if I go with the route that I'm thinking about for building something, then I know that I'm not gonna learn much, because you can just use the libraries and then maybe reading the source code of the libraries, Web3, Python, and the other ones to understand how they connect. Maybe that's a good idea. Or studying Lighthouse as well, the source code of Lighthouse. That might be. Yeah, but then I think that is pretty much the same thing as studying this one here, so it doesn't make a lot of sense. I have to remember which articles I read a long time ago about the MetaMask. I have to find those articles, but I think I will do that off stream, because there were several different articles that I read about the MetaMask and the connection of MetaMask with and Flashbots. Maybe Flashbots is a good starting point to find those articles. But just those articles alone is not going to be enough to understand what I'm trying to understand, I think. Yeah, I think I need to focus on the AVM, so there's no point in... And I can't think of anything that I can build that is gonna allow me to understand more. I have to understand first the code, then once I understand the code more, then I can think about... Maybe I can think about something that I can do directly, like calling these functions here from the node or something like that. And maybe it would be better to start with the Python implementation because I'm much more familiar with Python than with Go. I never used Go for anything. I'm not really sure if it makes any difference. I think I'll see the EVM chapter. Then tomorrow probably I'll look into this through here. I think I'm gonna reread the first ones as well to understand more another time, maybe tomorrow off stream. Decentralized applications. And then after I read these chapters, then I can look at the source code. I think they're, yeah, depending on how big they are. Because there is 1 hour and 20 minutes to close, 6 hours.
The Ethereum virtual machine.
Yeah, if they are short, then maybe I'll start studying the code right after I finish this. I also have to study this lipped cryptography thing, the curve here. But I think before I start studying this stuff, I'm probably gonna maybe I'll copy this stuff here. I think that's a good idea, because then I will remember. Actually, it needs to be here. And yeah, I should probably make an article about this. I'm gonna focus on this one first. So after I clarify the whole thing about the miners, the mempool, how it works, and I study the source code, then I think I'm gonna finish this article here, and then I'm gonna start working on this proposer builder thing, just to understand what is the difference between the way that it was back then and the way that it is now.
At the heart of the Ethereum protocol in operation is the Ethereum virtual machine, or EVM for short. As you might guess from the name, it is a computation engine, not hugely dissimilar to the virtual machines of Microsoft's .NET framework, or interpreters of other bytecode-compiled programming languages such as Java. In this chapter we take a detailed look at the EVM, including its instruction set, structure, and operation, within the context of Ethereum state updates. What is the EVM? The EVM is the part of Ethereum that handles smart contract deployment and execution. Simple value transfer transactions from one EOA to another don't need to involve it, practically speaking, but everything else will involve a state update computed by the EVM. At a high level, the EVM running on the Ethereum blockchain can be thought of as a global decentralized computer containing millions of executable objects, each with its own permanent data store. The EVM is a quasi-Turing. The EVM has a stack-based architecture, storing all The EVM has a stack-based architecture, storing all in-memory values on a stack. It works with a word size of 256 bits, mainly to facilitate native hashing and elliptic curve operations, and has several addressable data components. There is also a set of
You go grab back.
There is also a set of environment variables in data that is available during execution. We will go through these in more detail later in this chapter. The Ethereum Virtual Machine, EVM, architecture and execution context shows the EVM architecture and execution context. Compare
I'm just gonna spend some time so I understand here. I was thinking about it, whether or not it's worth it to go over the source code here and try to translate at least write the names of the functions on SkyLiDraw to see if I can capture the connection between them to make it easier to understand. Not really sure if it makes sense or not. I think I'm gonna study I'm gonna reread the articles here again tomorrow, but I'm gonna read one before streaming. I think probably the cryptography one, and then the other one after streaming. Because otherwise I'm gonna be too tired already to do like obviously I won't be tired if I read both of them before, but it's gonna be worse. Like I'd rather be as rested as possible. I'm not sure if rested is a word or not, but you get what I'm saying. Don't understand why here, if it's a no, it reverses the transaction.
comparison with existing technology. The term virtual machine is often applied to the virtualization of a real computer, typically by a hypervisor such as VirtualBox or QEMU, or of an entire operating system instance, such as Linux's KVM. These must provide a software abstraction, respectively, of actual hardware, and of system calls and other kernel functionality. The EVM operates in a much more limited domain. It is just a computation engine, and as such provides an abstraction of just computation and storage, similar to the Java Virtual Machine, JVM, specification, for example. From a high-level viewpoint, the JVM is designed to provide a runtime environment that is agnostic of the underlying host OS or hardware, enabling compatibility across a wide variety of systems. High-level programming languages such as Java or Scala, which use the JVM, or C#, which uses .NET, are compiled into the bytecode instruction set of their respective virtual machine. In the same way, the EVM executes its own bytecode instruction set, described in the next section, which higher-level smart contract programming languages such as LLL, Serpent, Mutant, or Solidity are compiled into. The EVM, therefore, has no scheduling capability, because execution ordering is organized externally to it. Ethereum clients run through verified block transactions to determine which smart contracts need executing and in which order. In this sense, the Ethereum world computer is single-threaded, like JavaScript. Neither does the EVM have any system interface, handling or hardware support. There is no physical machine to interface with. The Ethereum world computer is completely virtual. The EVM instruction set, bytecode operations. In addition to the typical bytecode operations, the EVM also In addition to the typical bytecode operations, the EVM also has access to account information, example address and balance, and block information, example block number, and current gas price. Let's start our exploration of the EVM in more detail by looking at the available opcodes and what they do. As you might expect, all operands are taken from the stack, and the result, where applicable, is often put back on the top of the stack. Arithmetic operations. Arithmetic opcode instructions. Add // add the top 2 stack items mul // multiply the top 2 stack items sub / subtract the top 2 stack items div / integer division sdiv / signed integer division mod / modulo, remainder. Note that all arithmetic is performed modulo 2, unless otherwise noted, and that the zeroth power of 0, 0, is taken to be 1. Stack operations. Stack, memory, and storage management instructions. Pop / remove the top item from the stack load / load a word from memory mistore / save a word to memory mistore 8 / save a byte to memory slowed / load a word from storage store / save a word to storage misize / get the size of the active memory in bytes pushx / place x byte item on the stack, where x can be any integer from / 1 to 32, full word, inclusive dupx / duplicate the xth stack item, where x can be any integer from process flow operations. Instructions for control flow. Stop / halt execution jump / set the program counter to any value jump p / conditionally alter the program counter pc / get the value of the program counter prior to the increment / corresponding to system operations. Opcodes for the system executing the program. Logx / append a log record with x topics, where x is any integer / from 0 to 4 inclusive create / create a new account with associated code call / message call into another account. I.e. run another / accounts code call code / message call into this account with another / accounts code return / halt execution and return output data delegate call / message call into this account. With an alternative / accounts code, but persisting the current values for / sender and value static call / static message call into an account. Logic operations. Opcodes for comparisons in bitwise logic. LT / less than comparison GT. Environmental operations. Opcodes dealing with execution environment information. Gas / get the amount of available gas, after the reduction for / this instruction. Address / get the address of the currently executing account balance / get the account balance of any given account. Origin / get the address of the EOA that initiated this EVM / execution caller / get the address of the caller immediately responsible / for this execution call value / get the ether amount deposited by the caller responsible / for this execution call data load / get the input data sent by the caller responsible for / this execution call data size / get the size of the input data call data copy / copy the input data to memory code size / get the size of code running in the current environment code copy / copy the code running in the current environment to / memory gas price / get the gas price specified by the originating / transaction x code size / get the size. Block operations. Opcodes for accessing information on the current block. Block hash / get the hash of one of the 256 most recently completed / blocks Coinbase / get the block's beneficiary address for the block reward timestamp / get the block's timestamp number / get the Ethereum state. The job of the EVM is to update the Ethereum state by computing valid state transitions as a result of smart contract code execution, as defined by the Ethereum protocol. This aspect leads to the description of Ethereum as a transaction-based state machine, which reflects the fact that external actors, i.e., account holders and miners, initiate state transitions by creating, accepting, and ordering transactions. It is useful at this point to consider what constitutes the Ethereum state. At the top level, we have the Ethereum world state. The world state is a mapping of Ethereum addresses, 160-bit values, to accounts. At the lower level, each Ethereum address represents an account comprising an ether balance, stored as the number of way owned by the account. A nonce, representing the number of transactions successfully sent from this account if it is an EOA, or the number of contracts created by it if it is a contract account. The account's storage, which is a permanent data store, only used by smart contracts, and the account's program code, again, only if the account is a smart contract account. An EOA will always have no code and an empty storage. When a transaction results in smart contract code execution, an EVM is instantiated with all the information required in relation to the current block being created and the specific transaction being processed. In particular, the EVM's program code ROM is loaded with the code of the contract account being called, the program counter is set to 0, the storage is loaded from the contract account's storage. The memory is set to all zeros, and all the block and environment variables are set. A key variable is the gas supply for this execution, which is set to the amount of gas paid for by the sender at the start of the transaction. See gas for more details. As code execution progresses, the gas supply is reduced according to the gas cost of the operations executed. If at any point the gas supply is reduced to 0, we get an out of gas, OOG, exception, execution immediately halts and the transaction is abandoned. No changes to the Ethereum state are applied, except for the sender's nonce being incremented and their ether balance going down to pay the block's beneficiary for the resources used to execute the code to the halting point. At this point, you can think of the EVM running on a sandboxed copy of the Ethereum world state, with this sandboxed version being discarded completely if execution cannot complete for whatever reason. However, if execution does complete successfully, then the real-world state is updated to match the sandboxed version, including any changes to the called contract storage data, any new contracts created, and any Ether balance transfers that were initiated. Note that because a smart contract can itself effectively initiate transactions, code execution is a recursive process. A contract can call other contracts, with each call resulting in another EVM being instantiated around the new target of the call. Each instantiation has its sandbox world state initialized from the sandbox of the EVM at the level above. Each instantiation is also given a specified amount of gas for its gas supply, not exceeding the amount of gas remaining in the level above, of course. And so may itself halt with an exception due to being given too little gas to complete its execution. Again, in such cases, the sandbox state is discarded, and execution returns to the EVM at the level above. Compiling Solidity to EVM bytecode. Compiling a Solidity source file to EVM bytecode can be accomplished via several methods. In intro chapter we used the online remix compiler. In this chapter, we will use the Solc executable at the command line. For a list of options, run the following command. Generating the raw code stream of a Solidity source file is easily achieved with the code's command line option. This code stream leaves out some information. The ASM option produces the full information, but it is sufficient for this discussion. For example, compiling an example Solidity file, example.sol, and sending the code output into a directory named bytecode.dir is accomplished with the following command. The output of code files generated will depend on the specific contracts contained within the Solidity source file. Our simple Solidity file example.sol has only one contract, named example. Pragma Solidity 0.4.19, contract example address contract owner, function example, contract owner equals message sender. As you can see, all this contract does is hold one persistent state variable, which is set as the address of the last account to run this contract. If you look in the bytecode.dir directory you will see the upcode file example.upcode, which contains the EVM upcode instructions of the example contract. Opening the example.upcode file in a text editor will show the following. Push 10x60 push 1. Compiling the example with the ASM option produces a file named example.ev in our bytecode.dir directory. This contains a slightly higher level description of the EVM bytecode instructions, together with some helpful annotations. / example.sol 26:132 contract example /mistor 0x40 0x60 / example.sol 74:130 function example /jumpy tag 1 is0 call value 0x0.1 revert tag 1 / example.sol 115 125 message sender /caller example.sol 99:112 contract owner /0x0.1 example.sol 99 125 contract owner equals message sender /0x100 exp.2 slowed.20x. You can investigate what's going on here in detail using the upcode list given in the EVM instruction set, bytecode operations. However, that's quite a task, so let's just start by examining the first 4 instructions. Here we have push 1 followed by a raw byte of value 0x60. This EVM instruction takes the single byte following the upcode in the program code, as a literal value, and pushes it onto the stack. It is possible to push values of size up to 32 bytes onto the stack, as in. The second push 1 upcode from example.upcode stores 0x40 onto the top of the stack, pushing the 0x60 already present there down 1 slot. Next is misstore, which is a memory store operation that saves a value to the EVM's memory. It takes 2 arguments and, like most EVM operations, obtains them from the stack. For each argument the stack is popped, i.e., the top value on the stack is taken off and all the other values on the stack are shifted up 1 position. The first argument for misstore is the address of the word in memory where the value to be saved will be put. For this program we have 0x40 at the top of the stack, so that is removed from the stack and used as the memory address. The second argument is the value to be saved, which is 0x60 here. After the misstore operation is executed our stack is empty again, but we have the value 0x60, 96 in decimal, at the memory location 0x40. The next upcode is call value, which is an environmental upcode that pushes onto the top of the stack the amount of ether, measured in way, sent with the message call that initiated this execution. We could continue to step through this program in this way until we had a full understanding of the low-level state changes that this code affects, but it wouldn't help us at this stage. We'll come back to it later in the chapter. Contract deployment code. There is an important but subtle difference between the code used when creating and deploying a new contract on the Ethereum platform and the code of the contract itself. In order to create a new contract, a special transaction is needed that has its to field set to the special 0x0 address and its data field set to the contract's initiation code. When such a contract creation transaction is processed, the code for the new contract account is not the code in the data field of the transaction. Instead, an EVM is instantiated with the code in the data field of the transaction loaded into its program code ROM, and then the output of the execution of that deployment code is taken as the code for the new contract account. This is so that new contracts can be programmatically initialized using the Ethereum world state at the time of deployment, setting values in the contract storage and even sending ether or creating further new contracts. When compiling a contract offline, example using Solc on the command line, you can either get the deployment bytecode or the runtime bytecode. The deployment bytecode is used for every aspect of the initialization of a new contract account, including the bytecode that will actually end up being executed when transactions call this new contract, i.e. the runtime bytecode, and the code to initialize everything based on the contract's constructor. The runtime bytecode, on the other hand, is exactly the bytecode that ends up being executed when the new contract is called, and nothing more. It does not include the bytecode needed to initialize the contract during deployment. / version of Solidity compiler. This program was written for Pragma Solidity 0.4.19 / our first contract is a faucet. To get the deployment bytecode, we would run solc bin faucet.sol. If we instead wanted just the runtime bytecode, we would run solc bin runtime faucet.sol. If you compare the output of these commands, you will see that the runtime bytecode is a subset of the deployment bytecode. In other words, the runtime bytecode is entirely contained within the deployment bytecode. Disassembling the bytecode. Disassembling EVM bytecode is a great way to understand how high-level Solidity acts in the EVM. There are a few disassemblers you can use to do this. In this section, we will be using the Ethers Play plugin for binary.
That's crazy. So he reached the same conclusion that I did. Maybe it is a waste of time, sure. But I think that it isn't a waste of time for me because he probably knew a lot more than I do. So I think it is worth it for me to understand like the fundamentals. But I agree with this position, I think. But I think he reached these conclusions for other reasons, probably. Because my reasoning for Ethereum not being... I think that Ethereum is not going to be the main blockchain in the future. But it's more for a macro perspective. Not so much from the technical aspect. He's probably saying from the technical aspect. Obviously, like this is nothing against people that build Ethereum or things like obviously these people are very intelligent. But I just think that from what I think about the conclusions I have about the macro and the macroeconomics and things like that, I think that it doesn't make a lot of sense. Like I don't see how it will be feasible for Ethereum to work in the future. But I don't know like how the other protocols look like. So it's kind of hard to say as well. So maybe I shouldn't go too deep into this stuff here. I should focus more on the fundamental. Like I want to understand exactly what it makes it work. So the peer-to-peer, the hash functions, like the whole process of building the AVM, and how the other protocols work as well. I think it's gonna be fundamental to all of them to have some form of networking and some form of consensus. I think those are the two pillars. That's what makes the blockchain. So is the network, the consensus, and the history of the transactions, which can go into consensus. And then obviously the wallet providers and the accounts.
In this section, we will be using the Ethers Play plugin for Binary Ninja and to start disassembling the Faucet runtime bytecode. After getting the runtime bytecode of faucet.sol, we can feed it into Binary Ninja, after loading the Ethers Play plugin, to see what the EVM instructions look like. When you send a transaction to an ABI-compatible smart contract, which you can assume all contracts are, the transaction first interacts with that smart contract's dispatcher. The dispatcher reads in the data field of the transaction and sends the relevant part to the appropriate function. We can see an example of a dispatcher at the beginning of our disassembled faucet.sol runtime bytecode. After the familiar mistore instruction, we see the following instructions. As we have seen, push 10x4 places 0x4 onto the top of the stack, which is otherwise empty. Call data size gets the size in bytes of the data sent with the transaction, known as the call data, and pushes that number onto the stack. After these operations have been executed, the stack looks like this. This next instruction is LT, short for less than. The LT instruction checks whether the top item on the stack is less than the next item on the stack. In our case, it checks to see if the result of call data size is less than 4 bytes. Why does the EVM check to see that the call data of the transaction is at least 4 bytes?
I'm still not sure whether or not I'll go back to working on the bot, the trading bot. So that's one of the reasons why I'm debating whether or not to study this further. As part of me thinks that it is possible to make money, and it might be worth it to go back into it, because I was almost at the point where I was going to start testing things and sending transactions and things like that. But the issue with that is that it might be a very risky thing to do, because the problem with that is that I don't know how competitive it is. I know that it is extremely competitive, and I also know that it's a zero-sum game, and that there is a lifetime to it where eventually it's going to reach a Nash where it's going to become impossible to make money. There's still obviously going to be a lot of different opportunities, I think, always, because there's always going to be new protocols coming up and different opportunities like that, but it's going to become harder and harder, so that there are diminishing returns and it's a lot of effort and a lot of risk as well. So those are the reasons why I'm not really sure if I continue that route or not. But for something like that, I think these kind of tools would be really useful, because you can get transactions from other people, and there are ways to know what are the bots that are doing the trades, and then you can get their transactions and you can decompile the contract with the code. So that's the reason why I'm forking this, in case I want to use it later. And this one is in Python as well, so it's probably gonna be easier for me to use if I want to. I'll probably not end up using it. I think it's more it's a better strategy to focus on something that is positive sum and that can have it has less risk and is also less competitive because it's creative. But I could be wrong about that. I think I'm gonna close this stuff. Maybe in the future I'll look into it. And this one as well, I was thinking about whether or not to use this code. I remember searching a lot, and then I also tried multiple different ways, but I was having problems sending the transactions and signing and things like that because the libraries don't work.
Why does the EVM check to see that the call data of the transaction is at least 4 bytes? Because of how function identifiers work. Each function is identified by the first 4 bytes of its cupcake256 hash. By placing the function's name and what arguments it takes into a cupcake256 hash function, we can deduce its function identifier. In our case, we have. Thus, the function identifier for the withdraw, UN256, function is 0x2E17D4D, since these are the first 4 bytes of the resulting hash. A function identifier is always 4 bytes long, so if the entire data field of the transaction sent to the contract is less than 4 bytes, then there's no function with which the transaction could possibly be communicating, unless a fallback function is defined. Because we implemented such a fallback function in faucet.sol, the EVM jumps to this function when the call data's length is less than 4 bytes. LT pops the top 2 values off the stack and, if the transaction's data field is less than 4 bytes, pushes 1 onto it. Otherwise, it pushes 0. In our example, let's assume the data field of the transaction sent to our contract was less than 4 bytes. The push 10x3f instruction pushes the byte 0x3f onto the stack. After this instruction, the stack looks like this. In our case, label is 0x3f, which is where our fallback function lives in our smart contract. The condominium argument is 1, which was the result of the LT instruction earlier. To put this entire sequence into words, the contract jumps to the fallback function if the transaction data is less than 4 bytes. At 0x3f, only a stop instruction follows, because although we declared a fallback function, we kept it empty. As you can see in jumpy instruction leading to fallback function, had we not implemented a fallback function, the contract would throw an exception instead. Let's examine the central block of the dispatcher. Assuming we received call data that was greater than 4 bytes in length, the jumpy instruction would not jump to the fallback function. Instead, code execution would proceed to the following instructions. Push 10x0 call data load push 29x0 push 10x0 pushes 0 onto the stack, which is now otherwise empty again. Call data load accepts as an argument an index within the call data sent to the smart contract and reads 32 bytes from that index, like so. Since 0 was the index passed to it from the push 10x0 command, call data load reads 32 bytes of call data starting at byte 0, and then pushes it to the top of the stack, after popping the original 0x0. After the push 29x0x100000 instruction, the stack is then. Swap 1 switches the top element on the stack with the ith element after it. In this case, it swaps 0x10000000 with the call data. The new stack is. In this case, x equals 32 bytes of call data starting at byte 0, and y equals 0x10000000. 29 bytes total. Can you think of why the dispatcher is doing the division? Here's a hint. We read 32 bytes from call data earlier, starting at index 0. The first 4 bytes of that call data is the function identifier. The 0x10000000 we pushed earlier is 29 bytes long, consisting of a 1 at the beginning, followed by all zeros. Dividing our 32 bytes of call data by this value will leave us only the topmost 4 bytes of our call data load, starting at index 0. These 4 bytes, the first 4 bytes in the call data starting at index 0 are the function identifier, and this is how the EVM extracts that field. If this part isn't clear to you, think of it like this. In base 10, 1234000/1000 equals 1234. In base 16, this is no different. Instead of every place being a multiple of 10, it is a multiple of 16. Just as dividing by 10, 1000, in our smaller example kept only the topmost digits, dividing our 32-byte base 16 value by 16 does the same. Since the push 40xffffffff and instructions are redundant, we can ignore them entirely, as the stack will remain the same after they are done. The DUP1 instruction duplicates the first item on the stack, which is the function identifier. The next instruction, push 40x2e17d4d, pushes the per-calculated function identifier of the withdraw, uint256, function onto the stack. The stack is now. The next instruction, EQ, pops off the top 2 items of the stack and compares them. This is where the dispatcher does its main job. It compares whether the function identifier sent in the message data field of the transaction matches that of withdraw, uint256. If they are equal, EQ pushes 1 onto the stack, which will ultimately be used to jump to the withdraw function. Otherwise, EQ pushes 0 onto the stack. Assuming the transaction sent to our contract indeed began with the function identifier for withdraw, uint256, our stack has become. Next, we have push 10x41, which is the address at which the withdraw, uint256, function lives in the contract. After this instruction, the stack looks like this. The jumpy instruction is next, and it once again accepts the top 2 elements on the stack as arguments. In this case, we have jumpy, 0x41, 1, which tells the EVM to execute the jump to the location of the withdraw, uint256, function, and the execution of that function's code can proceed. Turing completeness and guess. As we have already touched on, in simple terms, a system or programming language is Turing complete if it can run any program. This capability, however, comes with a very important caveat: some programs take forever to run. An important aspect of this is that we can't tell, just by looking at a program, whether it will take forever or not to execute. We have to actually go through with the execution of the program and wait for it to finish to find out. Of course, if it is going to take forever to execute, we will have to wait forever to find out. This is called the halting problem and would be a huge problem for Ethereum if it were not addressed. Because of the halting problem, the Ethereum world computer is at risk of being asked to execute a program that never stops. This could be by accident or malice. We have discussed that Ethereum acts like a single-threaded machine, without any scheduler, and so if it became stuck in an infinite loop, this would mean it would become unusable. However, with gas, there is a solution. If after a pre-specified maximum amount of computation has been performed, the execution hasn't ended, the execution of the program is halted by the EVM. This makes the EVM a quasi-Turing. Gas. Gas is Ethereum's unit for measuring the Gas is Ethereum's unit for measuring the computational and storage resources required to perform actions on the Ethereum blockchain. In contrast to Bitcoin, whose transaction fees only take into account the size of a transaction in kilobytes, Ethereum must account for every computational step performed by transactions in smart contract code execution. Each operation performed by a transaction or contract costs a fixed amount of gas. Some examples, from the Ethereum yellow paper. Gas is a crucial component of Ethereum, and serves a dual role, as a buffer between the volatile price of Ethereum and the reward to miners for the work they do, and as a defense against denial-of-service attacks. To prevent accidental or malicious infinite loops or other computational wastage in the network, the initiator of each transaction is required to set a limit to the amount of computation they are willing to pay for. The gas system thereby disincentivizes attackers from sending spam transactions, as they must pay proportionately for the computational, bandwidth, and storage resources that they consume. Gas accounting during execution. When an EVM is needed to complete a transaction, in the first instance it is given a gas supply equal to the amount specified by the gas limit in the transaction. Every opcode that is executed has a cost in gas, and so the EVM's gas supply is reduced as the EVM steps through the program. Before each operation, the EVM checks that there is enough gas to pay for the operation's execution. If there isn't enough gas, execution is halted and the transaction is reverted. If the EVM reaches the end of execution successfully, without running out of gas, the gas cost used is paid to the miner as a transaction fee, converted to Ether based on the gas price specified in the transaction. The gas remaining in the gas supply is refunded to the sender, again converted to Ether based on the gas price specified in the transaction. If the transaction runs out of gas during execution, the operation is immediately terminated, raising an out-of-gas exception. The transaction is reverted and all changes to the state are rolled back. Although the transaction was unsuccessful, the sender will be charged a transaction fee, as miners have already performed the computational work up to that point and must be compensated for doing so. Gas accounting considerations. The relative gas costs of the various operations that can be performed by the EVM have been carefully chosen to best protect the Ethereum blockchain from attack. You can see a detailed table of gas costs for different EVM opcodes and EVM opcodes table. More computationally intensive operations cost more gas. For example, executing the SHA-3 function is 10 times more expensive, 30 gas, than the add operation, 3 gas. More importantly, some operations, such as EXP, require an additional payment based on the size of the operand. There is also a gas cost to using EVM memory and for storing data in a contract's on-chain storage. The importance of matching gas cost to the real-world cost of resources was demonstrated in 2016 when an attacker found and exploited a mismatch in costs. The attack generated transactions that were very computationally expensive, and made the Ethereum mainnet almost grind to a halt. This mismatch was resolved by a hard fork, codenamed Tangerine Whistle, that tweaked the relative gas costs. Gas cost versus gas price. While the gas cost is a measure of computation and storage used in the EVM, the gas itself also has a price measured in Ether. When performing a transaction, the sender specifies the gas price they are willing to pay, in Ether, for each unit of gas, allowing the market to decide the relationship between the price of Ether and the cost of computing operations, as measured in gas. When constructing a new block, miners on the Ethereum network can choose among pending transactions by selecting those that offer to pay a higher gas price. Offering a higher gas price will therefore incentivize miners to include your transaction and get it confirmed faster. In practice, the sender of a transaction will set a gas limit that is higher than or equal to the amount of gas expected to be used. If the gas limit is set higher than the amount of gas consumed, the sender will receive a refund of the excess amount, as miners are only compensated for the work they actually perform. Gas cost is the number of units of gas required to perform a particular operation. Gas price is the amount of Ether you are willing to pay per unit of gas when you send your transaction to the Ethereum network. While gas has a price, it cannot be owned nor spent. Gas exists only inside the EVM, as a count of how much computational work is being performed. The sender is charged a transaction fee in Ether, which is then converted to gas for EVM accounting and then back to Ether as a transaction fee paid to the miners. Negative gas costs. Ethereum encourages the deletion of used storage variables in accounts by refunding some of the gas used during contract execution. Deleting a contract, self-destruct, is worth a refund of 24,000 gas. Changing a storage address from a non-zero value to 0, store x equals 0, is worth a refund of 15,000 gas. To avoid exploitation of the refund mechanism, the maximum refund for a transaction is set to half the total amount of gas used, rounded down. Block gas limit. The block gas limit is the maximum amount of gas that may be consumed by all the transactions in a block, and constrains how many transactions can fit into a block. For example, let's say we have 5 transactions whose gas limits have been set to 30,000, 30,000, 40,000, 50,000, and 50,000. If the block gas limit is 180,000, then any 4 of those transactions can fit in a block, while the 5th will have to wait for a future block. As previously discussed, miners decide which transactions to include in a block. Different miners are likely to select different combinations, mainly because they receive transactions from the network in a different order. If a miner tries to include a transaction that requires more gas than the current block gas limit, the block will be rejected by the network. Most Ethereum clients will stop you from issuing such a transaction by giving a warning along the lines of, transaction exceeds block gas limit. The block gas limit on the Ethereum mainnet is 8 million gas at the time of writing according to https://etherskin.io, meaning that around 380 basic transactions, each consuming 21,000 gas, could fit into a block. Who decides what the block gas limit is? The miners on the network collectively decide the block gas limit. Individuals who want to mine on the Ethereum network use a mining program, such as Ethminer, which connects to a Geth or parity Ethereum client. The Ethereum protocol has a built-in mechanism where miners can vote on the gas limit so capacity can be increased or decreased in subsequent blocks. The miner of a block can vote to adjust the block gas limit by a factor of 1/1,024, 0.0976%, in either direction. The result of this is an adjustable block size based on the needs of the network at the time. This mechanism is coupled with a default mining strategy where miners vote on a gas limit that is at least 4.7 million gas, but which targets a value of 150% of the average of recent total gas usage per block, using a 1024 block exponential moving average. Conclusions. In this chapter we have explored the Ethereum virtual machine, tracing the execution of various smart contracts and looking at how the EVM executes bytecode. We also looked at gas, the EVM's accounting mechanism, and saw how it solves the halting problem and protects Ethereum from denial of service attacks. Next, in consensus, we will look at the mechanism used by Ethereum to achieve decentralized consensus.
Looks like this only works on Mac and Ubuntu, which is a problem for me. Whatever. And it looks like this doesn't say anything about the whole mempool thing, peer-to-peer. Hopefully the consensus does talk about it.
Consensus. Throughout this book we have talked about consensus rules, the rules that everyone must agree to for the system to operate in a decentralized, yet deterministic, manner. In computer science, the term consensus predates blockchains and is related to the broader problem of synchronizing state in distributed systems, such that different participants in a distributed system all, eventually, agree on a single system-wide state. This is called reaching consensus. When it comes to the core function of decentralized record keeping and verification, it can become problematic to rely on trust alone to ensure that information derived from state updates is correct. This rather general challenge is particularly pronounced in decentralized networks because there is no central entity to decide what is true. The lack of a central decision-making entity is one of the main attractions of blockchain platforms, because of the resulting capacity to resist censorship and the lack of dependence on authority for permission to access information. However, these benefits come at a cost. Without a trusted arbitrator, any disagreements, deceptions, or differences need to be reconciled using other means. Consensus algorithms are the mechanism used to reconcile security and decentralization. In blockchains, consensus is a critical property of the system. Simply put, there is money at stake. So, in the context of blockchains, consensus is about being able to arrive at a common state, while maintaining decentralization. In other words, consensus is intended to produce a system of strict rules without rulers. There is no one person, organization, or group in charge. Rather, power and control are diffused across a broad network of participants, whose self-interest is served by following the rules and behaving honestly. The ability to come to consensus across a distributed network, under adversarial conditions, without centralizing control is the core principle of all open public blockchains. To address this challenge and maintain the valued property of decentralization, the community continues to experiment with different models of consensus. This chapter explores these consensus models and their expected impact on smart contract blockchains such as Ethereum. While consensus algorithms are an important part of how blockchains work, they operate at a foundational layer, far below the abstraction of smart contracts. In other words, most of the details of consensus are hidden from the writers of smart contracts. You don't need to know how they work to use Ethereum, any more than you need to know how routing works to use the internet. Consensus via proof of work. The creator of the original blockchain, Bitcoin, invented a consensus algorithm called proof of work, POW. Arguably, POW is the most important invention underpinning Bitcoin. The colloquial term for POW is mining, which creates a misunderstanding about the primary purpose of consensus. Often people assume that the purpose of mining is the creation of new currency, since the purpose of real-world mining is the extraction of precious metals or other resources. Rather, the real purpose of mining, and all other consensus models, is to secure the blockchain, while keeping control over the system decentralized and diffused across as many participants as possible. The reward of newly minted currency is an incentive to those who contribute to the security of the system, a means to an end. In that sense, the reward is the means and decentralized security is the end. In POW consensus there is also a corresponding punishment, which is the cost of energy required to participate in mining. If participants do not follow the rules and earn the reward, they risk the funds they have already spent on electricity to mine. Thus, POW consensus is a careful balance of risk and reward that drives participants to behave honestly out of self-interest. Ethereum is currently a POW blockchain, in that it uses a POW algorithm with the same basic incentive system for the same basic goal, securing the blockchain while decentralizing control. Ethereum's POW algorithm is slightly different than Bitcoin's and is called Ethish. We will examine the function and design characteristics of the algorithm in Ethish, Ethereum's proof-of-work algorithm. Ethereum also considers switching to POW, a more ASIC-resistant POW algorithm, which is still under development at the time of writing. Consensus via proof of stake, POS. Historically, proof of work was not the first consensus algorithm proposed. Preceding the introduction of proof of work, many researchers had proposed variations of consensus algorithms based on financial stake, now called proof of stake, POS. In some respects, proof of work was invented as an alternative to proof of stake. Following the success of Bitcoin, many blockchains have emulated proof of work. Yet the explosion of research into consensus algorithms has also resurrected proof of stake, significantly advancing the state of the technology. From the beginning, Ethereum's founders were hoping to eventually migrate its consensus algorithm to proof of stake. In fact, there is a deliberate handicap on Ethereum's proof of work called the difficulty bomb, intended to gradually make proof of work mining of Ethereum more and more difficult, thereby forcing the transition to proof of stake. At the time of publication of this book, Ethereum is still using proof of work, but the ongoing research toward a proof of stake alternative is nearing completion. Ethereum's planned POS algorithm is called Casper. The introduction of Casper as a replacement for Ethish has been postponed several times over the past 2 years, necessitating interventions to defuse the difficulty bomb and postpone its forced obsolescence of proof of work. In general, a POS algorithm works as follows. The blockchain keeps track of a set of validators, and anyone who holds the blockchain's base cryptocurrency, in Ethereum's case, Ether, can become a validator by sending a special type of transaction that locks up their Ether into a deposit. The validators take turns proposing and voting on the next valid block, and the weight of each validator's vote depends on the size of its deposit, i.e., stake. Importantly, a validator risks losing their deposit, i.e., being slashed, if the block they staked it on is rejected by the majority of validators. Conversely, validators earn a small reward, proportional to their deposited stake, for every block that is accepted by the majority. Thus, POS forces validators to act honestly and follow the consensus rules, by a system of reward and punishment. The major difference between POS and POW is that the punishment in POS is intrinsic to the blockchain, example loss of staked Ether, whereas in POW the punishment is extrinsic, example loss of funds spent on electricity. Ethish, Ethereum's proof-of-work algorithm. Ethish is the Ethereum POW algorithm. It uses an evolution of the Dagger, Hashimoto algorithm, which is a combination of Vitalik Buterin's Dagger algorithm and Thaddeus Dryge's Hashimoto algorithm. Ethish is dependent on the generation and analysis of a large dataset, known as a directed acyclic graph, or, more simply, the DAG. The DAG had an initial size of about 1 GB and will continue to slowly and linearly grow in size, being updated once every epoch, 30,000 blocks, or roughly 125 hours. The purpose of the DAG is to make the Ethish POW algorithm dependent on maintaining a large, frequently accessed data structure. This in turn is intended to make Ethish ASIC resistant, which means that it is more difficult to make application-specific integrated circuits, ASIC, mining equipment that is orders of magnitude faster than a fast graphics processing unit, GPU. Ethereum's founders wanted to avoid centralization in POW mining, where those with access to specialized silicon fabrication factories and big budgets could dominate the mining infrastructure and undermine the security of the consensus algorithm. Use of consumer-level GPUs for carrying out the POW on the Ethereum network means that more people around the world can participate in the mining process. The more independent miners there are, the more decentralized the mining power is, which means we can avoid a situation like in Bitcoin, where much of the mining power is concentrated in the hands of a few large industrial mining operations. The downside of the use of GPUs for mining is that it precipitated a worldwide shortage of GPUs in 2017, causing their price to skyrocket in an outcry from gamers. This led to purchase restrictions at retailers, limiting buyers to 1 or 2 GPUs per customer. Until recently, the threat of ASIC miners on the Ethereum network was largely non-existent. Using ASICs for Ethereum requires the design, manufacture, and distribution of highly customized hardware. Producing them requires considerable investment of time and money. The Ethereum developers' long expressed plans to move to a POS consensus algorithm likely kept ASIC suppliers away from targeting the Ethereum network for a long time. As soon as Ethereum moves to POS, ASICs designed for the POW algorithm will be rendered useless, that is, unless miners can use them to mine other cryptocurrencies instead. The latter possibility is now a reality with a range of other Ethish-based consensus coins available, such as PIRL and UBIC, and Ethereum Classic has pledged to remain a POW blockchain for the foreseeable future. This means that we will likely see ASIC mining begin to become a force on the Ethereum network while is it still operating on POW consensus. Casper, Ethereum's proof-of-stake algorithm. Casper is the proposed name for Ethereum's POS consensus algorithm. It is still under active research and development and is not implemented on the Ethereum blockchain at the time of publication of this book. Casper is being developed in 2 competing flavors. Initially, Casper FFG was proposed as a hybrid POW/POS algorithm to be implemented as a transition to a more permanent, pure POS algorithm. But in June 2018, Vitalik Buterin, who was leading the research work on Casper FFG, decided to scrap the hybrid model in favor of a pure POS algorithm. Now, Casper FFG and Casper CBC are both being developed in parallel. As Vitalik explains, the main trade-off between FFG and CBC is that CBC seems to have nicer theoretical properties, but FFG seems to be easier to implement. More information about Casper's history, ongoing research, and future plans can be found at the following links. Principles of consensus. The principles and assumptions of consensus algorithms can be more clearly understood by asking a few key questions. Consensus algorithms are evolving rapidly, attempting to answer these questions in increasingly innovative ways. Controversy and competition. At this point you might be wondering, why do we need so many different consensus algorithms? Which one works better? The answer to the latter question is at the center of the most exciting area of research in distributed systems of the past decade. It all boils down to what you consider better, which in the context of computer science is about assumptions, goals, and the unavoidable trade-offs. It is likely that no algorithm can optimize across all dimensions of the problem of decentralized consensus. When someone suggests that one consensus algorithm is better than the others, you should start asking questions that clarify, better at what? Immutability, finality, decentralization, cost? There is no clear answer to these questions, at least not yet. Furthermore, the design of consensus algorithms is at the center of a multi-billion-dollar industry and generates enormous controversy and heated arguments. In the end, there might not be a correct answer, just as there might be different answers for different applications. The entire blockchain industry is one giant experiment where these questions will be tested under adversarial conditions, with enormous monetary value at stake. In the end, history will answer the controversy. Conclusions. Ethereum's consensus algorithm is still in flux at the time of completion of this book. In a future edition, we will likely add more detail about Casper and other related technologies as these mature and are deployed on Ethereum. This chapter represents the end of our journey, completing mastering Ethereum. Additional reference material follows in the appendixes. Thank you for reading this book, and congratulations on reaching the end.
Yeah, so still doesn't explain the whole mempool thing. I think what I'm gonna do is search for this and then I'm gonna maybe read this stuff until I get to 6 hours. Just very close. The problem with researching is that it's really hard to... It's probably gonna be impossible to find. But like I said before, I wanna leave to study the source code for tomorrow. So for now, I'm just gonna study this. Just gonna research this. And I think I'm gonna read these ones off stream. But maybe I'll read them on stream tomorrow after I look at the source code. That doesn't have anything good here. Also, not gonna answer.
An in-depth guide into how the mempool works. The mempool stores transactions waiting to be validated by miners. To submit a transaction to the miners, nodes have to relay it to each other until it has propagated across the entire network. The mempool is the node's holding area for all the pending transactions. It is the node's collection of all the unconfirmed transactions it has already seen, enabling it to decide whether or not to relay a new transaction. There are as many mempools as there are as nodes. As the Bitcoin network is distributed, not all nodes receive the same transactions at the same time, so some nodes store more transactions than others at some time. Plus, everyone can run its own node with the hardware of his choice, so all nodes have a different RAM capacity to store unconfirmed transactions. As a result, each node has its own rendition of the pending transactions. This explains the variety of mempool sizes and transactions counts found on different sources. How do transactions get into the mempool? Before letting a transaction into its mempool, a node has to complete the series of checks listed below. Check syntactic correctness: make sure neither in or out lists are empty size in bytes. Must be in legal money range: make sure none of the inputs have hash equals 0, n equals -1. Coinbase transactions, check that n lock time equals 100. And SIGAP count. Or script pub key not matching the two usual forms: reject if we already have matching TX in the pool, or in a block in the main branch for each input. If the referenced output exists in any other TX in the pool, reject this transaction. For each input, look in the main branch and the transaction pool to find the referenced output transaction. If the output transaction is missing for any input, this will be an orphan transaction. Add to the orphan transactions, if a matching transaction is not in there already. For each input, if the referenced output transaction is Coinbase, i.e. only one input, with hash equals 0, n equals -1. It must have at least co-invest maturity, 100, confirmations, else reject this transaction for each input, if the referenced output does not exist, e.g. never existed or has already been spent. Reject this transaction using the referenced output transactions to get input values, check that each input value, as well as the sum, are in legal money range. Reject if the sum of input values. Empty block: verify the script pub key accepts for each input, reject if any are bad. Add to transaction pool, add to wallet if mine, relay transaction to peer S for each orphan transaction that uses this one as one of its inputs. Run all these steps, including this one, recursively on that orphan. If the transaction matches the above criteria, it is allowed into the mempool and the node starts broadcasting it. If it doesn't, the transaction is not rebroadcast by the node. How does a new block impact the mempool? When a node receives a new valid block, it removes all the transactions contained in this block from its mempool as well as the transactions that have conflicting inputs. This results in a sharp drop in the mempool size.
Not minor.
What happens when the node's memory get full? Unlike mining, there is no financial incentive for running a node. Therefore, the hardware dedicated to it tends to be limited.
But to me, minor extractable value makes more sense. Yeah, but I guess maximal makes sense as well. But I swear I heard it as minor extractable value. Where's the...
Therefore, the hardware dedicated to it tends to be limited, and so a node's mempool often max out its RAM. When this happened, in former versions of Bitcoin, the node would just crash and restart with an empty mempool. In recent versions of Bitcoin, 0.12 plus, if the mempool size gets too close to the RAM capacity, the node sets up a minimal fee threshold. Transactions with fees per KB lower than this threshold are immediately removed from the mempool, and only new transactions with a fee per KB large enough are not allowed access to the mempool. Over time, the node decreases its fee threshold to put it back to the node's min relay fee. This threshold can be monitored using the get mempool info RPC command. Here is a snapshot of the mempool min fee over a random period of time. Mempool stats are available via our API on Mashape. More from Keiko. Keiko is the leading source of cryptocurrency market data, providing businesses with industrial grade and regulatory compliant data. We empower market participants with global connectivity to real-time and historical data feeds across the world's leading crypto exchanges.
So the only difference there is that Maximo is the proof of stake and Miner is the proof of work version, but it's pretty much the same thing, I think.
The future of Web 3.
And according to the article there that I just closed, is pretty much the way that I was thinking about, where each node has its own mempool, and the mempool is just the transactions that are unconfirmed, like they're before they get included. And that's the reason why I search for flashbots, because I think I want to understand how the private thing works, the connection between the flashbots and miners, and how the relays work.
As multi-chain. Turn your blockchain into a multi-chain hub with Turn. What is the difference between miner extractable value versus maximal extractable value? By Olusegun Joel Titus. The battle of the MEV in Consensus POW blockchain learning objectives. What is miner extractable value? MEV. Who are miners? Who are searchers? What is front running? Effect of MEV on transaction or memory pool? Mempool. What are maximal extractable values? MEV. Introduction. In a proof of work consensus blockchain, the use of miners to approve transactions and add new blocks to the blockchain for an immutable record is an integral part of the decentralized blockchain protocol. However, in recent times, there have been concerns about miners' extraction and ability to front-run transactions based on the amount of the gas fee submitted by network users, and also how other network users known as searchers could significantly increase transaction fees so that their transactions will attract the attention of the miners. These have led to an increase in proof-of-work blockchain scalability and transaction latency that affect throughput and finality. And consequently, with the issue around miner extractable value becoming significantly important due to bidding war and transaction throughput in a POW consensus blockchain ecosystem, it's important to simplify the impacts this has on transaction throughput and finality. And in a proof-of-work consensus blockchain, due to a small number of transactions per second (TPS) allowed by POW consensus blockchain, transactions are not immediately added to the block but need to be confirmed before adding to a new block hash. Hence, the transaction will remain in the waiting area, also known as TX pool. And while a proposed block transaction by miners is waiting in the buffer zone, nodes will run a series of validity checks on these transactions to see if the transaction should be added to the network or rejected. However, each node could configure its own rules for mempool, and a node could beta first to receive a transaction and may not propagate the transaction to the rest of the network. And this process gives miners and searchers the ability to manipulate transactions by front-running other network users. Network users known as searchers can also use a complex algorithm bot to front-run other users by inflating the transaction fee submitted to the block to attract the interest of the miners, and transactions with the highest fee will be approved while transactions with a lower gas fee will be sent to the bottom of the pool. Thus, miners control blockchain transaction inclusion, exclusion, and reordering transactions within the block they produce. What is miner extractable value? MEV. In an existing permissionless proof-of-work consensus blockchain, transactions in the pool or memory are ordered entirely at the discretion of network miners. Miner extractable value, MEV, is a measure of the profit a miner, or validator, sequencer, etc., can make through their ability to arbitrarily include, exclude, or reorder transactions within the blocks they produce. MEV gives miners and searchers the ability to use complex algorithm bots to manipulate the ordering of their transactions to include or exclude within a block by changing the transaction fee they pay to block producers. Who are miners? Miners are the group of peer-to-peer node operators that confirm transactions on a proof-of-work consensus blockchain by solving complex computational mathematics for a block reward. Miners get block reward incentives based on the number of transactions they honestly add to the block. All honest nodes append and add the same transaction record and timestamp locally. However, all nodes on a state machine operate synchronously by sharing a global clock and timestamp. Who are searchers? Searchers are network users who broadcast the transaction to the blockchain using a complex algorithmic bot to detect profitable miner extractable value opportunities. In a proof-of-work consensus blockchain, transaction order can also be manipulated by network users known as searchers as a function of the network fees they pay running complex algorithms on blockchain data to detect profitable miner extractable value opportunities and have bots to automatically submit those profitable transactions to the network. What is front-running? Front-running is a technique used by network searchers and miners alike to generate additional profit, where a transaction with a higher gas fee is broadcasted to the network by the searcher so that miners would pick the transaction with the highest gas fee over others and send a transaction with a lower gas fee to the bottom of the transaction pool. Consequently, front-running occurs when miners prioritize making a profit by arranging specific transactions right before the users, leading to the failure of the user transaction while the miner's transaction is successful and profitable. This occurs because miners possess the ability to reorganize, include and exclude transactions at their own will, using their position of privileged information to execute a trade first by taking advantage of the trading opportunities the user's transaction signal. The proliferation of the concept of front-running in a proof-of-work blockchain is the realization of the systemic configuration of the POW blockchain by network users, searchers, and node operators, miners, using complex algorithms redesigning transaction mempools. Furthermore, another miner extractable value technique employed by miners is called backrunning, where miners take advantage of how the execution of the user's transactions will affect market conditions and place their specific transaction right after the user's. What is the effect of MEV on transactions or memory pool, mempool? In a proof-of-work consensus blockchain, miner extractable value has contributed to high gas fees, network scalability latency, delayed transaction finality, and throughput. Miner extractable value affects transaction and market conditions using the front-running and back-running mechanism. And searchers and miners contribute equally to the issue of scalability faced by proof-of-work blockchains such as Ethereum, Bitcoins, Monero, and Zcash. And consequently, as witnessed during the Bored Ape Yacht Club, BAYC, other side, metaverse virtual land sales on the Ethereum network, which generated the highest gas fee in the history of Ethereum, where investors paid $176 million on fees alone in the 24 hours. Users embarked on a bidding war during minting, which increased slippage and gas fees. These led to a lot of failed transactions in bidding war where searchers and miners front-run others to purchase the virtual land first. This causes a lot of scalability and network congestion, which increases gas fees astronomically. And the establishment of miner extractable value, MEV, has provided dualistic effect and utility to proof-of-work blockchains in both good and bad ways. And the good use of MEV is in enforcing blockchain security and decentralization because of the peer-to-peer distributed ledger technology used by blockchain Toby decentralized nodes operation around the world and the ability to prevent Sybil and 51% attacks. However, another direct effect of miner extractable value includes but is not limited to DEX arbitrage, NFT MEV, and sandwich attack, which is a
So I think these articles here are probably really good. So I'm gonna read them all, I think. I'm gonna read them off stream. Depending on how long they are, obviously.
How does Flashbots work and how to use it? Flashbots is an organization that wants to democratize MEV, maximum extractable value, opportunities. In practice, this means that ordinary users who transact on Ethereum have mempool privacy and pay a lower fee for their transactions. How does Flashbots work and how can you use it? Ethereum is much more complex than Bitcoin because of all its possibilities of smart contract transactions. That is why selecting and ordering transactions into blocks has become a science, or art, that only few master. Those who do it well can extract a lot of fees by, for example, front-running trades. This requires a bit more explanation of what MEV is. Maximal extractable value, MEV, is the potential profit that Ethereum validators can scoop up adding blocks to a blockchain. They can maximize the money they make from block creation by reordering transactions within blocks and even insert new ones. It's a form of legal insider trading. Why insider trading? After all, the mempool, waiting line of transactions, is public, right? Well, theoretically, it is indeed open to anyone. But only few experts have the advanced skill set of how to interpret and benefit from these data. These experts make the profits. As someone has to pay for these advanced traders' profits, we can view MEV as a tax on users. The Ethereum community is working hard on a new and more fair system of MEV. Flashbots arose from this ambition. It is by far the biggest player in this new, corporate MEV industry. It has 80% market share. Become a premium Wealth Mastery subscriber to read the whole article.
Wonder which one is should probably read these ones first, I think. And then go back to flashbots. I don't like having a lot of tabs open.
The History of Casper, Part 1. Republished from the Ethereum blog at the request of Steve D. McKee. Vitalik suggested last week that I share my basic research and design philosophy in a blog post. I agreed but complained that it was still changing. My friend John West told me that everyone would really appreciate it if I told everyone about my Casper research. I mostly agreed. Then someone on Reddit told me to focus on Ethereum. So here's the Casper tech story, given as a chronological history of the evolution of the key technology, ideas, and language that are involved in Casper research. Many of our favorite blockchain personalities are part of the story. This is my attempt to recount everything in an accessible, sequential way so that you can see where we are now, and where we're going, with our research efforts, so don't argue until the end of the story. I'm going to try to release a chapter per day until it's complete. Also note that this is my personal point of view, understanding what little I could manage through the process of working on proof of stake. Vitalik and Greg Meredith's accounts will vary, for example, as they each have their own view of Casper research. Preface: How I started doing research at Ethereum. March 2013 to April 2014. I immediately got hooked on the blockchain technology story when Bitcoin first, really, caught my attention in March of 2013. This was during the Cyprus crisis, run-up in the price of Bitcoin. I learned about cryptographic hashes, digital signatures and public key cryptography. I also learned about Bitcoin mining, and the incentives that miners have to protect the network. I was interested in computer science and security for the first time in my life. It was great. Set against a narrative of dystopian libertarian economics, it was underground developers, like Amir Taiki, versus central bankers in an epic global battle to save the world from the fractional reserve banking system. The blockchain revolution was better than fiction. I consumed content on Reddit, listened to Let's Talk Bitcoin and a lot of Peter Todd content. I lost money on BTC, once because I took advice from the troll box. I argued with my friends Ethan Buckman and Zach Ramsey about technology. We learned about Mastercoin and the possibility of building systems on top of Bitcoin, taking advantage of its proof-of-work network effect. When I first heard about proof-of-stake, POS, in the 2013 altcoin scene, thanks PP Coin, I thought it sounded like heretical voodoo magic. Replacing miners with coins seemed like an inherently strange thing to try to do. I ended up deciding that the long-range attack problem was fatal, and any solutions were going to involve developer checkpoints of one form or another, an opinion I learned from Peter Todd. Being a Bitcoiner in 2013 was one of the most intellectually stimulating experiences of my life. In January or February 2014, I read about Ethereum for the first time. I watched Vitalik's YouTube videos, and I met him in person at the Toronto Decentral Bitcoin meetups. He obviously knew way more of the tech story than I did, so I became hooked in, this time on Ethereum. Ethereum was the promise of decentralization made accessible to me, someone without much background. It was general-purpose smart contracts that could do anything, disrupt any centralized system. It could be and do so many things that it wasn't always clear to me what role Ethereum would actually play in the blockchain ecosystem. The blockchain tech story, as I see it, took an exciting turn with Ethereum, and I got to be closer to the action. Having been invited by Russell Verbeeten at one of these meetups, Ethan and I went to the hackathon prior to the 2014 Bitcoin Expo in Toronto. Vitalik taught me how to use Merkle trees at this event. I was thinking about properly incentivizing and decentralizing the peer review system for a couple of weeks, having recently had a paper rejected from an academic journal. Ethan and I tried putting this kind of system together at the hackathon. Ethan did most of the hard work using Ethereum, while I very slowly put together the first GUI I ever made. We came in second place at the hackathon, after Amir's dark market, which became Open Bazaar. We got to meet the whole Ethereum team at the expo, and we got ourselves invited to the public Skype channels. Charles Hoskinson offered us jobs. It was then, in April 2014, that we started volunteering for Ethereum. We even got at ethereum.org email addresses. So I got into the blockchain space because I got hooked on the Bitcoin tech story, and then on the Ethereum tech story. I then got hooked on the proof of stake tech story, which I now know to be very compelling. I'm going to share it, being as faithful as possible to the timeline and manner in which the parts of picture have been coming together, in an effort to help bring everyone up to speed on our efforts. It may take a few chapters, but story time ain't over till it's over. Chapter 1, Slasher plus Security Deposits, the move from naive proof of stake to modern proof of stake. May 2014 to September 12, 2014. When Vitalik first expressed interest in POS to me in May 2014, first over Skype and then at a Bitcoin conference in Vienna, I was skeptical. Then he told me about Slasher, which I think he had come up in January 2014. Slasher was the idea that you could lose your block reward if you signed blocks at the same height on two forks. This gave Vitalik the ability to directly tackle, and arguably solve, the nothing at stake problem. For the uninitiated, the nothing at stake problem refers to the fact that the POS miner's best strategy is to mine on all forks, because signatures are very cheap to produce. It also opened up our imaginations to a new space of interactive protocols for disincentivizing bad behavior. Still, I did not feel very satisfied with proof of stake at this time, despite Vitalik telling me a couple of times that he thinks proof of stake is the future, because I was really in love with proof of work. So during the summer I mostly worked on proof of work problems, ASIC hard POW, security sharing between POW chains via proofs of proof of work, neither to completion. But I did suggest the use of security deposits to a couple of contract developers on a couple of different occasions. This planted the seed for insights made on the fateful post-Ethereum meetup night of September 11, 2014. Kudos to Stefan Toole for organizing plus getting me to that event. Ethan Buckman and I stayed up late talking about proof of stake at the Hacker instead of the party section of Amir Taki's squad in London. I connected the dots and internalized the power of security deposits for proof of stake. This was the night that I became convinced that POS would work, and that making it work would be a huge amount of fun. It was also the first time I experienced the surprising size of the POS design space, through long arguments about attacks and possible protocol responses. Since the early morning of September 12, 2014 I have firmly advocated, to everyone who would listen, that blockchains move to POS because it would be more secure. Amir Taki was unimpressed by my enthusiasm for proof of stake. At least Ethan and I were having the best time. The use of security deposits always significantly leveraged Slasher's effectiveness. Instead of foregoing some profit X, a provably faulty node would lose a security deposit, imagined to be on the order of size X/R, on which the block reward X was to be paid as interest, at rate R. You place a deposit to play, and if you play nice you make a small return on your deposit, but if you play mean you lose your deposit. It feels economically ideal, and it's so programmable. Adding deposits to Slasher meant that the nothing at stake problem was officially solved. At least, I had made up my mind that it was solved to the point where we could no longer understand why anyone would want to build a proof of stake system without security deposits, for fear of nothing at stake problems. Also on September 12, 2014 I met Pink Penguin for the first time, due to an introduction from Stefan Toole. I breathlessly recounted my POS insights made the night before. And after I respectfully declined a job from Eris Industries, now Monex, that week, Pink Penguin began sponsoring this research. Thanks. At this point in the story I was unaware of the other, multiple independent discoveries of the use of security deposits in proof-of-stake systems made by Jay Kwan, Dominic Williams, and Nick Williamson. Stay tuned. The next chapter is about the central role that ideas from game theory played in setting the design goals that led to Casper.
I'm gonna read this one more and then I'm gonna stop, I think. I still don't understand how, like, what is the logic that they use to determine that proof of stake is the best, or it's gonna work. Like, in my mind, it doesn't make sense.
The History of Casper, Chapter 2. Reposted from the Ethereum blog. This chapter describes the game theory and economic security modeling we were doing in the fall of 2014. It recounts how the bribing attacker model led our research directly to a radical solution to the long-range attack problem. Chapter 2, The Bribing Attacker, Economic Security, and the Long-Range Attack Problem. Vitalik and I had each been reasoning about incentives as part of our research before we ever met, so the proposition that getting the incentives right was crucial in proof of stake was never a matter of debate. We were never willing to take half of the coins are honest as a security assumption. It's in bold because it's important. We knew that we needed some kind of incentive compatibility between bonded node incentives and protocol security guarantees. It was always our view that the protocol could be viewed as a game that could easily result in bad outcomes if the protocol's incentives encouraged that behavior. We regarded this as a potential security problem. Security deposits gave us a clear way to punish bad behavior, slashing conditions, which are basically programs that decide whether to destroy the deposit. We had long observed that Bitcoin was more secure when the price of Bitcoin was higher, and less secure when it was lower. We also now knew that security deposits provided Slasher with more economic efficiency than Slasher only on rewards. It was clear to us that economic security existed and we made it a high priority. The bribing attacker. I'm not sure how much background Vitalik had in game theory, though it was clear he had more than I did. My own game theory knowledge at the start of the story was even more minimal than it is at the end. But I knew how to recognize and calculate Nash equilibriums. If you haven't learned about Nash equilibriums yet, this next paragraph is for you. A Nash equilibrium is a strategy profile, the player's strategy choices, with a corresponding payoff, giving $ETH or taking $ETH away, where no players individually have an incentive to deviate. Incentive to deviate means they get more $ETH if they somehow change what they're doing. If you remember that, and every time you hear Nash equilibrium, you thought, no points for individual strategy changes, you'll have it. Sometime in late summer of 2014, I first ran into the bribing attacker model when I made an offhand response to an economic security question Vitalik asked me on a Skype call. I can just bribe them to do it. I don't know where I got the idea. Vitalik then asked me again about this maybe a week or two later, putting me on the spot to develop it further. By bribing game participants you can modify a game's payoffs, and through this operation change its Nash equilibriums. Here's how this might look. Image upload broken, so. Look here, http:// Image upload broken, so. The bribe attack changes the Nash equilibrium of the prisoner's dilemma game from up, left, to down, right. The bribing attacker in this example has a cost of 6 if down, right, is played. The bribing attacker was our first useful model of economic security. Before the bribing attack, we usually thought about economic attacks as hostile takeovers by foreign, extra protocol purchasers of tokens or mining power. A pile of external capital would have to come into the system to attack the blockchain. With the bribe attack, the question became, what is the price of bribing the currently existing nodes to get the desired outcome? We hoped that the bribing attacks of our yet-to-be-defined proof-of-stake protocol would have to spend a lot of money to compensate for lost deposits. Debate about reasonableness aside, this was our first step in learning to reason about economic security. It was fun and simple to use a bribing attacker. You just see how much you have to pay the players to do what the attacker wants. And we were already confident that we would be able to make sure that an attacker has to pay security deposit-sized bribes to revert the chain in an attempted double spend. We knew we could recognize double signing. So we were pretty sure that this would give proof-of-stake a quantifiable economic security advantage over a proof-of-work protocol facing a bribing attacker. The bribing economics of the long-range attack. Vitalik and I applied the bribing attacker to our proof-of-stake research. We found that POS protocols without security deposits could be trivially defeated with small bribes. You simply pay coin holders to move their coins to new addresses and give you the key to their now empty addresses. I'm not sure who originally thought of this idea. Our insistence on using the briber model easily ruled out all of the proof-of-stake protocols we knew about. I liked that. At the time we had not yet heard of Jaquan's Tendermint, of Dominic Williams' now defunct Pebble, or of Nick Williamson's credits. This bribe attack also posed a challenge to security deposit-based proof-of-stake. The moment after a security deposit was returned to its original owner, the bribing adversary could buy the keys to their bonded stakeholder address at minimal cost. This attack is identical to the long-range attack. It is acquiring old keys to take control of the blockchain. It meant that the attacker can create false histories at will. But only if they start at a height from which all deposits are expired. Before working on setting the incentives for our proof-of-stake protocol, therefore, we needed to address the long-range attack problem. If we didn't address the long-range attack problem, then it would be impossible for clients to reliably learn who really had the security deposits. We did know that developer checkpoints could be used to deal with the long-range attack problem. We thought this was clearly way too centralized. In the weeks following my conversion to proof-of-stake, while I was staying at Stefan Tool's house outside of London, I discovered that there was a natural rule for client reasoning about security deposits. Signed commitments are only meaningful if the sender currently has a deposit. That is to say, after the deposit is withdrawn, the signatures from these nodes are no longer meaningful. Why would I trust you after you withdraw your deposit? The bribing attack model demanded it. It would cost the bribing attacker almost nothing to break the commitments after the deposit is withdrawn. This meant that a client would hold a list of bonded nodes, and stop blocks at the door if they were not signed by one of these nodes. Ignoring consensus messages from nodes who don't currently have security deposits solves/circumvents the long-range attack problem. Instead of authenticating the current state based on the history starting from the Genesis block, we authenticate it based on a list of who currently has deposits. This is radically different from proof of work. In POW, a block is valid if it is chained to the Genesis block, and if the block hash meets the difficulty requirement for its chain. In this security deposit-based model, a block is valid if it was created by a stakeholder with a currently existing deposit. This meant that you would need to have current information in order to authenticate the blockchain. This subjectivity has caused a lot of people a lot of concern, but it is necessary for security deposit-based proof-of-stake to be secure against the bribing attacker. This realization made it very clear to me that the proof-of-work security model and the proof-of-stake security model are fundamentally not compatible. I therefore abandoned any serious use of hybrid POW/POS solutions. Trying to authenticate a proof-of-stake blockchain from Genesis now seemed very obviously wrong. Beyond changing the authentication model, however, we did need to provide a way to manage these lists of security deposits. We had to use signatures from bonded nodes to manage changes to the list of bonded nodes, and we had to do it after the bonded nodes come to consensus on these changes. Otherwise, clients would have different lists of bonded validators, and they would therefore be unable to agree on the state of Ethereum. Bond time needed to be made long, so that clients have time to learn about the new, incoming set of bonded stakeholders. As long as clients were online enough, they could keep up to date. I thought we would use Twitter to share the bonded node list, or at least a hash, so that new and hibernating clients could get synchronized after their user enters a hash into the UI. If you have the wrong validator list you can get man in the middle. But it's really not that bad. The argument was, and still is, that you only need to be able to trust an external source for this information once. After that once, you will be able to update your list yourself, at least, if you are able to be online regularly enough to avoid the long range of withdrawn deposits. I know that it might take some getting used to. But we can only rely on fresh security deposits. Vitalik was a bit uncomfortable with this argument at first, trying to hold on to the ability to authenticate from Genesis, but eventually was convinced by the necessity of this kind of subjectivity in proof-of-stake protocols. Vitalik independently came up with his weak subjectivity scoring rule, which seemed to me like a perfectly reasonable alternative to my idea at the time, which was basically, have all the deposits sign every nth block to update the bonded node list. With the nails in the nothing at stake and long-range attack coffins completely hammered in, we were ready to start choosing our slashing conditions. The next chapter will document what we learned from our first struggles to define a consensus protocol by specifying slashing conditions. I'll also tell you about what we learned from talking with fine people from our space about our research. The game theory and economic modeling story presented here will continue developing in Chapter 4.
This is actually really good. Yeah, I don't think I still don't think that proof of stake works on the long term. But I might be wrong here. It might be like my Dunning-Kruger kicking. But yeah. Because I don't understand really well the whole game theory that they did there with the picture. And it's not very clear to me. Like, how does it work? And I think it might be possible that from the technical aspect if you're looking at the details of the blockchain, then it works. But if you're looking at the bigger vision and the whole infrastructure, like the whole space where everything connects outside of the blockchain, then I think that there's a very low probability that proof of stake makes sense. I think it doesn't work. But I definitely might be wrong about this, obviously. So, like, yeah, it's just a intuition kind of thing. Because it might be the case that based on game theory, like, even though your people are validating based on the amount of money they have at stake on the chain, that it works because of the incentives that they have. But yeah, it doesn't make a lot of sense to me. I think I want to read all of these actually because they are very interesting, these articles. But I think I'm gonna do this off stream. So tomorrow, I'm probably gonna come back tomorrow. If not, I'll come back 2 days from now. And I'm going to study this. I'll probably read one of these chapters again, probably the cryptography one, or read these articles here before streaming, and then when I stream, I'm gonna start with studying the source code here, and then I'll go back to reading the articles, and hopefully after I study those things, I can finally finish this article here. I mean, I can finish right now. I think I already have the knowledge, but I'm just gonna, because it depends on how detailed I want to go here. But I think for explaining what it is and how it works, I think it's pretty much, there isn't a lot of things that I need to do here. But I'm gonna wait until I reread all of this stuff and study the source codes, because it might be possible that I learned through the details, I learned something, or I mainly want to clarify the whole centralization thing. Like, what exactly is the relationship between the miners and this RPC and these relays, like the connection between the MetaMask and the Flash bots, and the difference between different RPCs and how they connect with the miners. That's the stuff that I want to clarify. So hopefully I can do that tomorrow. So yeah,